Thank you, everyone. And so I want to welcome everyone to our fall symposium for the Duke University Program in Environmental Health and Toxicology. We are focusing this fall on emerging contaminants in the ambient environment. So this symposium is intended as a forum for us to talk about this issue of emerging contaminants and specifically polyfluorinated alkyl substances in water and how North Carolina is beginning to address these. I want to make a special welcome to our lawmakers who are here joining us. So we have senators and representatives from the North Carolina General Assembly and also distinguished guests. This issue of emerging contaminants in the ambient environment has really become a hot button topic in North Carolina, especially over the last few years. And so you'll hear today about some of the reasons for this. Specifically, hopefully all of us have been aware of the issue of the Gen X PFAS compounds and the related compounds that have been found in the Cape Fear River. We'll hear more about that from Dr. Mark Striner and Dr. Detlef Knappe today. Also, issues related to coal ash and coal ash pollutants that have been released into North Carolina waters. And then, of course, most recently, issues that are related to compounds that may have been released into our waterways through the flooding that is coming with major episodic storms such as Hurricane Florence, issues related to agricultural runoff, industrial contaminants, and other compounds that may have entered the water through these storms. So I think it's actually quite apropos that I stand here today exactly 1 year after I stood before the North Carolina Select House Committee on North Carolina River Water Quality as a representative of the North Carolina Coastal Federation with Rob LeMay. And I talked to the General Assembly about the issues surrounding emerging contaminants. And the basic premise was, how do we answer the question of the ability to avoid a situation such as we had with Gen X from happening again? How do we keep this from happening again? Right? And so in that intervening year, I had conversations with colleagues. Many of my colleagues also talked to lawmakers and policy stakeholders about these issues. And so this culminated after conversations in particular with Senator Michael Lee, who's actually here joining us right now, where he came to my laboratory and actually met with other members of our scientific community to talk about emerging contaminants and how we can address these compounds in our waters from a more holistic standpoint. So those conversations culminated in the drafting of bills that eventually became law in North Carolina, instituting a new network for monitoring PFAS compounds in North Carolina, surface water, drinking water supplies, and groundwater drinking water supplies. So this is an enormous step forward hopefully in water quality protection for North Carolina. This is, I think it's safe to say, at least in scope, the most comprehensive PFAS monitoring program for water in the United States. So we're really excited about that. Yes, thank you. All right, so the symposium. What are we hoping to accomplish today in our symposium? Well, so we have a number of speakers that are selected to give perspectives to guide future monitoring in North Carolina. So specifically, we're going to highlight international and national perspectives on emerging contaminants in water and how to assess their occurrence and risk. So we've invited colleagues from Switzerland. So my colleague Matthias Ruff will tell us about how the Swiss have instituted comprehensive emerging contaminant monitoring in drinking water supplies and rivers within Switzerland, specifically the Rhine River Monitoring Program, which can really serve as a model for how we can institute this sort of monitoring program in the United States. Also, experts who are going to tell us about the state of the science and perspectives on the state of the science for PFAS. So Professor Chris Higgins, who's a leader in the field of polyfluorinated alkyl substances and their fate, transport, and occurrence in the environment. Also, we'll hear from Dr. Gloria Post from the New Jersey Department of Environmental Protection, where she'll share some of the perspectives of New Jersey and how New Jersey's state environmental management agency has handled the issue of PFASs, both from a risk and a current standpoint in their waters. And then finally, we'll in the morning here, we'll hear from Dr. Mark Striner, who is a scientist at the EPA here in RTP, and he's going to talk about new developments in the identification and the discovery of novel PFASs, both here in North Carolina as well as other areas of the country. And then so after lunch, we're going to switch gears and focus on descriptions and perspectives related to the newly instituted PFAS Monitoring Network Consortium. So we'll hear from Professor Detlef Knappe, who's done such great work here in North Carolina and other places, but specifically to talk about GenX and other PFAS compounds and the landscape of PFASs in our ambient waters. And then so we'll have a discussion of the policy context. And so we'll have our lawmakers come up and talk, led by Jeff Warren, our scientific director for the North Carolina Policy Collaborative, is going to guide this panel and discuss the legislative and policy context of PFAS and emerging contaminants in water. And then we'll finish off the symposium with a description and a summary of the projects and the specific goals, aims, and objectives that are going to be addressed through this PFAS monitoring network. And so I really want to thank not only all of you for attending, but also our symposium sponsors. So this is actually a relatively unique symposium. Typically, this symposium for the Duke University Program in Environmental Health and Toxicology is sort of run within Duke, but in this case, we've partnered with institutions who have provided co-sponsorship. They're up here, so certainly Duke and the Superfund Research Center and NIEHS Superfund Research Program has helped support this symposium. Also, the UNC Center for Environmental Health and Susceptibility and the Gillings School of Public Health have provided important support. Very importantly, the North Carolina Policy Collaboratory has contributed significant support for this symposium. So I want to thank you all for the support and the sponsorship. Okay, so with that, I want to introduce our first speaker. So we're very honored to have Dr. Matthias Ruff here from Switzerland to tell us about perspectives on emerging contaminant monitoring in Swiss surface waters. So I've known Dr. Ruff for a number of years. He was one of the pioneering researchers that instituted the original Rhine River monitoring program for non-targeted emerging contaminant analysis. And so he's going to tell us about how that program has evolved and expanded. So, Matthias?
Yeah, Lee, thank you for this very warm introduction. I welcome you to the first presentation today about emerging contaminants monitoring in Swiss surface waters. I'm very happy to speak here today, and but give me in the first minute the opportunity to quickly introduce the four actors, the four institutions which were involved into that project. The first is the ERWAG, the Swiss Federal Institution for Aquatic Science and Technology, where I did a postdoc in the group of Heinz Singer for about 6 years, where we produced most of the results I'm going to present now. He's working in the group of Juliane Hollander. She's the head of the Department of Environmental Chemistry. So the idea was then to transfer all the knowledge from a research institution directly to a local authority. In this case, it's the Office for the Environment and Energy, Basel City. So in this, here at the institution, I work together with Stefan Rupper. He's in the group of Jan Masacek, the head of the laboratory. They are today responsible for the quality of the River Rhine. All this work wouldn't have been done without one very smart brain. This is Martin Loos, who did a PhD project at ERWAG, and he developed all the software approaches and the software solutions we needed to deal and handle all these data which are produced every day. And the idea for the whole project came from the Swiss Federal Office for the Environment. They initiated a project to do this know-how transfer directly from science into the authorities. The head of this department was Christian Loy. So, and all over this, I had the job to really handle these different institutions, all the different projects. I had to bring them together, and after this project, ERWAG, I'm not anymore working in research now. I'm working for a cantonal authority in Bern. It's kind of a state authority at the laboratory of the Office for Water and Waste. So, we fly to Europe quickly. The River Rhine is in the heart of Europe, so I can easily say that the Rhine is one of the most important rivers in Europe. So it has a length of 1,200 kilometers in a huge catchment area, and the total discharge transported from the Alps to the North Sea is 2,300 cubic meters per second. So if you transfer this data to Switzerland, already in Basel, so where the Rhine leaves the catchment area of Switzerland, it's already 1,000 cubic meters per second, and they are living 6.5 million people in the catchment area. So for Switzerland, the Rhine is also for a very high interest, because 70% of all the land area, all the water from this land area goes into the catchment of the River Rhine. So it's very interesting to see what happens in this river. If this is not only enough to do monitoring, the number of 20 million people who get directly or indirectly water from the River Rhine is a reason to do so. But the question why monitoring comes from a different part. So I want to show you now a very short movie about an accident happened in 1986, and this changed all the minds in Europe.
On the night of November the 1st, 1986, a huge fire destroyed a chemicals warehouse belonging to the Sandoz company, now Novartis, in the Schweizer Halle in Basel. 1,300 tons of poisonous chemicals went up in flames. The chemical store had neither smoke detectors nor sprinklers. And since there was no retention basin, the water used to put out the fire and chemicals flooded into the Rhine. At that time, no one knew this would have a major impact on the environment.
The red colour became a symbol of the poison. It was mainly phosphate esters and highly toxic pesticides that killed the fish.
The Rhine was contaminated over a 500-kilometre stretch. Only after closer examination of the ground and water did the specialists discover that the chemicals mainly consisted of poisonous quicksilver compounds from common pesticides. Following the catastrophe, a risk map has been worked out. Today, the storage sites feature retention basins as well as fire protection installations. But the transportation of an annual 12 million tons of dangerous chemicals in the region still poses a potential risk to the environment. A measuring station and a warning centre monitors the water quality of the Rhine on a daily basis. A system of tubes absorbs the water from 5 different places and pumps it into the measuring station. This allows an analysis of the origin of possible harmful substances. Thanks to these measures, today the Rhine is in a healthy state again.
So the last sequence was the presentation, now in 15 seconds summarized. So I'm talking today about this monitoring station. It was a shock for not only the population but also for the authorities and the industry. A lot of things changed since 1986 that this don't want to happen anymore. So the monitoring station which was installed is that directly at the border between Switzerland and Germany, where the Rhine now leaves Swiss territory and enters Germany. So the goal of such a station is to monitor long-term trends and to detect accidental spills, and with that also to localize, if ever possible, the polluters. So it's not so easy to monitor a river which has already 180 meters of broadness at the point of the station. As you already heard in the film, these five places where the tubes are mounted in the river basin help us to get a representative sample at this point, but the Rhine has a laminar flow at this point. So this means when we have an entry into the river, it will stay at a certain position in the river, it won't mix. So this is the reason why we need these 5 places in the river, but this is also a very good possibility for us to do the polluter localization. So the Rhine, the water in the Rhine is influenced by 5 sources. So at the right and at the left side we have 2 tributaries on the Swiss and on the German side, and then we have 2 industrial influenced wastewater treatment plants entering the River Rhine. So if there is any entry or any chemical coming into the Rhine, it will always give us a kind of concentration profile over the broadness of the Rhine, and so analyzing this cross-section gives us always a first hint of the localization of the polluter. So what are the requirements for monitoring? So sure, we want to have quantitative methods, we want to be actual, universal, we should measure everything, it should be contemporary, and it shouldn't cost too much, so we have to be efficient. So what they built up before we started the project, there are a lot of online parameters measured, some parameters, and inorganic stuff. So I don't focus on that, I focus on the organic analysis. There, as you can see here in the scheme, the methods are mostly influenced by GC and GCMS measurements. This made sense in the earlier years, but now in the last years we got a huge better instrumentation on the HPLC side, so we could more focus now in the new project on the polar substances, which are much more water soluble and not volatile anymore. So the goal of the project was to improve this side, and the result I can already show you here. We introduced a non-target screening, an unknown screening on the polar side, and we increased the number of targets we are measuring dramatically. So what is now the difference between trend monitoring and spill detection? So trend monitoring means we deal with known substances. We always have a question: what do we want to monitor over time? And we can just deal a limited number of substances, because otherwise the data would explode. But what we need for that is an exact quantification. In opposite of that, a spill detection, we deal with unknown substances, we deal with an unlimited number of substances, and the first thing is we have to detect them, we have to identify them, and we need a rough estimation to answer what we have to do. So the analytical strategy behind this was to implement a target analysis, and with them also a non-target analysis. We introduced at the station a high-resolution mass spectrometer. This instrument produces every day 2 times 50,000 peaks. So we measure in positive and negative mode. This means double of the peaks we are producing every day. And now we need algorithms to handle all these data. On the target side, we define 50 priority substances. So a priority substance is that we really do a manually processing of this data. We want as good quantification as possible. And sure, we do a standard calibration because it's a target. We have it in lab. And then we defined 250 site-specific substances. This is a list of substances which can vary over time. So we are more flexible on this side. We're just doing an automatic processing of these data and a semi-quantification. So the substance diversity we are measuring at the River Rhine is divided in a lot of pesticides we have on the target list, also pharmaceuticals, but also biocides, industrial chemicals, drugs, and sweeteners, and so on. So this is the normal program for doing a monitoring. Let me show you now a few results of all these measurements. I brought you now the results of the 24 hours composite samples of diclofenac, which is a very often used painkiller in Europe. I think it's not that important in the US. So here you see the concentration curve, but it's always hard to deal with concentrations. This is more for the ecotoxicology, but if you want to know more about the load and if you want to interpret the data, we calculate this together with the discharge, with this in the back in blue, without a scale, and so we can see how the loads, the daily loads, behave over this 2 years period, 2013 and 2014. What you can see is that we have an entrance of 2 to 4 kilograms of diclofenac every day coming from the wastewater treatment plants. So we have less in summer times and more in winter times. This also makes sense because there is a photolysis taking place inside the river, in the upper layer of the river, and so we lose some substances in summer. And what you also can see here in the graph are the sparks, and they mostly follow the discharge. So these are stormwater overflows from wastewater treatment plants in Switzerland. And as you can see, here in June in 2013, there was a very big event, a very big rain event over whole Switzerland. There were 4 times more substances flooding into the River Rhine due to these stormwater overflows. These are very nice curves, and we can produce these curves from all of the substances we are measuring. I just show you 2 more examples. One is isoproteone. It's a herbicide used just in agriculture. And what is interesting here is that you clearly can see in the River Rhine, you can see the seasons. You can see the 2 application times in spring and in autumn every year. And especially in the first spring season in 2013, we saw again a huge rain event which flooded 35 kilograms of the isoproteone down from the fields into the rivers, and we could detect them at the monitoring station in Rhine. This was 1/3 of the annual load. This event just flooded us 1/3 of the annual load into the river. So the last example I brought to you is saccharin. It's an artificial sweetener. Maybe the one of you had it in your coffee this morning. And as you can see here, this is a very special curve. So we see some single events, 5 single events in 2012, where we had more than 200 kilograms per day entrance into the river. It was not clear to us at this, so we had no handling at this time to really detect the source. But what we can say is that this didn't happen anymore in 2013 and also the years later. So this was a kind of single event. We don't know where it came from, maybe a harbor or something else. So the concentrations rise to 3.6 micrograms per liter in the river in 2012. And the important thing is that always when you have these sparks, this doesn't relate anymore with the discharge. So it's a clearly single entrance into the river. And there can't just be an industrial source behind this. So I come back to this slide because there are still 15,000 peaks per measurement waiting. And this is now the non-target analysis. All the remaining masses are the possible unknown substances. And now we have to deal with them. So for unknown substances, it's clear. We can't do any calibration. The concentration can just be estimated, and we need automatic processing for that. So. And what we are doing in this processing is we ask today the question, what is with this sample different to all the past? So how did the Rhine behave today different than yesterday? So with all these masses, we are doing a statistical analysis on the time profiles. We get over years now. Now we have time profiles for more than 5 years. And we look for changes and trends in these profiles. And all time when we have a big change, then this gives us a prioritization. The program doing this for us is NVMS. We developed together with the PhD student who have now his own small company developing this kind of workflows. So the most important thing is here the prioritization. The program has to tell us what is important today. So how do these time profiles look like? I brought you here one example, and this is a very, very good case to demonstrate the whole business, because we can see everything on this picture. So you see first, you see a time where nothing happened in the Rhine, so we didn't get a signal, so we didn't have to react on anything. Then we see a time when the substance, the green line, started to appear. So there was a substance measured, but it had no effect. It was not on the prioritization list, so we couldn't do anything. We didn't see it. But then at a certain point, the concentration increased dramatically, so we had it on the prioritization list and could do identification of this substance. And then 2 months later, we had a big spill. In this case, it was tetracline. It was a tetracline spill. This is a solvent often used in the industries. 3 tons were brought into the Rhine in between a 3 weeks period. And after we talked to the companies, if we are able to locate the polluter and we can talk to the people, they are maybe also punished, then you can also see that the concentrations go back dramatically and we don't see the substance anymore. So I brought you a second example here with indomethacin. We had this already on a list. So there's a long section where we didn't see this substance at all. And then in between 8 days, the concentrations rise, and we have a perfect peak in this time profile. And the software is exactly trained to identify these profiles and give us the information out that we can react on this. Also in this case, the source was located. We had concentrations measured with 0.4 micrograms per liter, and over 14 days, 170 kilograms flood into the Rhine. And the last example I brought here is a bit a much more difficult case. So there might be also continuous entries we want to measure, and this is not so easy anymore to come along with these statistical approaches. But although this is possible, so we called it first the non-target 141. We didn't have any information, but what we see is that we had some kind of gaps in this curve, and these gaps perfectly matched with the vacation in Germany. So we thought maybe this could be a company located in Germany. So good conclusion. So when the process started, so if we have a known target, we have to identify this. So the first thing is we need the molecular formula. So we get this by fitting our data with just a mathematical approach to combine some elements. And in this case, we got a very, very strange elemental composition. It's a C7H2N4. So H2 in an organic molecule is very rare. So first I thought, come on, this won't be anything. So we did a database search and were surprised that we find even 6 entries for this very special substance. So in this case, we used the ChemSpider database. So the in silico fragmentation things, we tried out, found 3 likely structures, but then we stopped. We didn't find any entry in a spectral database, so we had no comparison, and we also couldn't find a vendor selling us one of these 3 products. So normally, or usually, the story would end here. But during this project, we also built up a very good cooperation to the Basel industry, to the local industry and chemical companies who helped us in these cases to identify substances when we don't talk about them. or when we don't publish them and the company name. And this works very, very good. And in this case, also, the polluter reacted. On our request, he provided us a standard substance, and then we could identify this as tetracarbonitrile 1-propane. This was an unwanted byproduct in a synthesis. The average load was 800 kilograms per month. So the company after that reacted and worked on the processing of the wastewater, and we could reduce the emissions by 80% now. So this is a really success. But over the all time, when we measured this, it was 16 tons of cumulated load. So the monitoring just works when we have an international network. It's not only done if we measure somewhere in Basel and then the river takes it away. So along the River Rhine in the last years, or also in former years, there exist 6 other of these monitoring stations, and also in the last years there was built up a very good communication between these stations, so they inform each other what they are measuring. There is a kind of alarm activation plan, which means that they ask, we saw substances, do you also substances? So the important thing is that they start to cooperate, that they start to talk to each other, and that they use kind of similar methods. Otherwise, it is very hard to compare the data. But in this case, it worked. So all the governments along the River Rhine pushed these projects to build up more stations and to push the communication between these stations. So a very special, so a little special is here that we have different alarm values for known substances, for known active substances, which are pesticides, pharmaceuticals, and for other substances, which could be solvents or things like this. And there's always a regional alarm system where the station talks with the industries itself, and an international alarm plan where then all the other countries are also informed about that. So in 2014, we managed to identify 11 of these alarms along the River Rhine, and when we now compare the total annual load of wastewater treatment plants coming into the River Rhine from municipal wastewater treatment plants and compare this to the industrial load we got, then we see that there is still a big difference. So we have 100 tons per year coming from the wastewater treatment plants from households, but just 24 tons per year coming from the industries throughout these accidents. But in the next years, the Swiss government decided in the next 10 years to introduce a new cleaning step into the wastewater treatment plants, which will reduce the total load coming from municipal wastewater to down to 40%. So this means then we are coming in the same range. So there's still a lot to do, and in the future, this monitoring station can also show us if these strategies worked to reduce the load from the treatment plants, but also to get more information about the industry. So let me now give you 3 examples why I personally think that the monitoring is really working. So I hope I can convince you. So first, at the very early stage of this project, we could measure an accident spill in Basel. So we thought, come on, let's go a little bit downstream, get the samples and measure them with our own method and compare the data. And when we finished that, we were talking to another institution located in between, and they said, oh yeah, we are also measuring this substance. Come on, you can take our data. And now, when we calculated the load of all these 3 events, we can see that at the other stations, with our almost 300 kilometers downstream, that we almost measured the same load at these concentrations. So we have a gap of 5 days in between, and we are 300 kilometers downstream. So this means that the substances are somehow conservated in the river. They flood as kind of a wave through the system, and we can measure them at any point. So the second example is a point source in Switzerland. I was working with a master student on a project in a wastewater treatment plant. So we measured over 3 months daily the effluent samples. And then we did a non-target analysis, and then we found one substance with a very high impact. So we have very high intensities. And then we thought maybe we can see these single point source also at the monitoring station. And voila, we could find it. So if we do an overlay of the wastewater treatment plant peak and the monitoring peak we found at the station, sure, we have lower concentrations. This is just a single event somewhere in Switzerland. We have again a 5 days delay between the samples, but we have almost the same dynamics in the river. And this was a single source. And the third example is also a very interesting one. We have substances we always see, so in a kind of production pattern. We have recurring patterns. And in this case, we found a company who was producing a product, and they emitted in 2013 more than 1 ton of the substances. So we had to talk to the company, and then they shouldn't have done this again. But in the next year, we just saw that we just have a dilution. We didn't have a reduction, we just had a dilution. So we measured 3 times longer, third of the concentration, but the same load, exactly the same load. So it was exactly the same production process leading to this peak. So in principle, this is a criminal act. So at the end of the presentation, I would ask if there is a possibility to do a Rhine monitoring extended. So now I'm working not anymore for the river monitoring station, not anymore for ERWAG, so I'm working for a canton laboratory, and there I thought so, yeah, now I have the most important tributary in Switzerland for the River Rhine. This is the River Aare. So for your orientation, in light blue is the River Rhine, and in dark blue is now coming the River Aare, going through the canton of Bern and then entering the Rhine. So as it is the most important tributary, I thought it must be, so it would be really a benefit if we could do also a daily screening at this river. And I could convince all the people in the canton Bern and the authorities to install from beginning of next year 3 new sampling stations. So the one is just driven by alpine water. So this means there come clearest water down from the mountains. It goes through 2 big lakes where the raining time is more than a year. And so this is our reference point where we start the screening. Then the River Aare enters the Midlands where all the people live. We have wastewater treatment plants, and in the canton Bern we have a lot of agriculture. And so we are going to install a second station before the River Aare enters a lake again. This lake is an important drinking water reservoir, so we have a very good control how the water quality should be in the lake in the next years. And this convinced especially the authorities. And we install a third monitoring station when the river leaves the territory of the canton Bern. So with this, I will already come to the conclusion. So the monitoring station provides a very deep insight into a river. We can really follow and we can really see what happens in the catchment area. This can be very interesting. You see the seasons, you see some illnesses coming on. So you see in special seasons some special medicaments coming and leaving again. So the trend monitoring can be realized by a targeted approach, and the spill detection can be realized by a non-targeted approach. But this also needs huge data processing softwares, and it needs adapted and very intelligent algorithms to deal all this data. But the monitoring station, I could show, works over hundreds of kilometers and even in a complex river system. So it is best when all these monitoring stations build up a communication system where they learn to talk to each other, which should be normal in principle. And at the end, all this could help to reduce by identifying the polluters and introducing also or keeping the door open to the chemical industry. So with this, I want to thank you for listening, for inviting me. I'm open for questions.
Okay, thank you, Matthias. And we have time for discussion, plenty of time for discussion. So if you have questions, please.
So fascinating talk. I can only hope that we can get there one day also here. But I have a question, and that's related to sample preparation. I wonder whether you use any kind of extraction to prep the sample first, and whether that may lead to losses of certain compounds in your analysis.
Yeah, actually I skipped this a little bit of the presentation because I thought it's maybe not that interesting. So, I don't know if we have more chemists or not. So, so sure, the sample extraction is be done. Until now, it is still done with a multi-layer solid phase extraction, which costs us the whole morning. So the challenge in this project is also the restricted time for the alarm. So half a liter is extracted to 0.5 milliliters, and then we are measuring over the midday. So we have the results in the afternoon, and then all these algorithms start to work. Martin Lowe's workflow is called Ambient, and this picks us out single points in these 15,000 peaks we get every day, and then we are doing the analysis, so time profiles over time. Yeah, this is in principle what we are doing. So it needs to really reach low concentrations. It needs an enrichment step. In this case, it's a factor of 1,000. But this was installed 2012, 2013. I think we are now a little bit better. Maybe we can also work in the future with direct injection.
Thank you for that wonderful talk. I'm wondering, when you found something in the river and you could point to a responsible party, you mentioned a little bit about sort of that interaction, whether it was or was not something that was breaking a law that was being released, and how the interaction with those responsible parties went.
This is a good question. So I am the analytical chemist, and in principle, when I identify the compound and I also find the source, the story ends for me, and then it starts. So now I'm working also for authority, yes, but at this time it was clearly that it was clearly separated from the part where really then the companies were contacted by the government, and that they were discussing if they broke the law or not. So there is a clear definition of this workflow, but yeah, it wasn't in the focus or in my focus, but this is happening, yeah.
Thank you. This is really exciting to see. I'm curious, for capital and operations cost, how much does it cost on an annualized basis, and where does the funding come from?
So how much does it cost to drive this monitoring station? Haha, okay. So first, there are a few people paid by the Swiss Federal Office for Environment to do this work there. I think they have 5 people working for them, just doing the workflows at the station. So to deal with the station, to deal with the water, and to do the analysis in the lab to produce results. And additionally, for running the monitoring station, I think this is more than $500,000 per year.
The source of the funding?
The source of the funding is mostly the Swiss Federal Institution for Environment.
Fantastic talk. I'm wondering if these data are available to the general public or to other scientists such as epidemiologists and toxicologists, so that they can start to make associations with potential health outcomes?
Yes, sure. All these data are public because They are paid by taxes. So what they are doing is they make a not very comfortable to read and sure in German published annual report at this station, but they are working on that. And in principle, if anyone asks them a question, do you find these substances, do you find this mass in the River Rhine, they should be able to give us an answer. No. Or they have to give us an answer.
Thank you so much. I was wondering, you mentioned kind of briefly that the companies provided you like a standard if you agreed to not release that they were the source.
Mm-hmm.
Is that agreed upon internationally, or is that just localized? And how does the government agree to that? I'm just concerned.
So the government was involved in all this process, and at a very early state of this project, we built up a group together with the industry to discuss what we are planning there at this point and how we will deal in the future with the data. And for the chemical industry, it was the worst case that we publish this data, that we publish the polluters, or we publish really that others could say, okay, it was this company. So the deal was that they cooperate, and in this case, when they cooperate, we don't go to the press or something like this. So, and this is, I think, a good deal. How to really share this information on a basis where they trusted us, because we were scientists and they know we wanted to publish. But as it's now in the hand of the local authorities again, and not in the hand of the ERWAG again. So this shouldn't also be a problem, because the local authorities, in principle, are not allowed to talk about their daily work. So, yeah. But it's still a good cooperation, and it was very important for the success of this project. So,
Matthias, a really nice example of combining the chemical data with the river discharge data. I mean, the chemistry is wonderful, but of course, without the river discharge, you would not know the loading and the massive chemical released. So it's a nice example of emphasizing the importance of stream and river discharge measurements. Do you know what method is being used there to measure the river discharge?
Yeah, so mostly we relied on the stream of the River Rhine through Basel is very, very controlled. So we exactly know the profile, so we can directly go via the speed and the niveau measurements. So it's not that tricky to get a good value for the discharge, because the river is completely controlled. There are two power stations, one downstream and one upstream, and so the Rhine is completely regulated in this part. So this is also a reason for the laminar streaming of the river, and so this is not the big problem. It's not fancy.
Thank you for the talk. There's a question that you might have mentioned, but I might missed it. With limited numbers of monitoring stations in the river, when you see a contaminant spike, how did you locate a specific factory? Or it's because there are just so little around there, this is the only suspect?
Okay, you're right. So yeah, so we have one big monitoring station, but along the River Rhine, there are different small samplers located. So in principle, we have between Basel and the Alpine region, we have 11 power stations. So where the Rhine is regulated, and in principle, we have 11 ponds, big ponds, where the river flows, and then it's made energy, and then it goes to the next ponds. So in each of them, we have a sampler located, and so at each power station, the Rhine is mixed, and then it flows laminar to the next station. And so when we find something and it comes not from the Basel city itself, it comes from upstream, we go along the River Rhine, go to these sampling stations where just the sample remains in the sampler and is changed in between two weeks or so. So after 2 weeks, so these are cool samplers, and after 2 weeks, we just let the water go and fill it up with the next sample. And this works pretty good to localize at which point we saw this substance the first time, and then we start to distribute to the tributaries and to the local authorities at this time.
Thank you. That was a really nice talk. I'm hoping that you have some slides in the back here, in your back set, on the perfluorinated chemicals. Can you share any information on which ones you might be looking for, or how you're looking at them on the non-targeted, maybe some of your non-targeted approaches?
Yeah, this is, I'm not so good prepared on this. So I talked to different people. How is the situation in Switzerland? And all the people are convinced. So we are measuring some perfluorinated substances, but just the very common ones like PFAS, PFAS, and so on. So, so the traditional substances, I would say. But in this case, there haven't been done a lot of work, actually we have no idea. We have no idea. So we don't measure high concentrations of PFAS at the monitoring station. I checked the data last week. And we see in some wastewater treatment plants, in some project of authorities, we see some discharges, but not very high amounts of. But it's all the topic is PFAS. So all the topic is PFAS, and so yeah. So it's not the isolated new substances which are in the focus now, and I don't know who would work on this in the next years. So yeah.
So, Matsu, I'm going to take the chair's prerogative for the last question. So, one of the things that we really struggle with chemical prioritization is we've got this enormous list of compounds that are used in commerce, and then narrowing down the ones that are really important is difficult. This monitoring station and the data that you're generating, where you have both identifications of new compounds through the non-target approach as well as proposed loadings, it seems to me that that's a really great resource for helping to inform lists and prioritization. So does the Swiss and maybe the EU environment agencies, do they use your detections and identifications to help push compounds up in the priority list for assessment of toxicity, or do they make their way onto regulatory lists? I mean, it's kind of related to this, the first question that Mark asked, actually. But how does the agency interface with your identifications?
Yeah, so the Federal Office for the Environment is doing that. They are pushing some substances. They try to communicate what we are seeing, and they are really convinced of the system. But as the most of you might know, Switzerland has not the best position in the European Union because it doesn't take part. So, which is an advantage, but sometimes also a disadvantage. And in this case, yeah, so they participate in these discussions, but if they really can push them to a high level, I think maybe not. So, yeah. But the other institutions in Germany, where we have very good cooperations, they doing the same, and they really start to push these international lists, this US. Yeah.
Okay. All right. So let's thank Matthias again. Okay, so I'd like to introduce our next speaker, and this is Professor Chris Higgins, who is coming to us from the Colorado School of Mines. I've known Chris for many years. I met Chris at a bachelor party, actually. But he's a world-renowned expert in the area of polyfluorinated compounds in the environment. And so he's going to talk to us about the challenges we face in measuring and understanding these compounds in water. So, Chris? Got a laser pointer in there in the advance.
Great. Thank you, Lee, for the introduction. Yeah, we actually met before grad school at a bachelor party, so we can talk about that later. But I was asked to come talk about PFAS and specifically about the challenges addressing these compounds, particularly in water phases. And I'm going to talk through some examples of some of the work that we're doing and applying tools such as high-resolution mass spectrometry to addressing this question of looking at these broader suite of compounds. I also like to start with a thank you to all the folks involved in the work. So there's a number of PhD students and postdocs and collaborators. You'll note a couple familiar names on that list there. And I have started a tradition in my research group of going out on the river every summer. And so when we get a lot of water in Colorado, this is what we do. We don't quite get as much as you guys just got. But you know, this really is, the work I'm going to be presenting is really representative of a lot of efforts from a lot of different folks. And so I just want to acknowledge all the hard work from the graduate students, postdocs, and collaborators that went into this. And the world, with respect to PFAS, at least in the US, I should say, really changed on May 19th, 2016. Incidentally, I had just left here. I had lunch here with Heather and Lee at this very hotel a few days before this because I had been doing a sabbatical here. And what happened on May 19th was EPA released their health advisories for PFOS and PFOA, PFAS and PFOA, two of the compounds that are most commonly studied. Those of us who've been working in this area were not terribly surprised that they did this, but there were some water systems that were a little bit caught off guard by the relatively low levels of these two health advisories that were issued in 2016. Of course, this is a national issue. I know the focus here is North Carolina, but this is a national issue. And if you go back and look at the data collected under the Unregulated Contaminant Monitoring Regulation, the UCMR, where they looked just for 6 of these compounds, including PFOA and PFOS, they did see these compounds in some large water supplies, about 4% of water supplies. But one thing to keep in mind when you look at that data is the relatively high reporting limits of the data collected under the UCMR3. When you go and look more closely at where those compounds are being detected, there are some associations with industrial releases, some associations with also military bases, and really pointed to the fact that there might be releases of these compounds in these firefighting foams, which I'll touch on more, and that might be contributing to the fact that these compounds are being detected in the water of really millions of Americans. Of course, there was a lot of press about this. The New York Times Magazine had this article. 5.2 million Americans were informed that their water was above the health advisory. National Guard being mobilized in West Virginia. Alabama, 100,000 people were told that their water was exceeded the health advisory. In Colorado, it was about 80,000 people presumably impacted from a firefighting foam release there. And of course, this is kept up in the news. And just 2 or 3 weeks ago, there was a House hearing on these compounds. And just on Wednesday, there was a Senate panel hearing in the U.S. Senate about these compounds and the challenge these compounds give us in terms of a national issue. So I was tasked to talk about PFAS. I need to provide a little bit of background. I think there are a number of folks who are very familiar with these compounds, but for those who aren't, I'm just going to give a little bit of an introduction. I am going to talk about PFAS and not PFCs because this is some older terminology that was used and is a little bit confusing. And so we try and avoid PFCs now and really talk about PFAS because that represents the diversity of the chemistries that are at play here. So it's not just the perfluoroalkyl acids, the PFAAs, which we traditionally have focused on, but also these polyfluorinated compounds. And these compounds contain the carbon-hydrogen bond. The hydrogens are inferred, for those who don't remember their organic chemistry, and that's kind of circled there. And the point of this is that the polyfluorinated compounds, I'll spend a lot of time talking about this, can serve as potential sources of perfluoroalkyl acids when they get out into the environment or ingested and potentially transformed. And so the polyfluorinated compounds could be concerned in and of themselves, but they also have the potential to form these more problematic perfluoroalkyl acids, the compounds shown on the left, once released. So a little bit more on what these perfluoroalkyl acids are. These are fully fluorinated chemicals. They have no carbon-hydrogen bonds. They have carbon-fluorine bonds, repel both oil and water. What's important is that some of these compounds were used themselves, but more importantly, their precursors, these polyfluorinated compounds, these PFAA precursors, were used in a wide variety of products, textiles and paper packaging products, firefighting foams, which I'll come back to. And the perfluoroalkyl acids are very persistent in the environment, basically redefine the meaning of environmental persistence. Some of them are bioaccumulative to varying levels in either plants or animals. And there's some concerns, obviously, about their toxicity, which I will not touch on today. They've been widely detected in humans and wildlife all over the globe. And what's really interesting about their behavior is that they're relatively mobile and yet bioaccumulative. And those are two components which we don't normally think about. Usually we think about compounds that are bioaccumulative but not mobile, or mobile but not bioaccumulative. And these compounds combine kind of both problems. So again, what are these compounds? I'm a chemist, so I like structures. This is one of the poster child chemicals, PFOS or PFAS, has this perfluorinated tail, this anion head group, which leads to some unique behavior. These compounds tend to partition or absorb to the air-water interface. They are surfactants. And if you're using these compounds to put out fuel fires, which is what they're using in firefighting foams, it's actually really good news that the carbon-fluorine bond is one of the strongest bonds known. The bad news is the carbon-fluorine bond is one of the strongest bonds known, which means when they get out there into the environment, they really don't go away. Okay, so these are really, really persistent in the environment. When we step back from just focusing on the perfluoroalkyl acids, we have to recognize that there is a much broader suite of compounds out there. It's not just about PFOS and PFOA. This is a figure from a paper that Jamie DeWitt and I were involved in, and it talks about this family tree, which is incomplete, I'll just note, and highlights two compounds that are fairly well studied, PFOS and PFOA, but you notice also Gen X, which is obviously of interest here, is also on this list. And what's important is that these compounds rarely occur in isolation. Usually they occur as mixtures, and you really need to be thinking more holistically about these suite of compounds rather than focusing on one at a time. So where are they coming from? I mentioned they're used in a lot of consumer products, and when those consumer products are used, they can get released to wastewater, to landfills. If the wastewater produces biosolids, that sludge can then be a secondary source of these compounds. And that's a whole other discussion we can have. I've done a lot of work on focusing on these compounds and their use in firefighting foams. And when that foam is released, what happens to that? And the thing to keep in mind there, it's not just military sites that have used these firefighting foams. They're used in some light industry applications, such as chromium electroplating. The sulfonates had been used quite a bit, carboxylates a little bit less so, but also some of the polyfluorinated compounds have been used as replacement chemistries for some of these applications. And of course, there's also these industrial discharges. And I've highlighted a couple from the Northeast, but certainly what's going on here in North Carolina would also would fit into that paradigm. So there's a wide variety of potential sources for these compounds, and I'm going to come back to that as a potential complication in terms of figuring out potential exposure sources for these compounds. I'll spend a lot of time today talking about the use of these compounds in firefighting foam, or AFFF. And the reason for that is that these are places where when the foam is released, we're releasing very high concentrations in a very specific location directly to the environment. Okay? But it's important to keep in mind that it's estimated that only 3% of the fluorochemical production was used for these firefighting foams. A lot of that went to the military sites, but not all of it. There's plenty of commercial airports and oil refineries, and even your local fire department. When I walked down to the local fire department in Colorado, they had a can of AFFF available. All the trucks are typically loaded with AFFF to help put out fuel fires that arise on highways and the like. These foams are complex, very complex mixtures. They're proprietary, just figuring out what's in them. The brief history here really talks about the various formulations of these various foams that were essentially put on the military specification sheet, which allowed for bases and other entities to acquire these and use these foams. What's interesting is that when you see these foams being used, unless it's an accident location, typically these are multiple different types of these formulations have been used over the years, and again, often directly released to the environment, directly applied to soil or water, if it's a coastal accident, for example, and highways, if there's a fuel spill on a highway. Again, the PFASs are a very important ingredient in these foams, so they are a few percent in mixture, but it really translates to gram per liters in these foams. And what is interesting is that some of the foams contain the perfluoroalkyl acids. Historically, some of the 3M foams in particular contained PFOS as one of the active ingredients, but they also included these polyfluorinated compounds. And trying to figure out what those are, or what those were, has been quite a challenge. Jennifer Field at Oregon State has spent a lot of time trying to work on that. But what was kind of an interesting development a couple of years ago was David Sedlak and one of his graduate students, Erica Houts, developed an assay which is called the total oxidizable precursor assay. And the idea here is that even if you don't know the identity of some of these polyfluorinated compounds, what we do know is that the perfluorinated compounds are very resistant to oxidation, particularly things like hydroxyl radical. And so what they did is they took advantage of that and essentially took samples and oxidized the heck out of them, essentially, and converted all of those polyfluorinated compounds to things that we didn't know what they were, to things that we could measure, such as these perfluoroalkyl acids. It turns out that regardless of whether you start with different types of chemistry for the precursors, these polyfluorinated compounds, you tend to generally produce, most of the time, only the perfluorocarboxylates, which is one flavor of these perfluoroalkyl acids, but that doesn't mean that transformation, the same sort of transformation that might happen out in the environment. But this is an assay that was pretty ingenious in my view. And what Erica did, Erica Houts was a graduate student who did this work, was she applied this to some of these firefighting foams. And so on the left, we see the untreated, the directly analyzed firefighting foam. And so you can see some of the 3M formulations had a lot of PFOS in them. These other formulations had very low levels, you would say, except you look at the scale bar there, and we're talking grams per liter, okay? So these are relatively high concentrations, at least of PFAS in some of the 3M foams. When you take those same samples and you oxidize them with the top assay, all of a sudden we see gram per liter concentrations of some of these perfluorocarboxylates, and even in the 3M formulation, we see generation of PFHXA, the C6 version, which points to the fact that there are some precursors to those sorts of chemistries, even in the 3M foams. So this gives us a sense of kind of what these different compounds are in AFFF, and really points to the importance of these polyfluorinated alkyl compounds, these PFAA precursors, and led to additional work that actually Lee was involved in here, where we went and tried to identify what those compounds are. This is building off of after Jennifer Field thought she was done with this after doing a lot of discovery work over the years. But in the process of looking more closely, we observed 40 new classes of compounds. So not 40 new compounds, 40 new classes of compounds, either in the foams or in these AFFF impacted groundwater. And what this has led to, at least in my lab, and I'll talk a lot about this in the rest of the talk, is we developed a high-resolution mass spec library that includes about 1,500 compounds for accurate mass, but then we have full spectra for about 325 of those compounds. And a lot of them are polyfluorinated, but some of them are perfluorinated, okay? And we can use this library to go and query various systems that we're looking at to try and understand what compounds might be important. So when I think about PFAS, PFAS is the environment, I think of a lot of different varying levels of complexity in multi-dimensional space, if you will. I'll start simply with the chemical composition. And what I'm trying to illustrate here is that when we think about other environmental contaminants, things like TCE, nitroaromatics, brominated flame retardants, pharmaceuticals and personal care products, in terms of the chemical complexity, so if we think about this as a chemical complexity issue, PFASs are pretty high up on that list. And you might say the pharmaceuticals are higher simply because they're not really structurally defined. Everything else on this list has some sort of structural description in terms of its classification. So even just starting with chemical composition perspective, PFAS are a complex problem. However, if we added a second dimension to that and think about the environmental behavior, these start to separate out a little bit differently, okay? And you might say, at least in my view, that PFAS are pretty complex in terms of it's not just the fact that they have different head groups and chain links and all that sort of thing, but they have very different behavior in the environment than a lot of the traditional compounds. They're also very persistent in the environment. And that leads to a lot of challenges. And so when we think about treating impacted water, which I'll talk a little bit more in a moment, treatment of these compounds in water is very challenging, partially because of the stability of those perfluoroalkyl acids. They're really hard to degrade, but also the complex behavior of environmental behavior and the complexity of the mixtures themselves. Okay, and adding to that, the fact that in most cases the universe of PFAS potentially present is most often not really defined. Okay, and so that makes it makes it a pretty big challenge when you're trying to treat for a broad suite of these compounds potentially in a water supply. The other aspect, and I'll just say as kind of the third dimension here, which I'll talk about in a moment, is the fact that when we think about human exposure to these compounds, it's not just the drinking water. I've highlighted drinking water here, but we know that because these compounds can be released to soil, they can be released to water, there can be air emissions that aren't really captured here. People can be directly exposed through consumer products. They can be exposed through drinking water. They can be exposed through produce grown with a water that has been impacted by these compounds, or they might be consuming fish. And there have been states that have been issuing fish consumption advisories because of these compounds accumulating in fish and being that potential route of exposure. So coming back to our multidimensional complexity problem, when we think about this third dimension of human exposure, I would say that this really brings PFAS to kind of front and center in terms of the complexity of the problem. We're dealing with a complex mixture, complex behavior, and a complex exposure scenario. So what I want to take a few minutes to talk about is the potential role of these polyfluorinated compounds, particularly as it comes to initially talking about drinking water treatment. And the idea here is, when we're thinking about these polyfluorinated compounds, is there a huge amount of stuff there that we just don't know about because we don't see it because it's under the water, okay? And so I want to try and focus on that a little bit more today. I'll start with what we know about how these compounds behave, the whole class of compounds, I should say, but focusing on the perfluoroalkyl acids in terms of drinking water treatment. And I was involved in a study sponsored by the Water Research Foundation where we tried to summarize the state of knowledge as of 2016, focusing on full-scale treatment, but also a little bit of bench-scale treatment that we involved here. And Dr. Eric Dickinson at Southern Nevada Water Authority and Tim Appelman, who's with the Navy now, were involved in this effort. And the short story there is that we really only found 3 technologies operating the full scale that seemed to work fairly well for removing at least PFOS and PFOA. Those were granular activated carbon, anion exchange, and reverse osmosis. Okay, and these are not cheap technologies to employ, but they were the only ones that we observed at full scale to really show a lot of promise. There's been a lot of work since to try and advance other technologies, but at the time, this is what was really available. The other thing to note is that the systems have to be operated for removal of these compounds. RO is pretty good regardless, but certainly we found evidence that if the granular activated carbon or anion exchange resins were not operated to intentionally remove these compounds, you would get full breakthrough of these compounds in the system. The other thing I'll note is that you'll note this slide has removal and production. This really started to hint at the fact that in some cases we actually observed higher levels coming out of treatment plants depending on the type of treatment technology that was going on. And this hinted at the potential for precursors to be present that would be converted to these perfluoroalkyl acids, in this case PFAS and PFOA, in the drinking water treatment system. We'll come back to that more in a moment. So when we think about full-scale GAC treatment, which is one of the more commonly done technologies now, it's been fairly well established that these compounds break through a carbon filter in very logical progression in terms of order. And what's shown here is the fact that the short chain compounds, the butanoic acid, which is one of the shorter chain compounds, breaks through fairly rapidly as compared to the C6 or C8 version of these carboxylates in a full-scale GAC treatment system. This system was a lead and lag vessel design, which I think we'll probably hear some more about treatment technologies later. But essentially, when the arrows point out when the lag vessel, when the lead vessel was changed, and so you see a reduction in the levels coming out because they put a new carbon filter in. But the PFBA was only essentially removed when they changed both the lead and lag vessel. And then you can also see the very rapid rise again because it breaks through the carbon more quickly. So we knew that this behavior existed for these compounds in terms of carbon filters, but we really didn't have a lot of information in terms of precursors in their removal in these GAC systems. And so one of the questions after this was done and we started realizing how many precursors there might be out there, these polyfluorinated compounds, I had a student from China who really wanted to say, well, can we answer that using things like high-resolution mass spectrometry? And we've heard a little bit about that today already. In our case, we weren't doing truly non-target work, but we're really doing suspect analysis, where we were using that library that we had developed to look for these compounds in a water supply. So Jin Zhao, who spent about a year in my lab, wanted to look at these compounds and basically answering the question, if most utilities are installing a GAC, will this be enough? Will this be enough for removing these polyfluorinated compounds in a potential PFAS-impacted water supply? The approach was that we wanted to go out and sample a water supply and look to see if we saw these other compounds present. And the rationale is that what we might see in a drinking water supply may not be the same thing that you would see at a fire training area because you're fairly far removed from the source at that point. The second question is examine how well these carbon-based treatments could potentially work for these compounds. And again, the rationale there is that the short-chain compounds exhibit early breakthrough, but we really didn't have much information at all on these polyfluorinated compounds and their behavior in these carbon-type filters. Unfortunately, at the time that we started this study, there weren't a whole lot of full-scale GAC systems that we knew were impacted by the firefighting foams, much less those that would actually supply us with samples. So we had to provide us with enough water to do kind of full-scale testing. And so we had to do everything on the bench scale. We had a couple of liters of water provided from one water system, and we needed to evaluate that. So the approach we took is we used our high-resolution mass spectrometry library to look at the water supply to see if the other compounds were there. But for the removal, we didn't even have enough water to do what I refer to as rapid small-scale column tests. So we really had to use batch experiments and to do some modeling to predict what might happen at the full scale. So our results for full scale are really modeled results, but we're still relatively confident in terms of what they would mean. So just looking quickly at what we found, it wasn't totally surprising, but we did see around 30 different compounds in this particular water supply that we looked at. A number of carboxylates and sulfonates, those were expected. Fluorotelomere sulfonates, which are very common at these H12 impacted sites, but also perfluoroalkyl sulfonamides. What was a little bit surprising is about half the compounds we observed we had only recently discovered. So it was really within less than a year of when we had discovered them and started reporting them, we actually started observing them in this particular water supply. And I'll talk a little bit about some of these compounds, but the short story there is that other PFASs are likely present in other HFF impacted water supplies. I'll note the concentrations of PFOS and PFOA in this particular water supply were really high. So if it's fairly dilute, you may not see these other compounds, but they have the potential to be present depending on what the levels are. Just to give you a sense of some of the structures, a lot of these polyfluorinated compounds with varying head groups, so they contain these non-fluorinated, polyfluorinated components, and they have this perfluoroalkyl tail. And also what I'll refer to over here is these PFAS derivatives. So this particular version, it was a 7KK for ketone type PFAS derivative. We see unsaturated versions. We sometimes see chlorinated versions of these compounds. But these were observed in a water supply. Back to the question, will GAC work? So again, we had to rely on some batch experiments. We basically took some various activated carbons and some biochars that Zen was interested in and did some batch equilibrium, but also looked at the kinetics For those who know about carbon filters, it's not just about equilibrium. You also have to account for the kinetics of the system in terms of how quickly these compounds diffuse into the carbon particles. And so we did both some measurements of the equilibrium conditions, but also estimated and measured, essentially fit the kinetics of the interparticle diffusion of these compounds into the carbon particles. And the point there is we're trying to capture the types of behaviors that would actually happen in a carbon system. When we look at the equilibrium data and plotted here log KD, which is basically just how well these compounds stick onto the carbon, it was really interesting in that the perfluorinated compounds we observed showed a very clear linear progression with increasing molecular weight, increasing chain length, that they're more strongly removed onto carbon. This is entirely consistent with what others had observed in other systems and consistent with what we knew about GAC breakthrough. What was a little bit interesting is that the polyfluorinated compounds also showed a relationship with increasing molecular weight in terms of their affinity for the carbon, but it was not as strong a relationship because the polyfluorinated component likely contained other sorts of functionalities which led to a decreased affinity for the carbon. What this translated to is when you take that sort of data, you combine it with the kinetics and make predictions about what might happen. So what's shown here is the molecular weight versus breakthrough in a carbon system. There's a modeled breakthrough. A lot of these compounds would break through, we would predict, would break through carbon before PFOA would, and all of the compounds we observed would break through before PFOS did. And just to give you a sense that we weren't completely out on a limb modeling the actual breakthrough for a system that we were basically trying to model using a different type of carbon, a different groundwater, we were really close to and this was not fitted, this was a forward model prediction of how that would perform. So what this is really telling us is that GAC can work, but if you're treating for PFAS or PFOA, you're not being protective for all these other compounds that will likely break through the carbon before PFAS and PFOA would. So you might have people being exposed to these polyfluorinated compounds. And so the question you might ask is, should we care? And to help address this question, I partnered with Jamie DeWitt here and some other folks here. I should have Lee's picture up there because that's his student, Sarah Trokey. And Carrie McDonough is a postdoc in my lab who's been kind of continuing this work. And this is some work that we had started while I was here on sabbatical, but has continued since then. And the idea is we didn't have sources of groundwater enough to do exposures, but we did have sources of these firefighting foams. And so Jamie was interested in some of the toxicity of these foam mixtures, and I'll let her maybe talk about that later, or at least she can answer questions about that. But she did a series of dosed mice experiments and did all sorts of observations in terms of the potential endpoints for toxicity. What we were interested in, aside from the toxicity, is what sorts of compounds might be accumulating in the serum of the mice. And so we looked at the levels of the normal compounds we typically look for, targeted analysis, but also wanted to do suspect analysis to look for these other compounds that we knew might be present in the firefighting foam and might be bioaccumulating in the mice. Very briefly, it's not surprisingly that we saw a lot of these perfluoroalkyl acids in the mice. They were being dosed with decent concentrations, I should say, of these firefighting foam mixtures. We saw this was a 3M, primarily 3M foam. There was a little mix of other foams in there. So we saw a lot of PFOS, a little bit of perfluorohexane sulfonate, which is something fairly commonly observed when you have an AFFF release, as you see a lot of this perfluorohexane sulfonate, but there are other compounds there. But again, what we're really interested in is the other things beyond the things that we typically look for. So this is a bubble plot, as I referred to, and Mark, I don't know if you're going to show a bubble plot later, but the idea here is that the mass to charge of the compound versus the retention time in the analytical column gives you a sense of kind of the behavior of these compounds and their size and all that sort of thing. And what Carrie did here in this representation of the data is she removed the perfluorosulfonates, which are typically dominant in these exposures, and looked for these other sorts of compounds. And the size of the bubble really hints at the size of the peak. Keep in mind that we can't be quantitative as of yet. I'll talk more about that later. But we can see that these other peaks are there. And what you see is we see a little bit of fluorotelomere sulfonates. We see the cyclic unsaturated compounds, these double bonded structures, some of the ketone structures, some chlorinated versions of these compounds, and there's a whole gamesh of compounds that are observed in the serum of these mice. But at the end of the day, what we really care about is what is bioaccumulating. And so we thought about this and tried to think about what is the relative bioaccumulation potential, at least compared to something like PFOS. So what we did is we normalized the data by spiking RHBF in the serum. It accounts for matrix effects for those analytical chemists in the room. And then we addressed everything by normalizing to the PFOS bioaccumulation. So essentially what we're observing in serum versus what we're observing in HBF, again normalized to PFOS. And the point here being is that anything below that dotted line is something that would be relatively quickly eliminated or less bioaccumulative than PFOS. But anything above that line is something that either has a greater intrinsic potential for bioaccumulation or can be formed from precursors. And if you look at what those are, what we observe are things like the various substituted PFOS molecules, the chlorine, the unsaturated PFAS, the ketone PFAS, but also things like the perfluorohexane sulfonate and the perfluoropentane or perfluoroheptane sulfonate. So the C6 and C7 sulfonates showed, at least suggested, that they're either greater bioaccumulation potential or being formed from precursors upon exposure of these mice. So, the whole point of this is really to try and think about what sorts of chemicals we might want to prioritize for additional toxicity testing or additional analysis to truly understand their importance. It doesn't matter, even if the concentrations are lower, that they're bioaccumulating more, at least in these mice systems. So taking a little bit of a step back and thinking about this complexity of PFASs and how to address this in a more broad perspective, you might ask the question, or question that we keep asking ourselves, are how are the different compounds behaving in different systems under various different conditions? And I've talked a little bit about high-resolution mass spectrometry, but it's not just about high-resolution mass spectrometry. And I really think we do need some more robust analytical tools and approaches needed to really address this complexity. And so I'll just take a moment to step back historically and point to a study that was published before I was born, okay? And this was a study where they looked at the organic fluorine content of human blood, the Guy, Tavies, and Bray paper in 1976. And what they observed was they saw this, this peak in the organic fluorine, which they observed via a combustion IC, and they combined their, basically their combustion IC measurement of the total fluorine, the organic fluorine in the blood, with NMR, which is not the most sensitive technique. But what was really interesting is they identified, the NMR spectra shown here, PFOA. It turns out, if you actually have read any of the documents that were released through the Minnesota lawsuit, and in some of the internal documents that 3M had, 3M later confirmed it wasn't PFOA, it was PFOS. But it was observed in 1976 these compounds were in human blood, okay? And keep in mind, they did not have LC-MS, or high-resolution mass spectrometry at the time, but they combined the tools they had. They had the ability to measure organic fluorine and NMR, and they combined the two to draw a correct conclusion that these compounds were present in human blood. So use the tools you have, is what I'm trying to get at. So what tools are available? What tools can we use? So I already talked a little bit about the TOP assay. It's actually a fairly quantitative assay. But unless you're looking for things beyond the standard suite of compounds, you may still miss some compounds. You wouldn't, for example, see Gen X with the TOP assay. And if you're doing anything samples other than water, the technique is only as good as your sample prep. We heard a little bit about that question before, about how you're concentrating your samples. I won't talk through all the rest of these techniques. We might hear a little bit more about them later. Extractable or absorbable organic fluorine, which is similar to what the Guy and Tavies paper had done. 19F NOR, which they had done. Quantitative and compound specific, but not particularly sensitive. Particle-induced gamma ray emission is quantitative, but not compound specific. I won't have much time to talk about that unless you have questions. And then again, this high-resolution mass spectrometry focusing on LC-amenable compounds. And it's quantitative and can be semi-quantitative, but you do need to have people who are knowledgeable. In the case of, I guess in Switzerland, 5 people to run the system and analyze all the data. And so my kind of challenge or thought to folks here, and I know there are lots of folks doing high-resolution mass spectrometry, is think about the right combination of tools to get together to address your specific question and be creative in combining these various techniques. We're trying that. We're trying to walk the talk in our lab. And what I put up here is a paper that Carrie McDonough recently published, which tried to highlight how these various techniques come together. Your targeted LCMS is really giving you a very narrow focus. The top assay gives you a little bit broader perspective. If you do high-resolution mass spectrometry, you see a slightly different, potentially, picture. I should note this is hypothetical. We haven't actually known. We don't know what falls under exactly what beyond the targeted list. We don't know what falls under what part of the Venn diagram, if you will. And then you can go all the way back out to looking at total fluorine measurements. But the issue is that the further you get away from that kind of center of the image here, the less specific you are, and typically the less sensitive you are. And so you really need to think about a combination of tools to try and address the questions you have. So in an example of that, one of my other postdocs, Andrew Meisel, is looking at the release of these compounds from soil. As the soil as rain falls in the soil, and we want to understand the release of these compounds to groundwater, we're trying to figure out what's important. How many of these compounds are coming off? And so we're doing a series of column experiments, and he's taking the data and looking at it from the high-resolution mass spectrometry library and looking for these compounds. And what he observes is, just looking at 2 different soils, we observed 167 different PFASs that were in our library. We actually think we're still missing some, so we have some plans for some non-target work to try and figure that out. But we see a lot of different compounds coming off. And what's important is that there are a lot of these polyfluorinated precursors, particularly if you look closely, precursors to the C6 sulfonate. Okay, so these are compounds in the firefighting foam impacted soils that are potentially leaching to the subsurface and eventually leading to hexane sulfonate in the groundwater, or these precursors themselves can be in the groundwater if people might consume it. So these are examples of some of the elution profiles he's observed and how we're applying it. And we're trying some semi-quantitative approaches to try and get at the mass, but we can look at broad suites of compounds with this approach. And it's really turning out to be a pretty powerful tool to look at the behavior of this complex mixture. But what's really important is that when we think about the mass balance and combining the tool, we're concerned that we're not seeing everything. We're only looking at what's in our library, and we're going there, but we haven't at the point looked for the unknowns. And so when we think about comparing this data to something like the total oxidizable precursor assay or a total organic fluorine analysis, and just as a reminder, the top assay converts these polyfluorine compounds to measurable carboxylates. What we observe is that when we normalize things to the mass of PFAS in the soil, this is log scale. We do see an increase upon analysis of the soil with the top assay, which means there are other compounds that aren't normally captured with our targeted technique, and it differs between the different soils. In one case, it's a whole lot of compounds being generated with the top assay. And then if we, in fact, it's 42% increase in one case and 6,000% increase in the other, okay? And that's not necessarily uncommon at these firefighting foam impacted sites. And then when you compare it with something like the total organic fluorine measurements, where we're essentially measuring the fluoride content that's associated with carbon atoms in a sample, we see something similar. We see an increase relative to the base case of our targeted measurement with the total organic fluorine, and a slightly also higher increase in the second soil, where it's pointing to the fact that there's a lot of these other compounds present that we're not capturing with our targeted analysis. So what Andrew has been doing is trying to develop a semi-quantitative approach. So this slide highlights the targeted analysis of the various classes of compounds that we observe either in the soil or in the effluent. But then what he's been doing is developing a technique to semi-quantify a lot of these compounds. And what he's observed is that before we do the semi-quantification, some of these sulfonamide precursors to the things like the C6 sulfonate only account for about 0.5% of the total PFAS we observe in the system. But when we do our semi-quantitative analysis with our suspect list, that jumps to 50%, at least in this one soil. And that really points to the fact that we think that doing a semi-quantitative approach will help close this mass balance of understanding these compounds and highlighting the importance of these polyfluorinated compounds in the environment. So what this really points to is that looking at a broader suite of compounds using even semi-quantitative approaches will really help identify these missing PFASs, and particularly in this case, the ones that we think were identified via the top assay. So just to wrap up a little bit, I think it's pretty clear it's not just about PFOS or PFOA or even Gen X. Okay, there's a broad suite of compounds out there, and most are currently not currently examined. I think that in some cases, although not all, the concentrations are likely lower, but we are limited in terms of the availability of analytical standards. That's getting better. And I didn't speak to really any of the toxicity, but there's a significant lack of toxicity for a lot of these other compounds. And I think high-resolution mass spectrometry as a technique can really help. I'm very excited to hear about the efforts here in North Carolina to use this technology and approach. It can help you develop treatment goals for lesser studied compounds, prioritizing compounds for toxicity studies, and do what we call kind of full characterization of these impacted sites. And we focus on HLF impacted sites, but it can also help with other sites that are impacted. But I would point out that I still think it's best used in conjunction with other analytical tools, because until we fully evaluate everything, not everything is amenable to LC, as an example. We really need to get a handle on have a second line of evidence to point to these other compounds that might be there. So going back to our iceberg here, you know, what's there, what's under the water, what's above the water, it's really going to depend on your site and your site conditions. I started with the question of, you know, when we start seeing these compounds in the water, how should we communicate the unknowns? There are compounds we observe we have no toxicity information for. How do you communicate that? And that's a challenge. But I think the conversation over the last couple of years has really shifted from how should we communicate the unknowns, how should we treat for the unknowns? And this is more of a philosophical statement to some extent, but I think this is the question a lot of people are asking. And I know there are folks that would say, it's not how, it's should we treat for the unknowns. But I would challenge those folks to think about the fact that when you see communities that have observed relatively high levels of these compounds in human blood, and these are kids who happen to be the same ages at the time as my own kids, this really strikes home. And really, it ends up not being so much a how, or should, but a how. How do you treat for those unknowns? And so with that, I will leave you with a slide showing beautiful Golden, Colorado for those who haven't visited. And for those who are concerned about the winter, I'll just say this is an image of Golden in winter. It's really beautiful. And I'd be happy to have folks come visit and happy to entertain any questions you might have.
Thank you, Chris. Yeah, we have time for some discussion.
Hi, Chris. I really enjoyed your talk. I may have sort of a naive question. I'm an atmospheric organic chemist by training, and I'm very interested in your tools with looking at total organic fluorine. One of the challenges we struggle with is also developing tools to characterize all the hundreds of thousands of compounds, organic compounds, in air pollution samples. So our community is struggling with the idea, do we really want to try to characterize everything and then get standards, or should we focus on developing bulk sort of chemical tools to then try to associate with health outcomes? So I'm just curious if the total organic fluorine measurement is promising to sort of have something to say we know the total organic fluorine content, and can that be sort of used now to associate with maybe important outcomes related to health?
It's a great question. You know, I didn't delve into some of the complications of those various tools. One of the things with total organic fluorine as a singular tool is it does potentially capture other compounds that are not PFASs. So any pharmaceuticals that have a CF3 group that are retained in a total organic fluorine analysis are going to give you a signal. As to how important that is in the individual settings, I'm not entirely sure. But that's really kind of why I'm trying to say there's not one tool. It's really a combination of tools, and I think that's, if you put them together in the right way, you can try and address those questions. But I'd be really hesitant to put all my eggs in any one basket. because of our current state of knowledge.
Hey, thank you. So one of the lead national reporters on the PFAS issues reported that the military has begun to spend millions of dollars, I'm talking about AFFF, to replace with a C6 version. And I was just wondering, you were talking about targeting and putting your attention towards these kinds of unknowns. Is there work, to your knowledge, to look at this C6 that the military is now flooding the market with?
So the short answer is yes, in that, so I've had a lot of my work funded through the CERTIP program, which is a joint DoD, DOE, EPA research program. And they are fully behind the idea of looking at a broad suite of compounds. So not so much, well, I can't speak to the efforts in terms of toxicity because I'm not necessarily involved in those, but they helped me acquire a second QTOF in my lab to be able to look at these broad suite of compounds. So I think there's acknowledgement that you can't just look at the historical materials, but you have to look more broadly. I do think there's a lot of challenges with figuring out, what do we use instead if we don't use these fluorine foams. That's a whole nother conversation we can have, but I would say, at least from my experience, I think the various agencies, at least the funding agencies, are fully aware of these other compounds and are wanting us to include that sort of analyses in our studies.
Hi, Chris. That was a great talk. I have two questions, actually. One is, I noticed that you talked a lot about using the LC, high-res mass spec, to look at using non-target analysis, and I'm wondering if you have any thoughts on what PFAS chemical space you might be missing by not including a GC analysis. And then my second question, on your bioaccumulation data from the mouse study, it almost seemed like you saw sex differences where it was higher in the female mice compared to the male mice. And that seems to be the opposite trend that you see in the general human population. And I'm wondering if you have any thoughts on that.
I'll answer the second question first, in that we haven't really had a chance to delve too much into that data yet. Looking at Jamie because I'm hoping to catch up with her a little bit more on this trip. And I think there have been observations of different sex differences. We'll just have to try and evaluate what that is and what that means in terms of accumulation. With respect to the first question, that points at my comment about, all these compounds aren't necessarily amenable by LC. And one of the things when we were putting together that kind of target picture was, okay, the top assay, for example, might actually capture compounds, should capture compounds that are otherwise not detectable by LC because it's converting them, these basically neutral compounds, which were more GC compounds, to compounds that we can measure by LC. That's why those overlaps are not quite perfect, because there are some compounds that we're going to not observe. I personally think that in terms of exposure scenarios, the neutral compounds end up being more something consumer product derived and kind of maybe indoor air type scenarios, as opposed to things in the water or even things in the fish, because I think once it gets into the environment, those compounds tend to get converted to things that are amenable to LC. That's not been fully validated, but that's my general thought.
Beautiful talk, Chris. Thank you very much. You could have testified for me 2 days ago. That would have been nice.
I'm glad it was you, though.
Just a comment about the AFFF and the military, which I do think they deserve some credit for the fact that they are no longer using AFFF for training, which should reduce the amount that they're using putting into the environment. However, because of their military specifications, they are requiring fluorine. At the moment, though, the military are testing some non-fluorinated derivatives to see if that might work, because I think it's important to realize that, for example, in Sweden and at London Heathrow Airport and some other places in Europe, they are using non-fluorinated AFFF.
That's an excellent point, Linda. I think, the other thing to keep in mind is that, from my understanding, the DoD, I certainly know the Air Force, and it's my understanding the Navy as well, has severely restricted when the actual foam is used, and essentially when the foam is used, they basically treat it as a hazardous site. They dig up the soil, et cetera. I've heard recently that not all federal agencies are doing that, For example, FAA is not necessarily doing that. So you're clear. Good. You know.
In the FAA reauthorization, that's just because they are no longer required
Okay.
to use, to meet the mil spec, no longer requiring fluorine. Just that.
Good clarification. But you know, I think that's the point of that comment was to point out that it's not just the military, and there are potentially other locations where these foams were used where they're not necessarily treating it in the same way. So.
Okay, take one more question.
Thanks. I have sort of two questions I'm going to sneak in here. So the first one is, you mentioned that only 3% of production of PFAS is for the military foam, or for AFFF, and yet there's been a lot of attention to AFFF, especially in a regulatory context. And I was wondering if you could speak to, so that's the production, but what about the exposure? Like, what would you say the percentage of people's exposure, both through water and products, is, and versus other routes of exposure that we might want to think about in a regulatory context? And then secondly, the definition of PFAS has been somewhat controversial in a regulatory context, and I was wondering if you could speak to how you would define it. I know Washington State, a lot of people point to as kind of the best practice in identifying it as compounds that have one fully fluorinated atom, and I was wondering if you agreed with that, and if you had other thoughts.
So I'll try and address the second question first again. I think the issue of including just like one CF3 group, that can be potentially problematic because the number of pharmaceuticals do contain CF3 groups. From my perspective, anything that has two carbons, fully fluorinated, that's kind of the way we approach it. But again, we've mainly focused on these chemicals associated with the firefighting foams. Back to your first question about exposure, that's a big question. And from my perspective, and I think there's some general consensus, there is a kind of a background exposure due to consumer product use. And you know, I pointed out the complexity of that. There's consumer product exposure, there's food exposure, both animal and plant diet components, and then there's drinking water. And the best studies that I have observed that really try and tease that out are Robin Vestergren out of Sweden, who's tried to model a lot of this. And basically, from my understanding, is that when you have contaminated water, the drinking water is the dominant component. But when you don't, there's a combination of both food exposure and kind of consumer product exposure. And figuring out which is more important in those scenarios for the background population is a little bit tricky. But when you have contaminated water, it's pretty clear most times that that's the dominant route of exposure. No, not firefighting foams, just contaminated water, period. There's a whole other discussion about whether it's mainly the foams or the other chemicals. But
Okay, thank you, Chris. Let's thank our speakers. Okay, so we'll take a 15-minute break and come back 5 after the hour. Okay, so welcome back to the second half of our morning presentation schedule. So we've heard so far from the international and then the national perspective on emerging contaminants and PFAS in water. And so it's really a pleasure for me to introduce our next speaker, and that's Dr. Gloria Post from the New Jersey Department of Environmental Protection. Gloria has been involved in the issue of PFAS in water in New Jersey for over 10 years now, and has really come here to give us a perspective on what the experience in New Jersey has been with this issue and some of the science around risk as well as occurrence of these compounds. And so with that, it's my pleasure to introduce Gloria.
Thank you, Lee, It's an honor for me to be here and really with some of the top researchers on emerging contaminants and PFAS from anywhere in the world. I'm really honored to be here. I'm a toxicologist, I'm not a chemist, so I'm going to be speaking about occurrence and health effects and risk, but our occurrence data is not from research methods, it's from generally available methods. I'd like to say the work I'm going to present today is an overview of the work of many people, many scientists from the New Jersey DEP as well as the New Jersey Drinking Water Quality Institute, and I'm going to be covering a lot of material, like 14 years of work in half an hour, so I may have to skip over some of the details on some of the slides, but I understand it's being recorded and also they'll be posted, so if you didn't, you can go back to them later, they'll be available. So let me begin. Chris gave a very good overview of PFAS and perfluoroalkyl acids general background information, so I can probably go through this very quickly, but in general, we all know there are thousands of PFAS with many different structures, and this is the focus of current interest. Most of them have little or no health effects or occurrence information, and most are not, or almost all, I would say, except maybe Gen X and maybe others, a few, but most of them are not detected by the commercially available laboratory methods. They're detected with research methods. And Chris explained in a lot very well and clearly that perfluoroalkyl acids are a subset of PFAS. And those are the ones that were studied initially, like such as PFOA and PFAS, the carboxylates and the sulfonates with a fully fluorinated carbon chain and a charged group's carboxylate or sulfonate with different chain lengths. And those are the ones that we've been working on in New Jersey. Those chemicals have considerable occurrence and health effects information. They're also detected by the commercial laboratory methods that we've been using so far. As Chris explained, there were 6 of them included in the UCMR EPA National Monitoring Program. And although the use has been phased out, they do not break down, so the environmental contamination persists. The 3 we've done the most work on in New Jersey are the 3 in the box at the top of the slide: PFOA, PFAS, which have 8 carbons, and PFNA, which is the 9-carbon carboxylate. So New Jersey DEP initially became aware of PFOA in its waters in 2004 when PFOA was reported in groundwater at a large fluorotelmer manufacturing site in southwest New Jersey. It's shown on the map in the bottom right, the location. In 2006, a nearby public water system, the tap water was tested by a local environmental group. They sent a sample to Axis Lab, I believe, and it was found in the nanograms, in the up to 100 nanograms per liter range. Right after that, soon thereafter, the company that operates that facility tested the public water system wells of Wellfield, the wells of the nearby, that public water supply, and found it in the like 200 up to 280 nanogram per liter range. Later, nearby private wells were tested and found up to 600 nanograms per liter. So at this time, the initial New Jersey DEP actions were to undertake an occurrence study of PFOA and PFAS. Those were the 2 that were measured in the commercially readily available methods at that time. And we were asked by the affected public water system to provide guidance for drinking water, and we developed a guidance value of 40 nanograms per liter in 2007. So just to put this into the bigger context of New Jersey's work on emerging drinking water contaminants, New Jersey has done a lot of work and developed a lot of expertise in both risk assessment and occurrence and other studies of emerging drinking water contaminants since the 1980s. In the 1980s, in the early 1980s, my group, the Division of Science and Research, before I was there, did studies that found volatile organic contaminants in New Jersey groundwater. As you know, New Jersey's a heavily populated and industrialized state. These were considered the emerging contaminants of that time, the VOCs, and at that time there were no federal MCLs. They were developed later in the 1980s. They didn't have drinking water standards for these. So in the 1984, the legislature passed amendments, the New Jersey legislature, to the New Jersey Safe Drinking Water Act that required development of maximum contaminant levels drinking water standards for 23 listed contaminants and future additional ones based on occurrence and health effects. That legislation also established the Drinking Water Quality Institute, which is an advisory body charged with recommending MCLs to the Commissioner of New Jersey DEP. You can see on the slide different groups within our government appoint the members, and they represent the academia, the water purveyors, the water companies, and also the environmental health community, which could be anyone who has appropriate educational background, whether from industry, an NGO, or a retired person from the public who's a qualified scientist. Those are the majority of the members, and there's also 3 New Jersey DEP members and 2 from the New Jersey Department of Health. I am one of the 3 representatives from New Jersey DEP. The law also put a tax on water to fund drinking water research, including occurrence studies. So since that time, many emerging contaminants have been evaluated by New Jersey DEP and the Drinking Water Quality Institute. You can see them on the slide on the left of all different varieties, everything. They're all different kinds. There's something different about each one. And then our most recent ones have been for 1,2,3-trichloropropane, PFNA, PFOA, and PFAS. PFNA, what was I saying? The MCL for PFNA is adopted. It was adopted earlier this month, and PFOA and PFAS remain recommendations that have from the Drinking Water Quality Institute. They have not yet been proposed as regulatory standards. So when there are several of us, a bunch of us who've been working on drinking water contaminants, different areas with epidemiology, occurrence, toxicology for a long time. When these came across our desk, we viewed them like in the context of all these other contaminants that we had worked on over the years, and they struck us as having, these are different in several ways, and they caught our attention as being different from the other drinking water contaminants that we had previously worked on. This is kind of the summary of my talk in case I don't get to the end. So these are our conclusions based on what we knew then and what we know now about why these are of long-chain PFAS, these particular subset of PFASs, why are they of concern as drinking water contaminants? Some of this we've heard from Chris already. They occur in drinking water all over the place. They never break down in the environment. They're found in human blood serum at low levels. They have human half-lives of several years, so they remain in the body for many years after exposure ends. They cause multiple types of toxicity in animals, including some at low doses, and they're toxic generally at lower levels than the shorter chain, at lower doses than the shorter chain PFAS. They're associated with human health effects at low exposure levels, including general population exposure levels and in communities that have drinking water exposure. As Chris went into in his answer to the last question, relatively low levels can dominate the exposures that all of us have from food and consumer products and things like that, and I'll go into that more later. And this is very different than other PBT chemicals that we all know about, like PCBs and dioxins. For those other groups of chemicals, drinking water is not a major exposure source. They're more lipid soluble in the food and things like that. There's higher exposure when drinking water is contaminated, both breastfed and formula-fed infants will have higher exposures, and they're a sensitive subgroup for the developmental effects. So overall, this suggested a need for caution about exposure from drinking water. Okay, so in 2006, New Jersey did the first occurrence study. It was the first state to conduct such studies. 23 public water systems, surface and groundwater, and some of the samples were from raw water and some were from finished water. PFOA, our reporting level was 4 nanograms per liter using a commercial lab available at the time. PFOA was found in 65% and PFAS 30%. We've heard about this in a lot of detail, but this is like our old data before there was so much focus on it. In the studies, this is about treatment removal. In the studies where we had from the same water system, raw and finished treated water, the top panel's just PFOA and the bottom one is wells from a water, 10 perfluorinated chemicals emit. When we did our different analytical method that analyzed more of them in another place, these systems didn't have treatment designed to remove PFASs, and you can see it's not removed, it's the same or higher generally, or very close in the raw and treated water. So in our studies, for our current studies, we know that source water is generally a good indicator of finished water unless there's treatment specifically designed to remove PFAS. This just shows a New Jersey water system that did design granular activated carbon to remove PFAS, and it was removed to non-detect. This is a second study we did in 2009 through 10, and by this time the generally available method that from the commercial laboratory measured 10 of the PFAS, 7 carboxylates and 3 sulfonates with a reporting level of 5 nanograms per liter. Multiple PFAS between 1 and 8 compounds were found in 60% of the water systems, and the PFOA and PFAS occurrence frequency was similar to what we found in the earlier study. One important thing we found was PFNA with C9 up to 96 nanograms per liter in a southwestern New Jersey facility, or public water system, Gloucester County. In searching the literature, we learned that this was the highest recorded in drinking water and reported in the literature anywhere in the world, and I'll get back to that. Also, I just want to emphasize in New Jersey, we do not have any extremely high levels of perfluorinated chemicals, PFAS in drinking water. We have very widespread occurrence, but we don't have any of the micrograms per liter part per billion levels that have been found in some other states, including Pennsylvania and Colorado. I think that are they can be a lot of times from the firefighting foam, but we have not found any like that in New Jersey. So also, Chris mentioned the UCMR, the national study EPA did of all large public water systems, and it also includes a few small ones. The reporting levels are much higher than the studies we did generally for the chemicals we're looking at, the 3 we're focusing on, between 20 and 40 nanograms per liter. But we can compare our New Jersey data to national data on the same basis, looking at the UCMR results. So you can see in the top 2 rows, New Jersey has had a much higher frequency of occurrence of PFOA and PFNA than nationally, 10.2 versus 1.9 for PFOA and 2.3 versus 0.2 for PFNA. The PFOA was all over the state, not in one specific area, and the PFNA's in the one area of New Jersey where we had found it in our earlier study, and I'll go into that a little more, just in one part of New Jersey specifically. This is all of our data right now in our database from public water systems as of now. We have data from 216 of 580 public water systems. A lot of it's UCMR data with the higher reporting levels from our studies, UCMR, and also other data that's been submitted to our department. This database includes both raw water, like the sources of water, the wells or the surface water intakes, and finished water sampling locations within the treatment plants for finished water. So it's been detected. Our MCLs, or our recommended or final MCLs, are 14, 13, and 13. As you can see, it's been detected in 48 of these systems, one or more above these levels. PFOA, the most frequent, followed by PFAS, followed by PFNA. In the highest levels were between 150 and 330 nanograms per liter. I would like to emphasize strongly that this is a current state and not what people are exposed to. Most of these public water supplies, including those with the highest levels, have taken action to either treat, blend, take off the affected well, and people are not being exposed at all. Most of these sites, this is occurrence data, not. This is the same map showing some, indicating where we know some likely sources of the PFAS in these systems. The whole area in northeastern New Jersey that doesn't have a circle around it, we do not know the sources for most of these sites. The other ones we do know the likely sources, so I'll move on because I'm going to show each of them separately on the next slides. This one, in where the red arrow is in the near the coast in southern New Jersey, it's near a military site where firefighting training was done and firefighting foam was discharged. And we know there's like hundreds or thousands, I don't know how many PFAS is in the firefighting foam, but in the 10 these are the 10 we test in our studies. So a mixture like this, where you see a mix of the carboxylates and the sulfonates in the same sample, that's characteristic, I would say, of firefighting foam being the source, and it is here. This one is also near the coast further north. This is where we found 100 nanograms per liter of PFOA in a river that was used as the intake for a public water system. So our division and New Jersey, along with New Jersey Geological Survey and the water system, they do research at that water system, undertook a source track down study in this watershed of the river. So basically, by going upstream and sampling in the different branches, they honed in that it was starting in where the yellow box is upstream. There was not PFOA in the river. And then with further honing in, and they located it to a small industrial park within that area. And the facility that has the red box and the red arrow used PFOA to make various products. It's a small place that was using it to coat fabrics and different things like that. So the groundwater levels, those numbers in blue are nanograms per liter. It was very high in the groundwater going away from that place, and it was going into the river, so that was the source. Finally, this is about how we figured out about the perfluorone PFNA, the C9 in southwestern New Jersey. Actually, it's not very far from the place that the big industrial facility that had PFOA initially in 2004. It's about 20 miles away. As I said, PFNA is rarely detected nationally and not elsewhere in New Jersey. In the whole UCMR, out of over 4,700 public water systems outside New Jersey, it was only found in 10 above the reporting level of 20. But right near in the same area, we found 2 wells of 2 different public water systems that both were above the highest reported elsewhere anywhere in the world. Also, another agency, the Delaware River Basin Commission, studies emerging contaminants in the Delaware River watershed, that river that this is on, which is between New Jersey and Pennsylvania. They had done studies in 2007 to 9 of PFAS and other emerging contaminants, and starting right at that same river mile, right near that place, the red bars are PFNA. It just started being very high right there. Also, they studied fish, which is on the right, with the same river mile area. The both this C9 PFNA and also C11 was which is orange, started being very high in the fish right there. So it indicated there was something going on there. So we found out kind of in an odd way by searching the literature and Googling and whatever. Wikipedia referred us to a citation. That's really how it was found out. But in this paper by Pravadoris in Environmental Science and Technology, it has a very detailed supplementary information section that has a very detailed write-up of how PFNA was used industrially to make fluoropolymers in the same way that PFOA was used to make another fluoropolymer. This one is PFOA was used to make polytetrafluoroethylene, and PFNA was used exactly the same way to make polyvinylidene fluoride. And there was a lot of detail. So this was used in a technical mixture called Surflon S111. You can see that it contained mainly PFNA, 74%, and 20% C11 and other PFAAs at lower concentrations. The paper also listed the biggest users and emitters, I guess, of this in the world. And the second one is Thoroughfare, New Jersey. That is right near that where these water systems, and we were seeing it in the water. So that was how the source was revealed to New Jersey DEP, and we kept, and how our work on PFNA got started. The second half, how much time? 5? The second half of my talk's about human health risk assessment of PFOA, PFAS, and PFNA. I'm going to speed it up. Basically, when we started working on this shows the number of papers on PFOA in PubMed at different years. There was very little information when we first started. That's to the right of the red bar. That is when we developed our first guidance, most of the key information on mouse developmental studies and human epidemiology, none of that was available. Now there's many papers. The last bar was just part of 2016 when I made the slide. So when we did our PFAS search recently, there were more than 2,000 citations identified in screen. Basically, and this is one of my main points, that's one of our main conclusions that I want to make sure I get to. And this was discussed by Chris during his answer to the question. All of us have PFAAs in our blood, and the light orange is the average in the general population, probably mostly from consumer products and food. So there's factors, toxicokinetic factors called a clearance factor that relates the dose to the serum concentration for PFOA and PFAS. And then along with, we know what the average drinking water intake and higher percentile drinking water intakes are. You can combine all those factors and make predictions about how much serum will be increased by on average. There's individual variation, how much it'll be increased by a certain concentration in drinking water. So it's for PFOA with average drinking water, it's an average drinking water consumption. The average ratio is it's 114 times higher in the blood than in the water after ongoing exposure, and it reaches steady state. So you can see on the graph that very low concentrations, like 40 nanograms per liter, the blue is average consumption. That will overwhelm and dominate over the general population exposure. Similarly, we have this for the other ones that have longer half-lives. These ratios would be higher. And Dr. Scott Bartell from the University of California, a lot of people who are exposed to PFOA are interested in this. He put an online serum calculator that really shows the same thing, that people can put their individual drinking water concentrations in to make predictions of what their serum levels will be if they keep drinking that water. The reason we're concerned about this is because the dose response for the associations in the human studies is very steep at very low doses. in that low range, that's where we see these changes for cholesterol, increased liver enzymes, decreased vaccine response, and decreased birth weight. It's at these studies found associations in these low ranges. As I said earlier, infants drink more water, and it's in the breast milk. They drink more water on a body weight basis than older people. So if an infant's, the mother using the water, the infant will get higher exposure, the breastfed infant, and also a formula-fed infant drinking formula made with that water for these long-chain PFAS. These are 3 studies that shows how at birth it's kind of similar to the mother's level. There's in the infant, but then within a few months it goes up several fold. So it's another thing. I'm going to try to get through the rest of this very quickly, but basically there's a lot of epidemiology data, much more than for other drinking water contaminants, and we would prefer to use that in risk assessment normally, but we decided that, and most agencies have decided it's not appropriate. It's been precluded for use. A lot of it's because these chemicals co-occur, the exposure co-occurs, so you can't figure out the dose response for one chemical and get a number from that. But the human data provides support for public health protective approach based on animal data and justify concern about substantial increases in blood levels from drinking water. So we developed our risk assessments from animal data, and you can see the types of toxicity effects that we reviewed. I don't need to read it. They're based on reference doses for non-cancer effects for the most sensitive endpoint that's appropriate, meeting certain criteria. And we do need serum data because we compare serum data for the PFAS because we compare humans to animals based on the serum level, not on the dose. It's important because the same dose to a human, the same external dose gives a much higher blood level than in the animals, so we compare based on serum levels. For carcinogenicity, we evaluated that, but it wasn't the driving factor. A reference dose, it's the dose considered to be without risk over a lifetime. It's where you take the NOEL or LOEL from the study and divide by the uncertainty factors in case you're not familiar. And then those reference doses are combined with exposure assumptions for how much water people drink a day and how much could come from other sources other than drinking water to get like your health-based MCL or the lifetime health advisory that EPA develops. So our risk assessments come to different conclusions than EPA's. For PFOA, we based it on a different endpoint, liver weight, and the EPA's primary endpoint is developmental effects in mice. If we had just done that, our numbers would be identical, but we also looked at more sensitive mammary gland development effects. That's mostly from Sue Fenton's lab. I know she's here. There she is. And these it's very well documented and established. It caused a permanent change in the structure that persists to adulthood, and it occurred in the same animals at lower doses than liver weight. We did not want to base our primary risk assessment on that because nobody's ever used this for risk assessment before as the primary basis. The number would have been less than 1 nanogram per liter, but we did put an uncertainty factor for this and other low dose effects onto our reference dose, and that's why ours is 2 versus EPA's 20. For PFAS, the endpoint that EPA concluded to use was decreased offspring body weight in rats. We went through a very big process. It took my 2 colleagues, Alan Stern and Brian Pachkowski, several years. They reviewed thousands of papers, and immunotoxicity in mice came out as the most sensitive and valid endpoint, so it's about 10 times lower than the EPA reference dose. Okay. This just is to say recently, and a number of other agencies and government agencies, national and state agencies and academic papers have also concluded that it's the most
that immunotoxicity is the most sensitive effect of PFAS and are including it in their risk assessments. And these are the serum level increases like I showed before at the EPA health advisories and the New Jersey numbers. So we did PFNA also, as I said. We actually did it first. To sum it up, PFNA is similar to PFOA but more persistent in the body. It stays longer in the body. The toxic effects are more persistent. It's similar but more persistent and more severe. And our number for that is 13. And I'll skip the rest of the slides, but this one's extremely important because it's not widely understood. A lot of people think that New Jersey's MCLs are based on risk assessment and they're not achievable. It's a misperception we've heard at meetings in different places. The Drinking Water Quality Institute has 3 committees that consider 3 factors. The health-based number is the goal. Another committee evaluates the analytical capability of the drinking water lab community, the practical quantitation level, what the commercial labs can generally achieve, and treatability. So if one of those other factors was limiting, we would have set the number higher, but in this case, it was not limiting, so we were able to set it at, we have many other MCLs that are set at the PQL, so we did consider achievability. This is about our fish study, and I'm gonna skip it. We did a fish study and developed fish advisories. This is the status of our standards, which you can see later, and I just want to make it clear, I'm thanking a lot of people worked on this for many years, and all of our publications and reports are listed after the presentation if you want to look at them online. Thanks, sorry.
Thank you, Gloria. So to keep us on time, if we have one quick question, we'll take one quick question for Gloria, and then we'll have maybe some time for discussion later. Oh, Sue, right over here. And also, if you could please say your name before your question.
Yeah, Sue Fenton, NIEHS. So, Gloria, I think the paper that you published recently and that graph that you showed about the consumption is really important to think about, because not only is it the babies, but it's also the pregnant moms, the athletes, the military people who are in training and have to drink extra water. I mean, and so there's a lot that goes into that, the thought process. Right. Have other states used the same approach? Are they looking at that same susceptible subpopulation? Can you give us a flavor for that?
I didn't talk about exposure assumptions, but we use standard adult exposure assumptions, and we did say, because we consider that only 20% comes from drinking water. The standard assumptions are for an upper percentile. They're for the 80th percentile, so it's the people who drink a lot more water are somewhat included. Infants we did not specifically include, but we know that very young infants aren't eating a lot other foods and maybe not crawling around and getting exposed to carpets and things, so we thought that was somewhat protective. Vermont used they used EPA reference doses, but they used infant exposure assumptions. US EPA used a higher drinking water consumption for lactating women. It's not almost twice as high as what we used. And Minnesota has actually modeled exposure to infants through breast milk and formula for PFOA and PFAS, and they used that in their numbers for PFOA and PFAS.
Okay, thank you. Thank you, Gloria. Okay, so I'll introduce the last speaker for our morning session is Dr. Mark Striner. So Mark has done some of the pioneering work on identifying novel PFAS compounds, and of note, worked with colleagues at the EPA as well as Dr. Detlef Knappi, who we'll hear from, and Dr. Mason, who we'll hear from later, to identify the Genex compound and multiple other compounds related. With that, Mark, I'll let you have the floor.
Thank you, John Z. So I have, what, 7 minutes? No.
You're good.
So I'm glad to stand before you and tell you this story. It's not just my story. There's a lot of people that contributed. I'll show that at the end. But I'm part of the National Exposure Research Lab, and that's not just perfluorinated chemicals. It's many chemicals. So we're looking at what it is that makes it into human beings, and my job is to develop methods to look for those chemicals, because we can do nothing about them until we know what they are. So this paper actually is sort of the epicenter in the United States of the C8 study. So you could look over there on the far right, and that's an industrial plant that's making or using perfluorinated chemicals. They go up into the environment in the air, they go into the water, right? They make it into the soil, the groundwater, et cetera. We've done a good job of covering many of these things for the work we do. You know, Chris talked about all the different tools that we have. You know, we don't have GC high-res capabilities in our lab. That's missing, right? We're missing some of these chemicals. Those that are LC amenable, we can find in soil, groundwater, in water, et cetera. We can find them in runoff. There is still that missing piece, and this paper basically sets the stage and says these chemicals make it into the environment by being emitted into the air. So if you have GC capabilities and you're interested in this topic, then you've got a lot of work to do. Heather? So we're beginning to look at this. We're beginning to look at the compounds that are making out into the environment, and we know that these things are volatile and can get out into the environment and be disseminated. Public service announcement. If you use ChemSpider, maybe use it a little bit, and now start using this. This is our chemistry dashboard. Go to Google, search for it. We have an amazing group of people, Tony Williams and Ann Richards at the EPA, have put together this dashboard to be the warehouse or the storehouse for chemicals. There's a lot of information that you can look up. I show one poster child here, the PFOA. Toxicology data, structures, if you can't draw them, you can just copy them. Go and look for occurrence if we have tox data, et cetera. In our lab, we're trying to find out what's important. We're doing suspect screening. We're trying to find those suspects that require additional scrutiny, much like you do in a lineup. It's often large peaks. These are not the small things. They're often found in many samples. They have some of our favorite halogens. Fluorine is on there, but it's not the most exciting halogen, I would dare say. I like chlorine and bromine more. Negative mass defect is a tool we use. I'm going to tell you what that is. Related chemicals, sometimes we don't even know what these chemicals are, but we know how they're related to each other. That gives us information that's very important if they differ by a subunit. And we use this diagnostic fragments. Much like Lego pieces, if you break them up in their individual sizes and colors, you can use those little pieces to figure out, well, what is the larger molecule it comes from? We list some here, some of our favorite friends, you know, the CF3 and the CF3-CF2. At the very end, we're now finding these chlorinated species from these polyfluorochloro compounds. So this is a paper from 2013, the Wang paper. It's kind of like playing whack-a-mole when it comes to these compounds, right? And when the PFOA stewardship agreement sort of was happening, companies were agreeing to no longer make those things that they had been making for many, many years. And they were beginning to make other things that have oxygens in the structure. Here a couple are shown. Adana, 3M product. Gen X. We were not the first to name it Gen X. The Wang paper did. That's the fluoropolymer that we now see in North Carolina in the river. Polyfluoroethers. They're also the perfluorinated, polyfluorinated on one end. So we have a CH2, CF2, et cetera. Chris talked about these with the AFFF. So there's lots of different structures. And lastly, we're working with some states and regions in identifying some of these polyfluorochloroether compounds being found in the environment. Chlorine is a wonderful thing to see in a mass spec. It gets me very excited. I don't like to, however, see it in the environment. So there are lots of things to look at. The things that Chris showed are sort of underwater. And the mass spec actually shows us lots of features that we don't always know what they are, but we know they're associated with each other. We get these adducts and fragments and dimers. They all point back to the same molecule. My job is to figure out what they are. We also see these homologous series. Perfluorinated chemicals do not exist as one. They exist in groups. Much like at your family reunion, it's that unwanted Uncle Bob, right? Or that undesirable boyfriend that comes along for the ride. They show up. In-source related species. Many of these peaks point back to one individual compound. In this example, Gen X, or HFPO dimer acid, every one of these peaks in the mass spec is pointing to that one molecule. We have to be able to interpret what those are. Now we can figure these out and say, I know what this is, and they all point to the same thing. Early on, we didn't know this. An example of a homologous series, every one of these peaks is separated by a CF2 unit, and the molecular weight of a CF2 unit nominally is 50. So when you see peaks that differ by 50 units, and they separate in a homologous series with the smallest one being first and the largest one being last, you're probably onto something, and that's another tool that we use. And one of the ones that we use regularly is this negative mass defect. And I always have to preface this with saying this has nothing to do with charge, right? Negative mass defect is a term where when you put a molecule together that is made up of a bunch of elements, these are all of our favorite elements. If yours is not up there, I'm sorry, but these are the important ones. Carbon being carbon, mass 12, and as you add protons or oxygens or fluorines to that molecule, a positive mass defect just actually means it's higher than a whole number, okay? So a proton is. An oxygen and a fluorine, for example, are less than a whole number. So it's a mathematical manipulation. As you add carbons and oxygens and hydrogens and fluorines together, you basically make a whole molecule and you measure its molecular weight. That's what a mass spec does, to a high degree of certainty of the 4th decimal place. I'll point out, it only takes one proton to overwhelm 4.8 fluorines. So these polyfluorinated compounds, negative mass defect is not always the tool we can use, right? It's a tool that we've used here in North Carolina and other places to find things. Chlorine and bromine and iodine, which I don't have here, is also very helpful. And so in this example, octane, if you drive a vehicle that doesn't plug into the wall, octane's important to your car to make it run well, right? Only carbon and hydrogens. It's a positive mass defect. All those protons gives you the molecular weight that ends in the green number at the end. It's more than a whole number. If you oxidize that compound to make it octanoic acid, those two oxygens make it slightly more mass negative. It's still a positive compound, mass defect-wise. And if you fully fluorinate that compound, it now becomes a negative mass defect. So the takeaway would be it ends in 0.9 something. These show up in the mass spec. We can find them fairly easily. Chris mentioned AFFF. Essentially what you're doing is you're taking the one on the bottom and the one on the top and you're sticking them together. And what actually happens is you still have a positive mass defect. You have the negative mass defect portion of the molecule that's polyfluorinated there, and it could be tuned down to that point if you oxidize it or microbially contaminated sites degradation. Not easy to find sometimes unless you know what you're looking for. So our approach is to go out and take samples, measure for things, upstream and downstream of input sources. Could be this plant that's on the side of the Cape Fear River. Could be a golf course that has a waste stream going into the environment. It could be overland flow from a farm. All of these things happen. Take samples upstream and downstream of sources. So we did this in 2012. Around that time, we had already published on the Cape Fear River, Nakayama et al. 07. We were measuring for 10 perfluorinated chemicals. We found them in the Cape Fear River, the Haw, the Deep, etc. What we were not looking for at the time of 2007 were the two compounds at the top. That's C4 and C5. Excuse me. We were looking for all the ones on the bottom. And what you'll notice is that the red line coming from the right side upstream to the downstream side on the left, there was a large concentration spike. The other thing I want to point out is that these compounds were already in the river, many of the ones we were analyzing for, and they did go up. So they're already present, but we did find a spike. And we wanted to take a closer look at what was happening at that red line. So we use this negative mass defect tool. So the mass defect on the bottom would have negative mass defect, on the top would be positive, and those things in effluent or downstream would be in red, and those things in blue would be upstream. And what we noted was that there were a lot of things that showed up in the downstream sample that were not in the upstream sample that were negative mass defect and were likely fluorinated compounds that required us to look at more closely. So that's what we did. We also found that there are lots of things that go on in the mass spec. You know, 5 years ago, I really didn't understand this. Now I understand it well. There's a lot of stuff that goes on in the mass spec in the gas phase that helps us now figure out what these are. We can see the intact molecule. We can see a proton-bound dimer. This is just two of them coming together with a proton, two coming together with a sodium, and unfortunately, when there's a lot of them, they just start glomming together as trimers and tetramers. This is a tool we now use to pinpoint that we see polyfluorinated carboxylic acids in a sample, first published by Xenia Trier. So our paper in 2015, we identified 12 unique polyfluorinated compounds found in the Cape Fear River. We published on them. There were 6 monoether perfluorinated compounds, of which GenX is one. We use this name, the IUPAC name that's not as cool in the paper. Polyethers, we found 4 of those, multiple oxygen linkages, and lastly, we found these polyether sulfonates, Nafion byproduct 1 and 2, we call them now. And so we gave the details of how we did that and what we found. Problem is, it's really, really confusing. It's an extremely complicated process. At this facility, hexafluoropropylene oxide, or HFPO on the top there, is sort of the building block. It's used to make everything that we sort of see. All the compounds on the top, I will point out, are volatile, and these are not L-seeable compounds. These are G-seeable compounds, so this is really theoretical for me. I just know that that's what's going on. This one, that second, do I have a pointer? Okay. Those of you online won't see this, but there's these acid fluorides. These acid fluorides are intermediate that being used to make polymers, these polyvinyl ether intermediates. These compounds are all volatile, and if that fluorine leaves, it becomes a carboxylic acid. So we measure this with the mass spec. This is an anionic species that is seen by our mass spec that can either go through this HFPO dimer acid, which has this Cas number, or it can go through this ammonium salt, which we call GenX here with that Cas number. The mass spec does not differentiate, but all of that can come and lead to that analyte. So there's also these polyvinyl ether production facilities that take those acid fluorides and turn them into these polyvinyl ether compounds that are used to make larger polymers. We can detect those in the environment. And lastly, there's a production of this Nafion. This is a copolymer made up of tetrafluoroethylene, this end product, and there's a Marcouche structure for what it looks like. We can see those individual compounds via the mass spec. We can't see the polymer. We can't see many of the things that lead to the production, but we can see them in the environment. Again, analytically, it's an LC mass spec method. So this paper we published along with Mason and Detlef Kanapi in 2016, and that was the thing that got the press's attention, right? It woke up to find the toxins taint the water down in Sweeney plant. And that's sort of when our life changed. I wouldn't say for the better or for the worse, but it did. Just prior to that, I happened to be out on the river. This is Zach Hopkins. We had gone through Lock and Dam 2. They were beginning to already think about, well, how do we get rid of these compounds if they're present in the river, if they're present in the raw drinking water? And so we were out collecting from the river these compounds to see if they can be removed through batch culture, if you run them through GAC or ion exchange. And what we did find, this is in May of 17, before that news broke, HFPO dimer acid, or GenX, was that little blue peak right there. And hopefully visually you can see there are a lot of other players on the board, and the size of that peak is usually proportional to the concentration. So the hit home point here is there are other things in the river that were of higher concentration based on that response, of which GenX was one player. But these are all the compounds I just spoke about, this PFMOAA, et cetera. And we have to do something about that. So we started working with NCDEQ. Many of those people that are either not here in the audience or probably listening online. We had a 6-week, very, very intensive sampling protocol where we went out and started measuring for these compounds, not only on the Cape Fear River, but also in finished drinking water. And here's what we found. Over the course of those 6 weeks, not only in the Comores effluent, but also in the Sweeney finished drinking water, which is down in Wilmington, we saw a large drop in concentration after some initial high concentrations because it was actually saturating our detector on the mass spec. These compounds all dropped with time. But at the same time, what we found were these two compounds, Nafion byproduct 1 and 2, did not drop with time. So there's another source, there's another production that's going on, and those compounds, though these had gone down, were not continuing to drop as we went and sampled. And since then, I believe this has gone down as well, because we have to inform those that are regulated and are discharging into this river that we're seeing this, and the report back hopefully helps to figure out what do we do about it? How do we get rid of these compounds? And so now we see that. One of the things that some of the previous authors have talked about with high-resolution mass spectrometry is that we can go in and we can mine our data, not only for the things that we have right now. The grand thing is if you bank your data correctly and you ran them well to begin with, you can go back and look at samples years later. And so we did this recently. This is some work that's in press right now, or in prep, I should say, soon to be released from the agency to be looked at in a journal. James McCord, my postdoc, looked through all of our data since 2011 and started looking for things we hadn't yet figured out. And as it turns out, some of these molecules were always there, but we just didn't know what they were. Here's an example of one. It's a 1H substituted perfluoroether acid. Was always present in the sample. It's this column right here in green check marks since 2011 until our last sample for this study. And there are other associated analytes that only differ by a CF2 group. We were able to go back and remine that data. It turns out it has a name. Called up the Comores chemist and said, do you know what this is? And said, yes, it's called NVHAS. And now we have a standard for that. We can measure for it. In addition, we found these two molecules. The one on the bottom is called hydroeve. Hydroeve has always been there. In many instances, we would see it, and also its partner over here. This is much like Naphion byproduct 1 and 2, where you have a double bond on the end or you have a proton in this position. Again, the green or the red says if it's there or not. This has been present, and it has a name. We have a standard now from Chemours. We named it. It's hydroeve. And lastly, these are exciting ones from the standpoint of they're different. They're polyanionic. So there's a sulfonic group and there's an acidic group on the other side. If those are both charged, they really go through GAC very easily, and they're going to be hard to retain. And as you look, there's other associated ones differing by those CF2 groups, sulfonate on one end and a carboxylic on the other end. Hard to remove, likely ion exchange or reverse osmosis could do that. But we mined our data. We had it there and we could go back to it. And I'll say one thing about high-res mass spec, it's not the end-all be-all. Use the tools you have. Here's an example. This is extracted ion chromatogram confusion if you're not a chemist. These two molecules are almost identical in molecular weight. They only differ by about 5 ppm. And in molecular weight, that means they're very close in molecular weight. As it turns out, if you just extract for the molecular weight of these compounds, you see a peak. The chemist actually at Chemours actually asked me if they were seeing this one in samples and if I was seeing it. I said, no, I think you're seeing this compound. This is a compound you make and or use. And the reason is they are very similar molecular weight. When you do an extracted ion chromatogram, you get a peak. It doesn't necessarily mean it's your compound. You actually go and look at the spectra. The M is the molecular weight of the compound. The M+1 is due to carbon-13 and deuterium, et cetera. When you get over to the M+2, this is a sulfur peak. We can differentiate between these two compounds by going to that much detail. Those of you who don't do this for a living, this might have completely confused you. The take-home message is it doesn't answer every question when you have high-res mass spectrometry. Right? You still have to have a brain sitting there, looking at the data and figuring it out. So we have other stuff going on right now that I can't give the details because it's going on in states that begin with new and do not end with Mexico. It's also in North Carolina and, let's see, Michigan, Minnesota, et cetera. So we're looking for these other compounds that are out there in the environment. Like Chris said before, it's the stuff that's underneath the water on that iceberg, right? We're doing air work now. It's not getting a pass. We have groups within EPA that are starting to look at air more closely, and I'll mention a little bit about house dust. So on the end of the story here, these are Impingor samples that air people would be very familiar with. You go into an emission site where the air is being discharged up into the atmosphere, and you put this apparatus on. You take the air out from that emission site. You run it through XAD trap. This is an anion an exchange resin, series of aqueous impingers, and you trap and see what is present on them. I don't have a GC, I have an LC system, so I can still only look for those things that are LC-able. There are GC-able compounds in there. And once you get that sample and you don't know what they are, you can still do something with that data. James McCord, my postdoc, made this recently. This is a Kendrick mass defect plot. All this is doing is taking all the peaks that we see in any sample, regardless of what that sample is, and we put in, if it has a carbon, fluorine, hydrogen, or oxygen, figure out how those are related, and if they're related by those subunits, put them on a line, color them, and show them to me. Because it's hard for me to pick out that these three peaks are associated with each other. The algorithm can do it much better. And what you'll see here is some things are associated with each other in this red line by a CFO group. Some are associated in either green or yellow by a CF2 group, some by a CFO2, I can't read it from over here, the blue, and the purple one on the top by a CF2O. So it's teasing out the data, it's showing me the things that require more attention without me knowing what they are, and that helps us in discovering what those compounds are. Lastly, I'll tell you about house dust. We have a large group of people at the EPA that are interested in this, because it's not just water, as was mentioned, it's the products we use, it's the things we have in our home, it's the things that you wear, your carpeting, your upholstery, et cetera, right? The paper bag that has the popcorn in it, right? These get into your house and we see them in house dust. House dust is a great repository. This is a standard you can buy from NIST for house dust, 2585. And what I noticed was there were two peaks in the sample. I was sitting around a Science Friday, so these giant two purple peaks, bubble plot. It's a big peak. It's probably a high concentration. I wanted to take a closer look. And what I found when I extracted those two ions is it looked a lot like a PFAS peak or a PFHS peak. And what you see is a linear peak is the bigger one, and a branched peak is the one that comes right before it. And anytime we see that, I immediately think polyfluorinated sulfonic acids. As it turns out, they were eluting later than PFAS, which means it's probably bigger, still with that same type of retention look, and they differed by 2 CF2 units, so basically 100 AMU. And as we went in and looked on the mass spectra, we saw that it was chlorinated. And what we identified was this compound. So this is a polyfluorochloro compound, polyfluorinated on this end, tetrachloro. So one of these buttons did something bad, I'm sorry. Tetrachlorothalate on the other end. And I recently presented this at another location, and someone asked me, well, what is this molecule? I said, I have no idea. And I did some searching in SciFinder. It had 2 uses in the patent literature. It was for ant control, and it was for hairspray. So apparently this helped you keep your hair nice and neat in the 1980s, which could completely explain what we see in house dust. And this is how we figured it out. We looked at the fragment. In the mass spec, you have to do QTOF work sometimes, or Orbitrap work. A loss of a CO2, we see this spectral feature, which is that chlorine on that compound is 4 chlorines. And if it loses the CO2, this is what it was originally. This is what it is after. So we're very, very sure on the identification of that. And there are other associated compounds similar to that. So a little taste sort of what we do with the types of samples. I mentioned water. I talked about house dust. We are doing work with human serum. Some of our colleagues in the audience here, Jane Hoppin's here. We're doing work with fish with some of our state partners, dabbling with air now. I think at the end of the day, the story is the same. As a chemist, my job is to figure out what's there, to say this is the molecule, and then I have to go see Jamie and say, what does it mean, or go see Sue, or call Chris because he's not here and say, hey, can you do some tox testing on this? The identification of that compound and then being able to get it as a standard and do tox testing is really critical. So with that, I will take questions, but I will mention there are a whole bunch of people that contributed to this. I'm going to give them all kudos. I don't have a slide that gives all their names, but I'm just the one that gets to stand here before you and tell you about this. So I'll stop there.
Thank you very much, Mark. Yeah, we have some time for discussion.
Over here.
Hey, Mark, thank you. I'm guessing you're going to know what I'm asking, but any word on Nafion?
What about it?
On the last we heard prior to the hurricane was that the standard was somewhere at EPA, at a lab, and it was causing difficulty with the machinery, and so that we weren't getting the data. Do you have any update on that?
So since late fall of last year, everything's been done at the Region 4 lab. We have ceased to be the one that's doing the analysis. We do have standards in my lab for that. I know those standards have been shipped to the Region 4 lab to do the analysis. I'm out of the loop with respect to any problems they're having, so I can't give you an update.
Okay, is there any, I guess the question then is, if you have the standard and you have the capacity and they're having issues, and this is kind of an important piece of data that we've been missing, is there any way that we can encourage whoever's at 4 to send it back?
Detlef says he's going to show something about that, but I'm unaware.
Awesome.
I'm unaware that there's an issue. I'm glad to sort of jump in and help. We have the standard. We have the know-how. We don't always have the capacity, but I'm glad to talk to whoever's having that issue and help them solve it.
Hey, Mark, I'm going to ask a question. Lee. So I'm really intrigued by the PFAS, the alternatively halogenated PFAS. So chlorine, bromine, iodine. So you showed the example of the chlorinated phthalate with the PFAS tail. Have you seen brominated versions? Have you seen iodinated versions as well?
I can't say that I have. We have definitely seen chlorinated. I don't think we've seen anything brominated yet, and I really haven't looked for iodinated.
Have you gone into either the chemistry dashboard or to for example, SciFinder to kind of get an idea of what the possible chemical space is that would have PFAS sort of moieties of the molecules, but also have other halogens that might be used in industry? Do you have any idea of how many compounds there are, or what kind of compounds these are?
I mean, it's immense. I think our PFAS master list is something like 5,061, I think, is it right now. And I know that there are iodated species, but they're precursors to the things we sort of see in the environment. An example would be the fluorotelmer alcohols. There's an iodine on the end, and it's a great leaving group, and you can do lots of things with it. I'm not familiar with how much is there and what the chemical space is for the iodinated species, but I mean, it seems like a good approach to sort of go out there and see, what's the chemical universe. Good question.
One of the chemicals that's used, F53B in Asia, I think is chlorinated on its tail as well. So, and it's suspected to have a huge half-life as well.
And I think that was in the Wang 2013 paper. I think it was one of the ones on the bottom right there. It's been detected. John Z. Lang says it looks a lot like Naphthalene byproduct 2.
Any other questions for Mark? Or since we have a few minutes for Gloria, even? Okay, well then, in that case, let's thank our, one more, okay, sorry.
Oh, wait, are you going to ask Gloria? Okay.
I noticed in one of your slides, you showed a slide with other chemicals from the Comores plant. And I believe it was in the river. And one of them seemed to have a very high concentration relative to the C3 diamine-acid.
Mm-hmm.
And I believe that was the PFMOAA.
Correct.
Are you seeing a correlation where you seem to see that very high as you see the C3 dimer-acid, or is there no correlation?
Can you rephrase your question? Is there a correlation between that compound and the
Yes.
C3 dimer-acid?
Mm-hmm. Because it was at a very high concentration in that slide relative to the C3 dimer-acid.
Yeah. It still was, and basically as one came down, they all came down. So industrially, as that process where that effluent was no longer released into the environment at the effluent site and was taken elsewhere, we saw all of those drop the same. Doesn't mean concentration-wise that they all went to nothing. And we also can't tell you, because a big peak usually means it's higher concentration, that it's actually a higher concentration. It could just respond better. We now have that as a standard. We have gotten that from not only the company that makes it, the Comores site, but there's also a vendor that can sell it to you, and beginning to look at not only analytically measurement of it, but toxicologically, well, what is its effect on whatever organism you give it to.
Okay, well, so with that, let's wrap up our morning session and thank our speakers.
Can we shut all these down?
Okay, and so at this point, I encourage everyone to step outside into the hallway and grab some lunch, bring it back in, and have some discussion during lunch.
So we thank you all for staying for the afternoon session, and we're pretty excited this afternoon to share with you sort of the developments that have sort of built upon the researchers that gave great talks this morning on some of these emerging contaminants, and especially PFAS. And so this afternoon we're going to talk about PFAS in North Carolina and how a new monitoring network is being established to help sort of address some of the major questions we have about these compounds in both air and water samples throughout the state. So I'm sort of the new kid on the block. My name is Jason Surratt. I'm a professor at UNC in the Gilling School of Public Health. I say I'm a new kid because I'm an atmospheric organic chemist, and I have not studied PFAS in the past, but I think my team and others at UNC bring some unique expertise on the air side, and it was really exciting to hear Mark's opinions about how air emissions and the fate of these compounds in air can also help us understand the fate of these compounds in the environment. So I figured a lot of the PFAS researchers don't know who I am, so since I don't have someone introducing myself, I thought I would just say a few words about my background. I'm originally from North Carolina. I grew up here. I went to NC State for my undergraduate, and then went on to California for a number of years to get my PhD in chemistry. And the research that I have mostly been focusing on throughout my career has been looking at emissions of both natural and human-derived emissions into the air and how that gets transformed into urban smog in various cities. And so here are just two pictures of areas where I've helped in the past to organize major field studies. One here in Los Angeles, we've had a major field study occur there to look at smog, and sort of that brown cloud that you see over Los Angeles is the particles that I'm interested in studying in terms of organic particles. And certainly in North Carolina, we have a similar problem. And just very briefly, the expertise that I bring as the program manager. So my role in the PFAS network is more on the management side, so helping to guide the review process for proposals, solicit scientific reports that we use to report to the state legislature, and also interfacing our results with stakeholders across the state, so both communities and the state. But my research, what I bring to the table in terms of my research background is I also use both targeted and non-targeted mass spectral analysis to look at organic contaminants in the air. And so this picture is showing you a few molecules of interest to us in my research group, where we look at the natural emissions interacting with industry emissions or coal or combustion in this part of the world, and seeing how those complex interactions lead to smog in our area, especially in North Carolina. And so one of the things that I hope the air group will bring, as you'll hear later today, for example, is that how will fine particulate matter, for example, be carriers of these emerging contaminants, and how does that maybe affect transport to other parts of the state, and so on. So I just wanted to provide sort of a brief outline of our afternoon agenda. We're first going to start off hearing some important results from Detlef Knappe and his colleagues discussing PFAS in North Carolina. He's really been at the forefront of this area with colleagues at EPA like Mark Streiner. And then we have a nice set of talks sort of laying out by first Jeff Warren how this sort of came to be in terms of our PFAS network being established for the next 18 months to study these compounds in North Carolina. And so he'll provide some of the policy language and landscape of how this all came about. And then we'll take a short break. And then I think the part that I hope you all will find very interesting too is hearing about some of the details of the plans that we have in store to study these compounds in North Carolina. So we'll have 5 lightning talks, and what I mean by that is these will be 10-minute talks by each of our lead investigators from our 5 research teams. And then followed by the research talks, we'll have a pretty good time set aside for questions that you might have and answers that they can hopefully provide. So the talks are brief now only because the network has just been established and there was a lot of effort that has gone into that, and I'll discuss that a little bit later when we get into the lightning talks. But since we don't have results yet, we're as you'll see, we're beginning the process soon to be collecting data, and then we'll finally close. And so finally, for the welcome, I just want to thank the sponsors and also really Lee Ferguson and his team here at Duke for allowing us to come here and use the afternoon to sort of really share with you all our plans based on a lot of the important research, as you saw this morning, that highlighted some of the major questions that certainly apply here in the local area of North Carolina. And so we also want to thank our financial sponsors, obviously Duke for sure, Superfund, the North Carolina Policy Collaboratory for their funding, as well as folks at UNC, in particular the Center for Environmental Health and Susceptibility, as well as the Gilling School of Public Health. And I just want to note that the food and beverage were paid for by state funds, and so non-state. Yeah, you can tell. Sorry, non-state funds. Sorry about that. You can tell I need more coffee. So yes, non-state funds. So now we're gonna. Sorry, I'm sorry, Jeff. So now we're gonna move into. I hope you'll find a great talk. I've heard recently Detlef's work on PFAS in North Carolina, and so Detlef is a professor in civil engineering, civil construction and environmental engineering at NC State. We'll try to trade places here. Yeah, there. Thanks. And so his research is focused on, as many of you know in the room, on drinking water quality and treatment, water reuse, organic micropollutants, development of water treatment processes for polar and persistent organic pollutants, such as PFAS, and the fate of these organic pollutants in solid waste landfills. And we're really happy to have Detlef here to talk about this topic. As Mark kind of alluded earlier, Detlef has helped to also play a role in measuring these compounds in the Cape Fear River, which has drawn a lot of attention to this topic recently.
Thank you, Jason. And good afternoon. So I have the non-enviable task of speaking right after lunch. So I'll try my best to keep you all excited. And this is certainly an important topic, studying emerging contaminants in our drinking water supplies. And so my assignment for today was to talk about PFAS in North Carolina. So I'll tell you what we know about their occurrence. And this has been certainly a team effort, students and postdocs in my group. And as Jason mentioned, we've collaborated very closely with researchers at EPA. So you can see some of the actors here in the pictures. So in terms of an overview, I'll talk about this very briefly, this idea of we all live downstream, and that's in the context of unplanned potable reuse, and then move right into PFAS occurrence in North Carolina, and I'll talk about two data sets. One is the data that came out of the third unregulated contaminant monitoring rule, and then I'll focus primarily on PFAS occurrence in the Cape Fear River Basin. And I'll close with some remarks on what the impacts of PFAS in drinking water sources have been on drinking water providers in the state. So, you know, in North Carolina, PFAS are primarily a surface water quality problem. And so we really need to think about this idea of we all live downstream, right? There's always somebody that lives upstream of us. They're discharging stuff into our water, and that water gets reused for potable purposes in communities downstream. So it's very important that we understand what these wastewater inputs are into drinking water sources, and also what the non-point sources are of pollutants that run into our surface waters. So if we think about PFAS, you know, point sources of PFAS are municipal wastewater treatment plants, and they are important because often they receive wastewater from industries that discharge into the sewer. Also, wastewater treatment plants sometimes accept landfill leachate, and landfill leachate has been shown to have elevated levels of PFAS. And municipal wastewater treatment plants are currently not designed to remove PFAS from the wastewater. Similarly, as we all know, with the facility, the fluorochemical manufacturing facility by Fayetteville, some industrial wastewater gets directly discharged into the river. So there are, again, biological wastewater treatment plants that are removing the stuff that we all look for, like oxygen demand and suspended solids, but these treatment plants are not designed to remove emerging contaminants like PFAS. And then for the non-point sources, you know, we need to think about managing runoff, for example, from firefighting training areas, whether that's at military installations or at also civilian airports. And we also need to think a little bit about the land application of biosolids, or should I say sewage sludge. These are often laden with PFAS, and when it rains, stuff runs off from those fields into our surface waters. Then there are some other non-point sources, like contaminated groundwater can discharge into surface water. And then, as we've heard earlier already, there's dry and wet deposition that's connected to the air emissions of PFAS at fluorochemical manufacturing facilities. So to just highlight the importance of this we all live downstream concept, one of my students got paper records of all the wastewater discharges. This is for a couple years. This is now several years ago, 2011 to 2013. All the wastewater discharges upstream of the town of Pittsboro. So the town of Pittsburgh takes water out of the Haw River, and the Haw River is a relatively small stream that receives wastewater from many upstream communities. And so in blue on this figure, you see the stream flow, which I'm showing in millions of gallons per day, and that's kind of a unit that we use here in the US for designing drinking water and wastewater treatment plants. So just to give you a reference, right, the city of Raleigh on an average day treats about 50 million gallons a day. And so you can see here on this figure, you know, the Haw River sometimes flows at less than 100 million gallons a day. So it's a relatively small river, but it's receiving wastewater from several communities, including the city of Greensboro, city of Burlington, Reedsville, and so on. And in green, I'm showing the percentage that we calculated that in the Haw River that's actually wastewater from these upstream communities. And so you can see that during periods of low flow, you know, more than 50% of the flow in the river is wastewater, right? And there are no special considerations for this unplanned potable reuse, right? So that's something we really need to carefully think about. And so let me move now towards PFAS and look at national occurrence for a second and put then the North Carolina situation into perspective. So as we've heard already a couple of times, the UCMR data set was mentioned. It's a huge data set. Between 2013 and 2015, almost 37,000 samples were submitted by public water systems across the US, and in essence, almost 5,000 public water systems submitted their samples here. All of those were systems that served more than 10,000 people. And in the UCMR, 6 PFAS were included, and then a very nice analysis was done by Harvard University and many other co-authors, including also Andy Lindstrom, to look at the impact of PFAS on drinking water in the US. And so the US EPA in May of 2016 issued a health advisory level for PFAS and PFOA at 70 nanograms per liter. And based on this analysis of the UCMR3 data set, there are at least 6 million US residents then that receive drinking water that exceeds that health advisory level. Now, if we compare the US situation to North Carolina, you know, when you look at statistics, the occurrence of PFAS in US drinking water samples, maybe at first glance, almost seems somewhat unremarkable, right? 1.6% of samples had PFAS in it. 4% of public water systems had at least one sample that had PFAS in it. You know, that when people look at this at first, they don't get super excited about it. But when you think about that 6 million people across the US are impacted, that's already a sizable number, right? So statistics can sometimes be a little bit misleading. And if you're one of those 1.6%, you know, then you care about whether PFAS are in your water. Now, if we look at the occurrence, you know, if we look at where does the drinking water come from and where did the PFAS contaminated water come from, nationwide, PFAS is more of a groundwater problem. You know, more than 3/4 of the drinking waters that had PFAS nationwide were derived from groundwater. Now, if we compare this to North Carolina, the occurrence of PFAS is much higher, right? So basically double the number of samples relative to the national occurrence rate. And if we look at public water systems that had at least one sample that was positive for PFAS, it's 13%. So that's pretty significant. And then if you look at where did the PFAS contamination reside in North Carolina, essentially 80% was in surface water. So it's much more of a surface water problem here in North Carolina. And you can see at the bottom the statistics here in terms of number of samples and public water systems that were sampled. So where in North Carolina were these PFAS samples found? There were 20 public water systems, and they were located in 11 counties, and most of those counties are in the Cape Fear River watershed. So if you go from Guilford County, Orange County, Wake County, Harnett County, Cumberland County, Moore County is also interconnected with Harnett County, and then New Hanover and Brunswick counties. All of those are counties where communities receive water from treatment plants that treat Cape Fear River water. So I'll focus on the Cape Fear River in particular then, and so the Cape Fear River is the largest watershed that's completely contained in the state of North Carolina, and it's the drinking water source of 1.5 million North Carolinians. And when we look at wastewater discharges and industrial contaminants that are discharged into the river, the Cape Fear and its tributaries, about 1 million North Carolinians are impacted by those discharges. And so we'll look at a number of different communities. Community A is Pittsboro, B is Fayetteville, and C is Wilmington. And we'll start out kind of in the upstream area. So let's look at Pittsboro here for a second. So these are some data we collected in 2013. We collected composited daily samples. And in this case, this is the source water for the city of, or the town of Pittsboro. And we summed up here the PFAS and PFOA levels. And you can see that for the first half of the study period, the PFAS and PFOA levels were lower relative to the second half. But even during this first portion of the study period, there were several days where we exceeded that health advisory level of 70 nanograms per liter. And then after September, things became significantly worse in the sense that the PFAS and PFOA levels were highly elevated. When we look at why this is occurring, this is primarily related to stream flow. From September to October, stream flow was much, much lower. We were in a drought period, and that's why the concentrations in the river were higher. So in essence, there was less dilution of these upstream wastewater discharges. But there's also, not just PFAS and PFOA in this water. If you look at all the other PFAS compounds that we targeted at the time, you see that there's several hundreds of nanograms per liter of the heptanoic acid and the hexanoic acid and so on. And so if you sum all this up, you're getting into the microgram per liter range, greater than 1,000 nanograms per liter PFAS in this drinking water. So you might also ask, this was 2013, what is the situation like today? We're working with river keepers across the state, so this was a sample that was collected last month. And here we're just breaking down the concentrations in the Haw River at Bynum, which is the intake location for the town of Pittsboro. And you see it's basically a very similar picture. There's still about 1,000 nanograms per liter PFAS in the source water. Now, if we look at the situation across the different communities that I highlighted earlier, again, these are some older data. In Community A in Pittsboro, the levels were relatively high. These are averaged over 127 samples. Once we go down to Fayetteville, these PFAS concentrations dilute out because a lot of tributaries come into the Cape Fear River that have very low levels of PFAS in them. But then when we get down to Wilmington, this red bar popped up, and as everybody knows by now, this was the Gen X that was identified. And the challenge with these PFAS compounds is that even advanced drinking water treatment plants like the Sweeney Water Treatment Plant down in Wilmington, which contains advanced oxidation, biofiltration, all processes that you wouldn't find in most treatment plants around the state. Even with all the additional treatment that they had installed, the PFAS compounds passed through the plant untouched. And the other important thing that we observed was when you look at the Gen X here in red, and we look at the Gen X here in red again at the very left end, there were several other PFAS in the Wilmington drinking water that were present at much higher concentrations, here shown just as a mass spectrometer response because we didn't have standards at the time. And none of them were removed by this treatment plant. So as Mark already pointed out, we try to get the word out. Scientists do this through peer-reviewed publications, but that didn't really stick very much, and it wasn't really until the press picked up on the article that the public and also public officials became aware of the situation. Now, in this case, a single manufacturing facility, the Chemours plant near Fayetteville, was the source of the Gen X and the other newly identified PFAS. And this company then agreed on relatively short order to collect their processed wastewater. And so it's an experiment in source control in a way, right? So the source was shut off, and we can see, well, how does the watershed respond as a whole? And you can see here in June of 2017, on June 19th, the sample was collected 2 days before the plant started to collect their processed wastewater. And by July, mid-July, the levels had dropped already dramatically. And by October, the levels had dropped even more because additional processed wastewaters had to be collected. And as Mark pointed out, these processed wastewaters were related, for example, to the Nafion manufacturing process. Here you can see an estimate of the Nafion byproduct 2 concentration in July at 1900 nanograms per liter. That's an estimate based on the Gen X MS response. That's the only thing we had at the time. Now, you might ask then again, what's the situation look like today? Or not exactly today, but in February of this year, we did a little study with Brunswick County. And what you can see is that the concentrations of the legacy compounds that are shown more towards the left are relatively low, in the 10 to 30 nanogram per liter range. But we still see a bunch of them, right, from C4 to C8. They're all detectable. PFAS is also there. And then still the PFAS signature down in the Wilmington and Brunswick County area is dominated by these new ether compounds, and PFMOAA, a very short-chain ether, is the dominant species. And now we have analytical standards for these compounds, so these are the actual concentrations that we measured by LCMS. And so there was earlier a question about Nafion byproduct 2. So in this particular sample, it was somewhere around 20 nanograms per liter. So this is where we are today in the lower Cape Fear River. But there are other places in North Carolina that are impacted by PFAS. And this here is an image of Cane Creek Reservoir, and the little dots on the map are land application sites for sewage sludge. And some years ago, Andy went out with a colleague to collect samples. And when you look at these the little streams that run off the fields here and drain into the Cane Creek Reservoir, the PFOA and PFAS concentrations in these water samples were very high, right? So this is runoff from land-applied sewage sludge. and different tributaries, also very high levels. You move off of that area, you get lower levels, and in the end, you got to non-detect in a stream that's outside of this land application area, right? So there's no reason why Owassa should have PFAS in their water. There's no industry discharging into Cane Creek Reservoir. The only known source are the biosolids in this watershed. Another community that's been impacted is Greensboro, way upstream in the Cape Fear River watershed. Greensboro doesn't even get their water from the Haw River. They get it from a tributary to the side. And when you look at point number 5 here on the top right, that's the drinking water intake to the Mitchell Water Treatment Plant. And the PFAS level at that location was 120 nanograms per liter, so it's above the 70 nanogram per liter health advisory level. And some source tracking back upstream shows the one tributary being basically at very low levels, whereas the other tributary, which is Horsepen Creek that drains the airport, is at 750 nanograms per liter there, right? So there's yet another source. So we've already identified many different sources now, right? An industrial source, land-applied sludge, an airport where it's most likely firefighting training activity related. So this is not a simple problem to manage. And as was mentioned already before, there's yet another input into the environment, the impacts from the air emissions, again, from the Chemours plant. And I just put this table up. Don't worry about reading everything on it. The main point is there are many, many different PFAS compounds that are being emitted into the air. And based on process model estimates, about 90,000 pounds of PFAS were emitted into the air in 2016 at that location. And as we know from some of the stack sampling, these are probably underestimates of what was really emitted into the air. And when you look at the DAQ and DEQ activities surrounding the Chemours site here, some rainwater samples were collected to show that wet deposition is an important source of PFAS onto the soil in this community. You can see that the Gen X concentrations here are elevated in the rainwater, even many miles away from the plant. So in this particular rain event, the highest Gen X concentration in rain was 810 nanograms per liter. This was collected in February, at the end of February and early March of this year. And so imagine, this plant has been emitting these compounds for decades. It's been raining onto the soil for that same amount of time. And so there's been now plenty of time for this precipitation to also migrate into the subsurface, and as a result, private drinking water wells are impacted by these emissions. And so you can see here land plots where the private wells were sampled by DEQ, and in red are the wells where the Gen X level is above 140 nanograms per liter, which is our health goal here in North Carolina for Gen X. And yellow is any detectable Gen X, and green would be non-detect, meaning less than 5 or 10 nanograms per liter, depending on the lab. So about 1,000 wells have been analyzed around the site, maybe even more by now. The highest concentration of Gen X in these wells is 4,000 nanograms per liter. So we're also interested in fingerprinting PFAS. So we've taken water samples in areas where wastewater was input into the surface water. And then we also looked at samples that were not impacted by the wastewater discharges from the Chemours facility. And so you can see here by these pie charts, just by looking at the colors, there's unique fingerprints in the water samples that were impacted by the wastewater, which you see on the right-hand side of the slide. There's a big turquoise color on that pie chart. That's PFMOAA. That's not such a big player in the samples that were more impacted by the air emissions, where GenX is actually the major player. Based on all the data that I've seen so far, GenX is somewhere between about 1.25 of the total PFAS that we can analyze for at the moment in the water samples that were impacted by air. And so, then there are lots of questions in the community that lives around the Chemours plant. It's not just that their well water got contaminated, but this rural area, people have their gardens, people fish, people hunt, and people have bees, and so there's all these questions now. Is it okay to eat my tomatoes? Is it okay to eat the fish I catch? And so there's a lot of need here to further identify this. So there's been one data point that GenX was found in honey, I think at 2,000 nanograms per liter, and DEQ has collected some fish and found GenX in sunfish, for example. So the last piece of this presentation is about treatment and the impacts on drinking water providers, what treatment technologies work. And so, the Cape Fear Public Utilities Authority has decided to go with granular activated carbon as their treatment technology for PFAS removal. And as you can see in this figure, activated carbon works to remove PFAS, but only for a certain amount of time. So I heard earlier some sort of feedback on, activated carbon works, and it certainly does. And the question is, how frequently do you have to replace it to keep the PFAS levels down? And what I'm showing here, these are actually pilot data I pirated from the CFPUA website. The thing that I want to point out here, and which is what Chris also showed earlier, is that as the chain length of the PFAS compound gets shorter, it's more difficult to remove from the water. So GenX is the curve that's most to the left here. It's the first of these groups of the group of 5 compounds that I'm showing here that's breaking through. It breaks through before the hexanoic acid. So the shorter the PFAS gets, the more difficult it is to remove by activated carbon absorption. When you look at the impact of activated carbon addition on during drinking water treatment, here this is an example from Pittsburgh. This is a sample again collected by the river keepers. We're comparing here the Haw River and then the Pittsburgh drinking water, and you can see that the PFAS levels in the Pittsburgh drinking water are lower than what they are in the river. That is a result of the addition of powdered activated carbon in the plant. And as the chain length of the PFAS increases, you see higher removal of the PFAS. So, they're primarily trying to right now meet the health goal for PFOA and PFOS, which was exceeded in the raw water, but not in the finished drinking water. But when you look at the totality of the PFAS exposure in this water, it's still quite high. Now, another utility that's pursuing a treatment upgrade is Brunswick County with their Northwest treatment plant. That's mostly a conventional water treatment plant. And their plan is to basically go to a reverse osmosis plant. And what I'm showing here in blue are the PFAS concentrations I showed you earlier in the source water. And then in red would be the concentration of PFAS in the RO-treated water, but you don't see any red on this graph because they all got removed. And then in the green is the PFAS levels in the concentrate. And so RO for sure is very effective in removing PFAS, and then the question is the management of that concentrate stream. We can discuss that a little bit more if you want to ask questions about that. Now, for the private well community, there are questions also, how can we get cleaner water? And so right now there's a pilot study going on to evaluate whole house filters. And so these are fairly large activated carbon filters, 200 pounds of activated carbon in each canister. You see those big blue canister that are sitting on the floor there in this shed. Two of these filters in series, and so these filters should actually last for quite a while. However, at one of the test locations, one of the ether compounds started to break through the first filter after about 4,000 gallons of water were used. So that study is ongoing to evaluate how long these filters will last, how effective they are for the range of ether compounds that are present in those private wells. We've also worked with residents in New Hanover and Brunswick counties. There are lots of questions, right? CFPUA decided to go with granular activated carbon, but you don't get a granular activated carbon plant tomorrow. It'll take a year or more to design and build this plant, right? The same with the RO plant down in Brunswick County. So in the meantime, residents have a lot of questions about, well, there's still PFAS in my water. How can we get it out, at least the water that we drink? So we did a small study working with residents and evaluating different types of filters. And the main message that I give people is, if you want a filter that's reliable and that you don't have to babysit too much, these under-sink reverse osmosis filters do a nice job in removing these compounds from the tap water. And that's illustrated here. So, there are also legislators here in the room, so I think there's always a big question about economic impacts. So I wanted to just show some dollar figures there so that everybody gets a sense of what these impacts are. So Brunswick County, to install this new RO plant, that's a $99 million investment. To run this new RO plant is $2.9 million a year. For CFPUA, just adding the activated carbon filters to their plant is an additional $46 million investment and about a similar operating cost per year. The town of Pittsboro started feeding powdered activated carbon to maintain PFOA and PFAS levels below 70 nanograms per liter. City of Greensboro temporarily actually stopped using the Mitchell water treatment plant because the levels were elevated at that plant. They have a lot of redundancy in their system, so they purchased water from a neighboring treatment facility to make up for the loss of that capacity. And then Cary Apex and Fayetteville, they're both evaluating treatment options to manage PFAS and other emerging contaminants in their water. So that leaves me with this final thought. Treatment options for PFAS removal are expensive, so source control should be the highest priority. So it's important that we really look at NPDES discharges. We look at industrial pretreatment programs across the state. We test biosolids before we put them on land, and that we manage runoff from firefighting and firefighting training activities. So with that, thank you very much.
Sorry. Do you have any questions for Professor Knopen? Oh, sorry.
Well, thank you for that information. I want to ask you a couple of questions about operational things concerning water plants. GAC is usually regenerated in most plants. They take it out and take the pollutants out. And are you able to do that? The first question is, are you able to do that with these pollutants? Can you regenerate it and reuse that GAC, or do you have to replace it? And then the second question on RO systems, the waste stream from that is pretty nasty. And so you remove the material with the RO. Typically that's for saline systems. They discharge it back under an MPDES permit. So concerns about those two things in terms of managing a water system on a long-term basis.
Yeah, those are both very good questions. So the activated carbon related question, that is still somewhat under investigation. So one of the activated carbon manufacturers has done some studies. They reactivated PFAS-loaded activated carbon thermally. Then they did a leaching study after the reactivation of that carbon, and that carbon did not leach the compounds that they were looking for. Now, that doesn't prove that there's not other stuff that we formed during that thermal reactivation that we're still missing. So, there was a study done in Japan that looked at the mineralization of PFAS during thermal reactivation, and they did show that the vast majority of the PFAS were mineralized during reactivation, but it wasn't 100%. So EPA is working on that question also. So you have to stay tuned a little bit there. In terms of the RO, that's also a very interesting question, right? So one thing is, with the current mode of operation, the PFAS that are in the river, migrate through the distribution system, through the sewer collection system, and go back out into the river. So in total, in the terms of total mass flow, there wouldn't be really anything different with the RO, but the RO is more concentrated. So in the vicinity of the discharge location, you have elevated levels, and so that is a question that also needs to be carefully considered. And it may actually be the salts in the water or something else that may be the bigger issue compared to the PFAS that are in the water. In fact, the PFAS levels of the legacy PFAS that were in the RO concentrate in Brunswick County were lower than the PFAS levels in the Pittsburgh drinking water.
Detlef, that was really useful. A lot of great information in there. And honestly, my question is more like, how can you guys start communicating now to the different communities that may not be aware of, like Burlington putting their biosolids on the aquifer? I mean, somebody needs to talk to them and say, look, we need to have a different plan because you're contaminating however many thousands of people with your biosolids. I'm hoping that that's something that can really start to happen over the next year, is that all of this amazingly useful information can be communicated to those communities so that this won't continue to happen, and you won't need as many treatment facilities and dramatic things to happen, very expensive things.
Yeah, I think it's an excellent comment. So as part of the PFAS network, there is a communication team, and I think in my perfect world, this goes back to Matthias's talk also from this morning, we need, collaboration among academics, DEQ, local officials, industries to tackle this problem. I don't think we can continue the way we've been doing things.
Yeah, thanks for the update, Dr. Knappe. Over here.
Hey, Manny.
I know if I stand up, it's not much better either, but recognizing that it's been difficult to safely get out onto the river lately, are there any plans to do sampling post-Hurricane Florence, especially knowing that a good source of the load now is a non-point source runoff?
Yeah, so we're doing some of that. The Policy Collaboratory actually funded several researchers to do some post-Florence sampling, including Lee here also and my lab. And so the idea is we've already gone out and collected samples around the Chemours plant, and we are working with CFPUA to collect daily samples there. So we'll have a sense of what the impact of the storm is and look at mass flows of these compounds also. Now my suspicion is there's going to be a lot of dilution in this case, but you know, we won't know unless we look. And so I'm also very grateful for the residents that live near the Chemours facility for helping us out. We had parked some coolers with sampling bottles in their homes, and they came in handy right now.
Very nice
Bart?
talk. So when I think about biosolids, then if I'm correct, I'm thinking about municipal wastewater. So that would be a biomarker of human exposure to PFAS from inhalation, ingestion, and dermal exposure. Isn't that correct?
It may be in a community where there are no big industrial uses, but I think what we see here in North Carolina is that the majority of the input of these industrial contaminants are derived from industrial activities. So you know, there's a few communities where a lot of stuff comes into the river, and then it's all the rest.
In the municipal wastewater.
Mm-hmm.
Okay, so I have to move on now for the sake of the schedule, but please, Matt, we're going to have a break after the next section. So if you have more specific questions for Professor Knapper, I please encourage you to do that. Can you guys hear me on this mic? Okay, thanks. So I'm going to move on now to a policy discussion. We have a couple of state representatives and state senators here. This panel discussion will be led by Dr. Jeff Warren from the North Carolina Policy Collaboratory. So Dr. Warren, I'll just give a brief introduction of him. He's the research director of the North Carolina Policy Collaboratory. He's formally trained as a marine geologist, and he received his PhD from the University of North Carolina at Chapel Hill. He has spent more than 14 years in the state level science policy positions. He's worked as a coastal hazards policy specialist for the North Carolina Division of Coastal Management and as a science advisor for the North Carolina State President Pro Temp. So with that, I'll let Dr. Warren take over. Thank you.
Thank you. I was so compelled to change the name of my presentation to Food and Beverage Purchased with Non-State Funds. Thanks for hanging around this afternoon, everyone. My name is Jeff Warren. I'm going to give you a really brief run-through of what the legislation said for the PFAS network study, and then we'll bring up our 4 legislators for the panel. And I'm going to try and go through this very quickly so we can spend the majority of the time with legislative Q&A and some public Q&A. So in June, in the Appropriations Act, there was a provision in Section 13.1 that actually created this study mandate. I'm not going to go through every word in the legislation. I'm just going to hit some high points of it. The first one was pretty much some finding statements that North Carolina should rely on its academic institutions for input on complex issues like this. The second section really was the scope of water sampling and the requirements that every surface water, public water intake would be sampled at least once, and that every municipality with at least one public water well would be sampled. And so that was to be defined by the Department of Environmental Quality. We've already talked with them, and we have a sampling universe of 348 individual discrete sites that will have to be sampled at least once. I believe our hope is to get it at least twice. But it's the Smokey and the Bandit analogy. We got a long way to go and a short time to get there. So this just gives you a sample spatially of what we're talking about. The orange dots are surface water intakes. The aqua dots are groundwater well systems. These are public water systems. And the color map, you can see that most of our groundwater systems are out on the coast, which you would expect in the aquifers of the Piedmont, of the coastal plain. And this one just shifts the color block to look at where the majority of our communities are with well systems. And you can see, as you would expect, the majority of surface water users are in the western and the Piedmont. We've got reporting requirements, and magically we are pulling together our first progress report that is due to the General Assembly on Monday. So we've been very busy organizationally and getting the money out the door, so working with the budget offices across our different campuses in our system. The appropriation was $5 million. That was a non-recurring amount, so it's one-time money, but it's non-reverting money, so that gets to be held for the duration of the 18-month project and does not expire at the end of next fiscal year. So that was key to give us a little more time to use this money. And then we were mandated and suggested that we leverage the research dollars using our challenge grant and look for additional related research. So without going into a lot of detail, we've already used our challenge grant from a separate funding line from the General Assembly 2 years ago. We've already drawn down about $350,000 of additional money to go towards PFAS-related research. I think I've got another $150,000 in the pipeline to the budget office, and some early intel is telling me that I've got a couple more grants about to come online that we could match up to about $500,000. So in addition to the General Assembly's $5 million direct appropriation, we're going to be supplementing with between $500,000 and $1 million through our challenge grant. So it's a very nice investment. Section K was state agency support that if the EPA could no longer assist by running the analyses, that DEQ, that the state university system would work with DEQ and provide those analyses for them. And then there were some other research directives, and you'll hear a lot about this in the lightning talks that follow. But in addition to taking the baseline sampling from all the public water supplies, do some predictive modeling of private well contamination and look at some risk assessments. Do some performance testing of mitigation and removal technologies, look at air emissions and atmospheric deposition, and evaluate other research opportunities. So this was this was part of the scope of work given to us by the General Assembly. And this was the team assigned by the General Assembly, and the collaboratory will manage this, but you can see we've got a large part of our UNC system in here, and we've also got Duke University as a partner as well. So we are off and running, and you will hear the details from these co-PIs later. But now I'd like to bring up my panel. So come on up, senators and representatives. We are delighted to have 4 members of the State General Assembly with us today. Coming up right here in front of me, Representative Pricey Harrison, right next door from Guilford County. Coming up right behind her is Senator Floyd McKissick. He is a state senator, Durham and Granville County. Representative John Soka is from Cumberland County, and Senator Michael Lee from New Hanover County. So thank you all for joining us. And I think I'll jump around on these questions that I've already provided you in advance. I think I kind of like to get to the directed questions regionally. Senator Lee, you represent New Hanover County, which is kind of ground zero, one of the ground zeros for Gen X. Your constituents get most of their drinking water from the Cape Fear River. And certainly after Dr. Knappe and the EPA and all their colleagues, we know that Cape Fear has a signature of Gen X. You sponsored the Water Safety Act, and portions of that eventually made it into the budget that created the PFAS network. So I guess the question is, okay, what are you hearing from your public officials and your citizens and your constituents regarding how they think the state is responding or should be responding to the Gen X issue?
I think, hear me? As is evidenced by today, it's a very complicated issue. So I think a lot of our constituents are just really, really concerned. And looking at treatment technologies is great. Trying to cut off the source or turn off the spigot, to coin a term from Dr. Mead at UNCW, I think is important. But I think there's just a lot of concern around all the unknowns. And I think what we're doing, or what we've done as far as that first step in trying to identify what the scope is through the monitoring system, I think has helped somewhat, but most folks really don't want to wait on us finding the scope. They want a solution. They want it tomorrow. And as evidenced again by this conference, it's hard to find an absolute solution tomorrow. Even if you turn off the spigot, you've got the bioaccumulation, and you've got the other issues that are going on. So what we've tried to do is have kind of a twofold, not just in the legislation, but in when we are out there talk about, let's identify the scope. Let's also work at treatment technologies because of the bioaccumulation issues and the fact that it's just not one point source for the PFAS that's in our state, which is evidenced by Dr. Canapi's presentation because for the communities that are not downstream of the Cape Fear. So it's a complicated issue. Everyone's really nervous about it, and they continue to be. And they will not stop being nervous about it until there is a solution, whether it's through filtration technologies or better understanding what the impacts of the 5,000 some odd compounds that make up the family.
Okay, Representative Harrison, you are not too far from here in Guilford County. Detlef talked a little bit about the AAAF, the PFAS chemicals that have been found in your all's water supply. Heavily related to firefighting foam and other chemicals. What are your thoughts on what the government, federal, state, and/or local, and/or industry, and/or academia should be doing to address some of these not so well-known unregulated chemicals?
I have a lot of thoughts on this. I'll try and keep it brief. Personally, I subscribe to the precautionary principle. I don't think we ought to be putting anything that we don't know is safe into our air or our water, and I feel quite strongly about that. And but sort of in addition to that, I feel like what's happening to the EPA right now is troubling. I think that we need to make sure that they are shored up with the funding and the staffing that they need. I just read today that the scientific advisor was let go, and that's a very important position. And then the head of the Office for Children's Health was let go and or put on administrative leave, and we're not sure why. But I have spent a lot of time working on toxics management at the state level, and with not a lot of success, obviously. But it's clear to me that we aren't getting a lot of that the federal government, TSCA, is broken, and even though it was reformed a couple of years ago, it's still not as strong as it needs to be. So I think we need more teeth in TSCA to make sure that we at least have a federal floor for a minimum amount of, regulation where there's a lot more money and expertise than we have here at the state level. At the state level, I think we need to adequately fund our agencies, and I would add DHHS to that. We have one state toxicologist, and I think that's a real problem given the exposure to these toxic chemicals and their public health impacts. I believe that we need to unhandcuff the agencies to be able to do the job that they need to do to regulate, to protect our citizens in North Carolina. And that's lately we've been sort of rolling back some water quality protections. I think that's a problem, and some air quality protections, and this Hardison Amendment that limits an agency's ability to regulate if it exceeds a federal standard. I think that we need to probably get rid of that. I think that specifically relating to the issue about the firefighter foam, the state of Washington has passed legislation because that was a problem in their state. And the state of Washington is a good model for managing toxics at the state level. And they sort of ban the use of the toxic firefighting foam for practicing. There's no reason the firemen ought to be practicing with the toxic material. They can find a substitute. But other parts of the legislation would find for an easier way for collecting and a safe way to collect and dispose of it, best practices for entities that are going to use this foam. There are models out there in other states, such as Vermont and Maine and Massachusetts, that have been working on these toxics for longer than we have. And I believe we don't have to reinvent the wheel, but I think that our state could push forward with a new sort of green chemical policy where we really are avoiding using these toxic chemicals unless we know they're absolutely safe. So thank you.
Okay. Thank you, Representative. And right next door, Representative Soka, Cumberland County, Fayetteville area. You've got a lot of rural constituents that are on water wells instead of surface water. What are you hearing from your constituents and your public officials? What are their concerns when it comes to water wells?
Well, the concerns, as you might imagine, are very severe. As a matter of fact, not in a kidding manner, but in all serious manner, this is the first meeting in which I've been at talking about Gen X contamination groundwater, where there haven't been several hundred people, and most of them not very happy. Not happy enough to disrupt the meeting, not happy enough to get some of them escorted out by sheriff's deputies. And it's not because they're bad people, it's because they're scared. It's because they've lived in these areas, sometimes families, for generations, and they've related to me, a number of them, a series of medical issues which may or may not be related to this. They don't know. I don't know. Their doctors don't know. Nobody knows. So it's really the uncertainty of what's happening to them in their homes, of what's in their water, and what's it done to generations that have already passed away. So it's almost like it's a breach of trust in their mind that the one thing you should be able to count on is clean water when you have your own well coming up. From a public policy perspective, when I talk to them, the problem with this issue, as in with many issues, is how are we supposed to look into the future and come up with the right public policy? That's something we grapple with, I grapple with at least on a daily basis, whether it's with this, whether it's with energy, tax policy, or whatever. And this is even more complicated because we have a collection here before us of some of the best minds in the country and the world right now who can tell us the sampling and the data, and we can see the charts, which is all very useful, but how do we fix it? And that's what folks look to me and the rest of the representatives and senators here for, and how to fix it. So what is the best way? I don't know that right now. I think that just in the fact that I got here for lunch and heard the previous presentation, that's helped me know more about it. What we need, I think, is exactly where we're going in the state with the direction we have with the NC Policy Collaboratory. I believe that there's a difference between basic research and enforcing regulations. Our Department of Environmental Quality, their job is to enforce regulations. They have to have the right regulations to enforce. We have to know the right scientific standards on that. What I am very happy to see is the attendance at this meeting here today and the presentations that are going on and the plan going forward to figure out how widespread the problem is. I think we know a little bit about that. How pervasive it is into health effects, which from my understanding, every article I read has the same paragraph, and it's kind of a disclaimer so nobody can be blamed on it. It says, well, it has been shown to cause cancer in some animal studies, but we don't know its effect on humans. We need to know its effect on humans, for sure. I mean, I'd like to see somebody take that on so we can know, because if it doesn't have an effect on humans that's devastating, like people assume it does, then we need to know that. So maybe that's a long question to a seemingly simple question, or a long answer to a seemingly simple question, but to sum up, basically my constituents want action. They want us to take action. And it's very difficult to look into the future to determine exactly what that action is. I think we're on the right path here with what we passed in the budget. I think some of the other things that are ongoing now.
Okay. Thank you. Thank you, Representative Soka. Senator McKissick, you're kind of sandwiched in between the coast and Representative Harrison's district. So, you know, the Jordan being in some ways the headwaters of the Cape Fear. What flows into Jordan flows into Cape Fear. So if we've got firefighting foam coming from Guilford County, it's coming here. But your constituents not only drink out of Jordan Lake, but also Falls Lake. What are you hearing from your public officials and your constituents? I know that Kerry, I believe, did some sampling and did not find Gen X per se in Jordan. But we certainly know anecdotally that there probably are multiple PFAS compounds in there that will be looked at as part of this study. So what are you hearing? What do you think the path forward is?
Well, the challenging thing is knowing exactly what you're testing for. And I mean, you can go out and do a broad variety of testing, and I think if we could really bring together the best and the brightest minds and really understand what these emerging compounds are, understand what it is we're testing for, and having a methodology for doing effectively, I think it would help dramatically. I think right now we're not using our resources and deploying them the most strategic way that we can. Now, in terms of what we can do here in North Carolina that would help that, I know the group you lead, the collaboratory, is certainly making right steps and moving in the right direction. At the same time, we have our division of environmental management, which is in part, working on this regulatory piece. If we could get the two pieces working together collaboratively, more strategically, I think it would help us really define how we can best get our arms around this problem and address it in a more comprehensive way. I can't sit here today and tell you that I know what that path would likely be. But when I look at the presentation that was by the professor earlier and looking at the work that they're doing, and I know I had a chance to meet with him yesterday evening and discuss some of his work, and it's very impressive. I understand that we have a long ways to go in terms of knowing really the best road and the best method for getting there. So, I mean, I know we're sitting here talking about Jordan Lake, because it's in my district, Falls Lake, but it's in my district. But you know where I'm hearing the most concern? Granville County. And it's not about Jordan Lake or Falls Lake, it's about other water supplies that they're utilizing because they've been designated as a cancer hotspot. Now, is that on anybody's radar screen? Nobody but the folks that were there in the Department of Health and Human Services, who we've brought in to try to understand what's going on, and people who ran Camp Butner, which was a military camp, going back 50 years ago, which had one of the highest concentrations of military establishments in our country. Now, what's over there in that ground at Camp Butner? They've had water quality studies done in that area, which suggest that there are serious issues and problems with the water. Is that what's leading to this cancer hotspot? I'm not going to tell you that it is, because there's not enough data to suggest that that's true. What we do know is that the data suggests that there's a cancer hotspot that begins there and moves toward Henderson area over in Vance County. Now, can we do more research and identify what that is? The strongest voices I hear in my district not just includes all of Durham in terms of the issues that you see in this urban core, but a rural district that runs from Virginia all the way down to North Raleigh, right over there in Creedmoor and Butner. And you don't hear a lot about it. It's not in the news every day. It's not on the screen like Gen X, but it's real, and it's something that perhaps needs to be on our radar screen as well in terms of what we're looking at, because the people there believe it's water related.
Right, that's very good points, thank you. I want to pivot away from some of the pre-prepared questions I have, because we've got a room full of experts and interested stakeholders, and I would like to devote a lot of time. Before we go to the Q&A in the crowd, would any of the four of you like to do follow-up comments on any of the comments that the other legislators have said? Because there's been a lot of interesting information put out there.
So,
So,
I mean, from the speaker this morning talking about the Rhine River and how the testing is working with targeted and non-targeted, the original bill that we filed really was for all emerging compounds. It wasn't limited to the PFAS family. And I think that a lot of times with policy, especially when you're talking about environmental policy and you're dealing with very complicated issues, that we take these kind of one step at a time. We set up this infrastructure, this robust mechanism by which we can test all over our state, and then we can expand that beyond maybe just the PFAS family. But what I have to say is one of the things that I'd really be interested in as a policymaker is really just in anything I know I've stolen from Dr. Knappe or Dr. Ferguson or someone else in this room. I'd really like to help from a public policy perspective in funding research to take this beyond the wet lab experience. What do we need from an IT infrastructure, data analytics, you heard from the Rhine River process that they relied very heavily on a computer science solution to run the algorithms to assist with the massive amounts of data that you're going to acquire, not just dealing with what you're looking for under targeted, but when you're looking at the non-targeted, trying to find out compounds you don't even know exist yet, that don't have a name. So those are the kinds of things that I think we really need to be looking at together. There are people from EPA, NIH, state government, a gentleman here is in uniform, for which I can't remember the acronym. I mean, there's a lot of people in this room working together on this. And if we can start working on some of those solutions together, working on real modeling, I know we're relying upon toxicology, but really look at modeling, whether it's through bioscience or through an IT solution. That's when we're really going to be able to make some real headway, because when you're talking about over 5,000 compounds within just one family, I'm not sure how we get a handle on this until we can have some real sophisticated and reliable modeling that goes on with respect to toxicology and health impacts.
Representative Harrison, you had some.
Yeah, real quickly, and I, just because I have really strong feelings about this, I appreciate Dr. Knappy's presentation and his point that it's a lot cheaper to prevent this stuff from getting into our water and our air and our land than it is to clean up, and we don't even know that we can clean it up. And I do think there are some known health impacts. We do know this is a known carcinogen and a neurotoxicant, and I think that we have to protect the citizens' public health. So I feel like in the absence of any federal leadership, the state needs to step in. And it's difficult because we don't have the resources or the technical expertise, but we've got great university resources, as has been evidenced today, although I missed this morning's presentation. But I'm very concerned about the public health impacts. I'm very concerned about the length of time our citizens in North Carolina have been exposed to this. We don't know I want to give the speaker a lot of credit for putting together the committee that's been looking into this issue for several months, nearly a year, I guess, and they've really had an in-depth analysis I have never experienced on any legislative committee before. So I appreciate, and we're hearing this. What we know is that we don't know what we don't know, and the fact that there are 3,000 to 10,000 of these chemicals in just the PFAS family, that we've got flame retardants we're being exposed to. You tweak a molecule and it's maybe a different chemical. If you ban one chemical, it still has the same impact, health impact. So I think that it's a fraught issue that deserves a lot of attention, and I appreciate the fact that the legislature is taking this on. I hope that we get a little bit more aggressive about protecting our citizens. Thanks.
Thank you, Representative. Senator McKissick, Representative Soga. Okay, I'd like to go to the crowd. I know Mark Striner's got a question, so we'll start with him. You can ask it to one legislature or any legislature. No, you can ask them. one or all.
All right, it'll be to all. So thank you for coming first. I know I stood before the legislature 6 months ago. I remember Representative Harrison. I remember your face. I talked about Cadillacs and Chevys and Teslas and mass spectrometry. And our DEQ is understaffed, and they have not the best equipment. We have very good equipment, and they need the same equipment to do the job that we do. And my understanding is that they're not getting the equipment that they really need to do the job. They're getting a triple quad, and I'm wondering if you can comment on the why.
Pardon my candor. I believe that the House supported the mass spectrometer, the Cadillac model that you mentioned, and actually there was one available for the same price as what was ultimately appropriated, which was very frustrating. But as I understand, there was some input from industry, and this is the rumor anyway, that maybe they didn't want the mass spectrometer that would have revealed all the chemicals that are in the emerging contaminants that we don't know about. So that's what was reported in the news. Somebody else might have it.
Well, I would simply say that DEQ needs the type of equipment that's necessary. If they need the Cadillac mass spectrometer, which they've been advocating for, as well as the support staff, as well as the resources, they should have it. We shouldn't have to rely upon the universities to do it. We shouldn't have to rely upon the private sector. It's great if they can supplement, but suppose they're out there already working at capacity. We should have that in-house capacity to do it. And I think we should dedicate the resources for that. And I think if we fall short of that, then we're shortchanging ourselves. So, that's where I've been all along, and I hope that we can get the point where that's possible to do so. I think to do anything less than that is to shortchange our technical capacity and ability to provide appropriate analysis and identify those types of contaminants that really should be appropriately regulated and the amount of regulation they should receive.
I'd just like to jump in here. I've got 2 points that may seem separate, but they're interrelated. The first is, and it goes back to what I said earlier in my comments, was I believe there's a difference between research and enforcing regulation. It is not my personal desire, and I only speak for myself alone, it's not my desire to turn DEQ into a mini version of the EPA with its own research staff to do the research that many of you are doing here in private universities. I don't feel that that's the job of our Department of Environmental Quality at the state level to take on issues which, in my opinion, should be handled at the federal level by the EPA with these 50,000 emerging contaminants that we've known about for decades but haven't done anything about. So we could do that, and we could spend a whole lot of money mimicking the structure of the EPA, but I don't think that's the right policy move. I think what we're doing right now is a better policy move. And the second thing I would say is that oftentimes in legislation, whether it's this legislation or any legislation, you have 120 members in the House, you have 50 members in the Senate, and this is kind of like schoolhouse rock stuff, but you know, 5th grade math, 50% plus 1, you have to have enough votes to get something. Sometimes things seem like they're not well thought out, and sometimes that's a result of negotiations between chambers, within a chamber, between parties, within the same party. There's all these dynamics going on, and I don't know that I can really respond any better than that sometimes things that appear not to make as much sense as another option wind up in legislation and getting passed.
Senator Lee?
And the first step, I think in January, the House passed a bill with equipment and staffing. And the reason that didn't get through in January is because we were looking kind of, if the EPA were to stop, they would not have had enough time to get the equipment and the staffing up to speed. So we kind of had the backstop as being the university system. When we came back for the long-term funding mechanism, which ultimately rolled into the budget bill, as Representative Soka mentioned, you know, if you were to look at the bill that we co-sponsored, one in the House and one in the Senate, it looks different than what ended up in the budget bill, and it's that legislative process. Although there was significant funding, additional funding for staff and other things to DEQ, but you know, the idea is not unlike the Rhine River example, and where you've got this ongoing monitoring that occurs and reporting, and the reporting is all public. And you heard the speaker from this morning explain how the reporting is directed to the governmental authorities for enforcement. So, you know, this is a partnership that we've got right now with the leading researchers in the world in this room, and a lot of y'all are here in North Carolina. We've got the EPA office we've got in the Triangle and the resources that y'all have. This is something that we wanted to address now, that we wanted to jump on and really get this process going so that we could, I mean, we're only a year from, it didn't take very long to get this up to speed and running because of the way that we were able to accomplish it. The research institutions, all of y'all in this room are already getting grants from NIH and EPA and other federal government institutions. So it makes sense that the state also take part in this, especially since we in North Carolina are being impacted by the PFAS family of compounds. So I mean, that's kind of the engine that we've started here to really jumpstart where we want to get to.
All right, additional questions? No, Jackie, you're right here in front of me.
Yeah, so I wanted to congratulate the legislature for supporting this idea of establishing this statewide monitoring network and looking for things that aren't currently regulated. I think that really puts North Carolina ahead of so many other places. But I've thought for a long time that the way that drinking water quality is regulated in the United States doesn't make any sense. It's like whack-a-mole. You know, they're regulating contaminants one at a time. It takes many years to get one regulation through, and by the time that one's through, there's, you know, maybe dozens or hundreds of more contaminants that you weren't even thinking about when that one went through. And many of the contaminants that are currently regulated barely occur in water. They were sort of arbitrarily added to a list of things to be regulated. under the original Safe Drinking Water Act. And so, to me, what would make much more sense is another approach entirely that goes after groups of contaminants and requires the most advanced treatment processes and has the support to help local governments be able to afford those kinds of treatment processes that they need to implement such an approach. And I'm just wondering if, from your position, you have any thoughts about the feasibility of really overhauling how we regulate drinking water in the United States.
Wow. That's a question. If anybody wants to address the United States, you're welcome to. Yeah, I mean, so the way, from my perspective, and I know you and I have talked, we in New Hanover County, and you heard Dr. Knappe, I think, mention, we've got one of the most sophisticated water treatment facilities in the state and maybe the nation. When I met with some folks over at the Gilling School, I learned that the infrastructure around the state is nowhere near where we are in New Hanover County. So in many ways, we're lucky, even though we've got this PFAS issue that we're dealing with and we're very concerned about. So I do think that as a state, we are going to, once we kind of get our arms around the scope, and we are looking at the family as opposed to Gen X specifically, and a lot of folks in my area are only concerned about Gen X, not quite realizing that it's just one in the family. So that's why the legislation really kind of captured the family. And then hopefully we've got this infrastructure in place if we move to other emerging compounds. But I think what we're going to have to deal with in the state of North Carolina is maybe not on the regulatory side, because that's kind of been captured by the federal government, but what we really need to be looking at is the infrastructure for our citizens, and that is going to take a statewide approach, because I do a lot of education related policy, and 75% of our counties are low wealth, receive low wealth funding. So they're not going to be able to establish a lot of these very sophisticated treatment facilities that cost, $50, $100 million, depending on what the volume is they're trying to treat at any given point. So we are going to have to be working on some statewide program for infrastructure.
Okay. Just real quick.
Absolutely, follow up.
On the EPA issue, and Dr. Schreiner probably knows a lot more about this, but having looked at this issue for a long time, so TSCA was passed in 1976, 60,000 chemicals were grandfathered in. Since then, 20,000 have been introduced. The burden of proof forever was on the EPA to prove that it wasn't safe. And maybe 200 chemicals have been regulated by the EPA. And as you point out, you sort of move a molecule or something, and it's in the same family, but the same sort of public health impact. So the TSCA reform that was passed 2 years ago was inadequate. It was a compromise, and it probably didn't do enough to address its family and chemical issues. So that it's not something we're going to be able to deal with at the state level. I think, as I said, in the absence of federal oversight, we need to do something, but we really need some help at the federal level on this. And and there's another piece of this we haven't really talked about. It's very centrally just touched on it is the cost to the ratepayers. We're looking at a super expensive upgrade in our water treatment plant in Greensboro. They're looking, you saw the figures for Brunswick County and Cape Fear, and from my perspective, the ratepayer ought not to be paying that. It's the polluter that should be paying that, and that ought to be clear in whatever legislation that gets passed. But thank you for your question.
And I'll simply say this. With the current administration in Washington and the administrator they have there at EPA, and with Congress in the hands that it is in, and a lack of belief in basic science, I have absolutely zero confidence that there'll be federal leadership in this area in the near term.
Next question.
So this is a follow-up on those statements. I'm just wondering whether the legislature has considered on a bipartisan basis, and maybe banding together with other states that are struggling with this same issue, in calling for the leadership that you're looking for from EPA. Is there any effort? Have you all done anything in a letter together? Have you considered kind of a state outcry?
Well, I didn't talk on the last one, but let me start on this one. I will tell you that I personally and other members in the region, and I have been communicating with our U.S. congressmen, U.S. senators about this, about some of the issues with TSCA that we've been talking about, trying to get the EPA to reform And I would take respectful disagreement with my colleague here, Senator McKissick, on his opinion of the EPA and their abilities to do things. And I will tell you that the congressman and both U.S. senators from North Carolina that I have spoken to many times are taking this very seriously. That's it.
And I'd like to, you know, the one thing that kind of gets lost sometimes here, so I live in Wilmington. I live at the end of the river, and I have 4 children, ages 11 through 18, and my son just went, oldest son went to Chapel Hill. We've been drinking the water for, 20-some years, and our children drink the water, and it's a very personal thing. So while we have reached out to the congressional folks from our state, and while we want to work with others, I mean, I'll just be honest with you, that we want to figure something out as soon as possible. And the only way that we're going to be able to do that, I mean, the federal government, it's great, a lot of stuff they're doing, and they're moving a lot on PFAS and doing lots of other things, but we aren't going to see any real results in any timeline by which anyone would find acceptable in my house, let alone my community. And even then, with this concept of identifying scope and looking at toxicology and trying to find treatment technologies, and is GAC going to work, and how long is it going to take to install, and once it is, if you've got shorter chains, they're going to go through and it may not work. I mean, we in our community, and my wife asked me these questions, we are dealing with this on a daily basis. We are concerned. So there's a lot of great stuff that we talk about from the federal government and regulations and all this other stuff, but for folks in my community and my house, we are trying to figure out as soon as possible what the result is of this exposure over time, whether it's the water, whether it's the fish that we eat, the oysters that we eat, whether it's taking a shower. I mean, we are trying to figure it out by looking to y'all. And as policymakers up here, we don't always agree on the policy, but I think we all agree that we really want to help the folks who are impacted by this, not just within our districts, but within our state. And if we can do that and help other folks at the same time in other states and other places, I think that's great. But we've really got to be focused on us right now.
Thank you. I was going to ask one more question, but we're starting to run up against that time. I wanted to give each of you one last comment to close this out as kind of a closing thought. Maybe a question that you didn't get asked that you wanted to be asked. So maybe we'll just go down the line. I'll start with Representative Harrison.
I don't want to repeat what I said, except that I think it can't be emphasized enough that we can't be putting stuff in our water or air or land that we have some potential negative public health impact, and we know it's a lot cheaper to prevent this than to clean up afterwards, even if, and especially we may not even be able to clean up. So I think it's incumbent on us to do something about limiting our exposure. Hopefully we can get some help at the federal level, and if we can't, we definitely need the state to step in and do what it can, as other states are doing. Thanks.
I'd just like to thank all of you for attending this and doing the work that you're doing, applying for the grants that you're applying for, and my understanding, more of those grants are coming online. Because our jobs as legislators is to take care of the people, not only in our districts, but to look out for the health and welfare of the people of the state of North Carolina. We need your help in doing that. We need your help as soon as possible in figuring out what the best course of action on any number of different potential actions are. None of us individually or collectively are smart enough to know that on ourselves. And we need you to tell us what the science is. We need you, as best as you can, we need you to help point us in the right directions. I'm not asking for a 100% solution. I'm not asking for you to do our job. What I am asking for is your 100% support and your 100% dedication to getting this figured out for this family of chemicals. And hopefully by doing it this well, we'll have a template for the next family of chemicals and so on and so forth, and we go on. We can be a leader in that. We can be. But I am against funding expansion of government. That's one reason I ran for office, because I saw too much of that and it becomes too ineffective. The academic environment that you all work in on a daily basis is unrestricted from politics, for the most part, my understanding, and you can find good solutions, you can do good science, and you can really help us come up with the best solutions for this problem and the other problems down the road. Thank you.
And I'd like to start by really thanking the groups that came together to sponsor this particular conference. I think it's very important to have these type of opportunities to share ideas and for people, the best and brightest, to really assemble to think about things strategically. I think if we could get help at the federal level, that would be outstanding. I would love to see the federal EPA engaged in these issues. When I made my remark earlier about no confidence, part of it was inspired by just an article today in the New York Times talking about the Office of the SAISI Advisor, senior post that was created at Council EPA Administrator on the scientific research underpinning of health, environment, regulations. We're getting ready to get rid of them. It's going to be abolished. That's what gives me concern at the federal level. Can we do things here in North Carolina? Absolutely. I appreciate the leadership team that's coming together here in North Carolina. I think it's possible for our collaboratory, as well as our governmental entity, to work together on issues such as PFAS. There's a role for each. There's a way to come up with a memorandum of understanding. One's going to do part of the work, others going to do part of the work, and we're going to work together on some initiatives as well. Can we collaborate with other states? If other states are willing to commit the types of resources that are necessary, that we can come together in a collegial way with a plan, a strategic plan, and a combined methodology that's cared about what one will do versus the other, wonderful. No need to duplicate resources. But if that can't be done, then here in North Carolina, we have to come up with our answers, the way Senator Lee spoke about. I think that that's the type of approach I think is essential and that is necessary. So I think we're making the right steps. I think we're moving in the right direction. I do have faith and optimism that here in North Carolina, we can establish kind of a best case example of how we can approach dealing with PFAS. I mean, I think that is clearly something that we're capable of doing, and something that I hope that we will be able to look at. People can look at us in terms of a leadership and how we're addressing it. But, you know, North Carolina is the one that has to fix things right now for our state, our district, and our constituents. We can't wait on the federal government to do what needs to be done, even though I would love to see that occur.
Senator Lee, you've got the last word.
I know the rule was we were supposed to answer a question that someone didn't ask, but I'm going to ask y'all a question, and you don't have to answer it right now, but maybe see me later. Is there something we can do to help? And there are folks in this room that have been great to speak to me. A lot of time, I'm a co-chair of education appropriations, so when I go to a university, people are a little nervous about talking to me, especially about spending money. But the university system has been terrific in speaking to me and trying to help educate me about a lot of these issues and what's going on around the world. Dr. Ferguson at Duke has also been great about that as well outside of the UNC system. But is there something that we can do? Is there something on the data analytics side that we can help with, that we can help connect with another company or research that we can help fund that's tied into this beyond the wet lab? That can crunch the numbers. When I looked at the mass spec report or whatever you call it with the dots all over the screen, and I don't know how you crunch all the data and get it all done without being able to set up some type of data analytics or algorithm to help sift through and prioritize. So my question to y'all is there something we can do to help in the research grant process to help us take another leap forward in this process? And in particular, something that I'm interested in is modeling on the toxicology side, because again, the only way that we're going to be able to really get a handle on this is if we can do effective modeling, because of the very nature, and y'all know this better than I do, of the way the compounds are manufactured and how they can be changed. So those are my questions to y'all, and I hope some of y'all will come see me. Thank you.
Thank you. Representative Harrison, Representative Soka, Senator McKissick, Senator Lee, I'd like to thank you all for your time. Having you here at a scientific conference is a wonderful thing. We need more of it. We need more legislators to take time to get into the labs and into the conference, the lecture halls. And we also need to get more of our academics down to Jones Street. And I promise to try and do that. So let's give our panel a big round of applause. Thank you.
Yeah, we have. All right, we're going to take about a 15-minute break. So we'll actually come back at around 2:50 and start about 5 minutes late. Thank you. If I could ask everybody to take their seats, we're going to go ahead and start the next and final session of the afternoon. All right, well, to sort of close out this afternoon session, what we'd like to do now is introduce to you all the newly established PFAS testing network. And so hopefully you've seen through the afternoon talks and the panel discussion, hopefully you've seen how we've sort of evolved now to the, with the recently passed legislation, the need to establish a network. And so as soon as we got word from the state that we were going to receive funding to start studying PFAS in the state of North Carolina, we first established sort of a project management team led by UNC, and then we also seeked out the active PFAS researchers in the state who are really leading experts, as you've already heard from a few of them today. And so our executive advisory committee is formed by 6 of the institutions across the state that are part of the testing network. So we have Lee Ferguson from Duke, Detlef Kanape from NC State, Jamie DeWitt from ECU, Jackie McDonald Gibson from UNC, Ralph Mead from UNC Wilmington, and May Sun from UNCC, I'm sorry. And so as mandated by the legislation, we assembled research teams that are really in direct response of the scope set out by the legislation. And so what you're going to hear today is from some of the project leads, which are shown here in these gray boxes for the research teams. We have co-leads. So for each team, as you'll see, one of the co-leads is actually an active PFAS researcher. And then for some of the other teams, what we've done is we've brought in some other experts in these areas who we thought could really add to the goals for that particular research team. And in addition to those teams, we have a risk communications team that are sort of being led by Kathleen Gray at UNC, Jane Hoppin at NC State, and Joy Wontrop from Duke. And then we also have a data management team that will help us provide a repository for our data that we collect from all the research teams. And so the idea here was once we've got word of the funding that we were going to receive from the state, myself and the rest of the project management team decided we would solicit proposals for scopes of work. And this occurred in June of this year. And we asked that the teams get together, formulate the teams that they would like, and submit a proposal to us by mid-July. And once we got the proposals, we solicited external reviewers. So these are experts from outside of the state who are very well established in PFAS to provide important feedback and recommendations to us about how the PIs could improve their scopes of work to add to the PFAS network. In addition, we had at least one of our executive advisory committee members to review the proposals as well. And so the reviewer comments for these proposals have been sent back this month. And so now the PIs and their teams are responding carefully to the reviewer comments that we solicited and revising their proposals accordingly to hopefully improve the impact of the research work that they are setting out to do under the network. And so we plan by mid-October, once we receive the revised statements of work, to meet again. Myself and the rest of the project management team are going to meet with the executive advisory committee members to approve and make final recommendations on the 5 research teams' proposals. So what I'd like to do now is we'd like for each of one lead from each of the research teams to give us a sort of a overview of what they're proposing to do over the next 12 to 18 months. And so we're going to ask that everybody, if you have questions on a particular project, please either write it down or keep it for the end. We'd like to actually go through all of the research team's approaches first, and then we'll try to leave plenty of time at the end for your questions so that we have more meaningful interactions with the audience. So first, I'll quickly go through this. Team 1, our first team that we'll have go up is we have the co-leads of Lee Ferguson and Detlef Knappe. Lee Ferguson is a professor, as you already know, here at Duke in civil and environmental engineering, and Professor Knappe, who we've heard from, who's in civil construction and environmental engineering. And they're going to lead a team that will sample public water sources statewide to establish a baseline and monitoring protocol for PFAS. Our second team is our air emissions and atmospheric deposition team, and this is being co-led by Ralph Mead at UNC Wilmington and Barbara Turpin at UNC Chapel Hill. And this team will set out to examine air emissions to understand how air particles will impact water under and on the ground. Our third team that we have for the research is PFAS removal performance testing, and this is being co-led by Professors Cornell and Mason, and they will be testing the performance of different types of technologies in removing PFAS. Our fourth team that we have is being co-led by Professors David Jonero from the NC State and Professor Jackie McDonald Gibson from UNC Chapel Hill, and they will develop predictive models to identify private wells at the greatest risk of PFAS contamination. And finally, as sort of set out in the legislation, there's an opportunity for us in this network to look for other applications or other research opportunities. And so this team decided to really go out and assess the impact of PFAS on public health. And this is being co-led by Professor Jamie DeWitt from ECU and Professor Rebecca Fry from UNC Chapel Hill. So our first lightning talk will be by Lee Ferguson from Duke University.
Thanks, Jason. Right, so I am co-leading Team 1 with Detlef Knappe, who you've already heard from. We also have as a member of this team Dr. Mason from UNCC. So the research questions we are trying to answer in this task are pretty simple. So first of all, what are the concentrations of targeted legacy and emerging PFAS contaminants in North Carolina public drinking water sources, right? So this is one of the mandates of the bill that was passed by the legislature. So to accomplish this, we're going to collect and analyze raw water samples during 2 consecutive quarters of 2018 and 2019. And so we're going to do this at all 191 municipal surface water intakes and all 149 municipal drinking water systems that treat groundwater in North Carolina for PFAS. So as Jeff mentioned, this is somewhere north of 350-ish sampling sites. So we're going to do this twice, and then we're going to repeat this sampling for systems that had detectable PFAS in the first 2 rounds of testing. We're going to repeat that in the 3rd quarter of 2019. So this is going to be a large-scale effort in our laboratories. So now we're also going to look for unanticipated and untargeted PFAS compounds. As you heard today in the morning, and as well as in Detlef's talk earlier, it's not enough just to look for the compounds that we have standards for and that we can quantify. We're going to use a variety of techniques to look for non-targeted PFAS as well, also mandated in the bill. And then importantly, just as Chris Higgins mentioned in his talk, it's not enough just to apply a single tool like mass spectrometry, high-resolution mass spectrometry to assess PFAS contaminants. This is one of the reasons why we brought Mei Sun onto our team. We're going to ask the question, how much of the total organic fluorine in public drinking water sources can be accounted for by our targeted PFAS quantitation? So we're going to use absorbable organic fluorine analysis of these water samples to get at that. So why is this research needed? This is like the easiest slide to answer on the entire day because of all, so the answer to this, why is this research needed? Because of all the talks you've already heard, okay? And so specifically, obviously we all know, and we've heard a lot about Gen X and the related compounds that are in the Cape Fear, that have been found in the Cape Fear from the Chemours plant, but also importantly, as you heard in numerous presentations, it's not just a Gen X story, okay? So there's numerous sources of PFASs. This is some data from work that Heather Stapleton and I did. Looking at Jordan Lake, Cary drinking water, Chapel Hill drinking water, Durham, et cetera, Robeson County, and you can see that you have profiles of legacy PFASs. And then also I should mention that Heather actually did find Gen X in Jordan Lake at low levels, but it is making its way all the way to Jordan Lake, probably through atmospheric deposition. Low levels, nanogram per liter-ish. But so we need to address a wide variety of PFAS compounds from different sources in a variety of different sample types. So what's our strategy? 191 surface water sources, 149 well water sources. This is what the sampling universe looks like. So we're going to be quite busy driving around to the treatment plants to acquire samples throughout the next year or so. So our analysis strategy, we're going to collect samples, coordinating this between NCSU and Duke. So my lab and Detlef's lab are going to be the primary mass spectrometry analytical facilities in this effort. About 25 to 30 samples a week, organizing this in geographic sectors. So we're going to basically be rotating through the state, sampling using pretty standard PFAS protocols. QA/QC, we're paying close attention to the QA/QC issues to make sure that we have high veracity, high precision, high accuracy in our data. We're going to do duplicate sampling for 10% of the sites, and 20% of the sample universe is actually going to be cross-analyzed by both Detlef's lab and my lab, so that we can basically compare and cross-validate. So here's basically how we're going to do this. So our samples are going to be basically split for three modes of analysis. So we're going to do our targeted analysis with triple quadruple mass spectrometers or something similar to this, looking for a list of compounds that I'll go through in a moment. So the instrumentation that we've acquired, both in my lab as well as Detlef's lab recently, is sensitive enough to allow us to do this by direct injection. So this really speeds up our throughput. Then we're going to also do high-resolution mass spectrometry analysis. Again, we've got some harmonized instruments in my laboratory as well as Detlef's lab. Both have brand new Orbitrap systems that we can use to do high-res MS screening for PFAS through non-targeted approaches. And then May is going to get absorbable organic fluorine analysis on all of these water samples. And so we're going to use this to try to calculate our PFAS mass balance. I'm not going to read this to you, but we have a large and growing list of PFAS target compounds. So part of our strategy here is to essentially go through and find all of the possible PFAS quantitative standards that we can use to build this list from my lab, from Detlef's lab. We're also going to be cooperating with EPA, with Mark and Andy's lab at EPA to get access to standards that are relevant both to legacy PFASs as well as to the compounds that are relevant to North Carolina. You've already actually seen something about this. This is actually the EPA chemistry dashboard that Mark talked about earlier. It's curated by Tony Williams at the National Center for Computational Toxicology up the road. We're going to use this basically to pull out our PFAS suspect list that we're going to use for our suspect analysis with our Orbitrap mass spectrometer. So this is about north of 5,000 compounds. So the data analysis and dissemination, we're going to validate this and curate it based on assessment of compound ID confidence. So we've got some custom non-targeted analysis routines that we've built in my laboratory over a number of years, very analogous to the type of work that you saw earlier from Matthias Ruf and his group in Switzerland. Cross-validation of our suspect screen and our quantitative measurements, really to kind of give us enhanced confidence. and then assessment of PFAS mass balance using the adsorbable organic fluorine data that May is going to give us. And then importantly, what do we do with this data? So the data analysis and communication is really key. So we're going to work with the Team 6, PFAS Team 6, which is communications, to assess these compound IDs, concentrations against known or suspected toxicants for risk assessment, and this is based on predicted exposure and hazard. So we're going to work with our communications team for risk communication and hazard communication. We're going to work with PFAS Team 3. This is the removal performance testing. We're going to be feeding them identifications and identities of compounds that we're finding and concentrations of compounds that we're finding, so they can help to address this question: how best can we remove these compounds from water? The data summaries are going to be included in reports to the General Assembly and to stakeholders, and then we're going to have curated and georeferenced data uploaded regularly to our PFAS communications website, so that this will be accessible to the public, because this is all publicly funded work. And that's it.
Thank you, Lee. So next we're going to hear from our air emissions and atmospheric deposition team. So our co-lead that will be speaking today about this research project is Professor Barbara Turpin. She's the professor and chair of our department at UNC in environmental science and engineering. Her research focuses on combining laboratory experiments, chemical modeling, and field research to improve our understanding of linkages between the pollution emissions and human exposure.
Thank you, Jason. So this Team 4 is a collaboration between UNC Chapel Hill and UNC Wilmington, and also Mason at UNC Charlotte. And Ralph Mead is the co-team lead, but he apologizes he's not here today. The hurricane blew the roof off their building, and then they got 20 inches of rain. So the first thing he told me is his equipment is all fine, and he's moving it this weekend to another building. That's what he's doing right now. Okay, so there's a lot we don't know about the concentrations of perfluorinated and polyfluorinated compounds in air, but they have been measured in air and in atmospheric deposition. There are many more measurements in Europe, but an increasing number in the United States and in China. Human exposure to airborne PFAS is a result of direct inhalation and dermal exposure to direct emissions, and also indirect exposure as a result of atmospheric deposition into watersheds. And what are the sources of airborne PFAS? There are several. So one is, of course, production facilities like Chemours in Fayetteville, and also the use of perfluorinated or PFAS-containing products at industrial facilities and military bases, for example, and that includes, of course, you've heard about the firefighting foams, but also high-temperature lubricants and hydraulic fluids are another source, especially at military facilities. And also use of PFAS-containing products indoors in residential environments through consumer product use, and that's something we haven't heard about very much today, but something I'm concerned about, both from inhalation and dermal exposure. And then also fugitive emissions from waste streams, from wastewater treatment plants, from contaminated soil, and from landfills. We don't know very much about the atmospheric transformation of perfluorinated and polyfluorinated compounds, but PFAS is measured in the air in locations that are pretty distant from point sources. And so one hypothesis is that that is because of atmospheric gas to particle transformations that may very well occur, that we think probably do occur, and airborne particles have atmospheric lifetimes of 1 to 2 weeks, and so that would help to explain that. We're very interested in understanding those atmospheric chemical transformations. There's, as I said, a lot we don't know, and so this is my why slide. And from what we do know right now, We know that in some cases, indoor concentrations are much higher than outdoor concentrations as a result of people's use of consumer products and perhaps from showering as well. And so for those homes, indoor sources are probably the major source of their inhalation and dermal exposures. We know that concentrations are elevated near point sources, and that they're elevated in urban areas because of the waste streams, basically. So there's an awful lot that we don't know, and we don't know very much about the concentrations in ambient air. We don't know about the composition of ambient PFAS, and we don't know very much about atmospheric transformations, and all of those things will have a big impact on trying to understand the fate and the effects of these compounds. So that's my why slide. We're working on answering these questions. What PFAS compounds are present in ambient North Carolina air and in wet deposition? What is the geographic distribution, and what does that tell us about sources? What is the contribution of wet deposition to the Cape Fear watershed? And does gas to particle conversion or multi-phase atmospheric chemistry alter the fate of small polar water-soluble gases, as we have seen for other non-fluorinated organics? So we have, this is the planned approach. We will be making wet and dry deposition measurements on an event-based plan, mostly in Wilmington, but in some other locations as well. We'll do integrated gas and particle sampling every 6th day for 24-hour integrated samples over a course of a year. And here's the map. I'm still learning my way around North Carolina, but we have 5 sites, and so we're trying to identify a good site with power really in between the Chemours plant and the military base in Fayetteville. We've got a site in Charlotte and a site in Greenville at ECU, a site in Wilmington, and a site in Chapel Hill. And so, you know, in the summer, usually we have airflow from the west or from the southwest. In the winter, we can have flow from the north or the south, and we think this will give us a good deal of information about regional transport and local sources. We'll also do one intensive field campaign. We have a chemical ionization mass spec, which will give us real-time data on small polar organic compounds. And so that'll be a 1 or 2 hour intensive real-time measurement campaign in Wilmington. And we plan to look at atmospheric deposition into the Cape Fear watershed and do some controlled laboratory experiments to start to study atmospheric chemistry. And here's why we're interested in that. Here's an example. So Jason Surratt and I, most of our career, have worked on multi-phase atmospheric chemistry and looking at how small polar water-soluble organic gases are taken up into fogs and clouds and also into the wet, acidic, fine particles that we have in the southeastern United States, and the chemistry that happens as a result. And so here's one of Jason's favorite compounds here, isoprene. It's an isoprene epoxide, and that is sucked up by fine particles in North Carolina, and there's a lot of interesting chemistry that happens, but it converts those small organic gases into particulate matter, and it completely changes their fate and effects. And so then I've put one of our favorite emissions of perfluorinated compound here, HFPO, and look at that, it's an epoxide. And so we're pretty sure that nucleophilic reactions will be important, and we're interested in studying this in using the same kinds of techniques we have for other compounds in the lab. And Ralph sent this slide just to give you a little bit of data These are wet deposition measurements for 2 events. On your left is an event where the airflow is coming in from the ocean to Wilmington, and the concentrations of Gen X are quite small, below detection limits, below 3 parts per trillion. And then on the right, here's an air mass coming from the north, and the concentrations in that water are larger than 50 parts per trillion. So concentrations in the air and in rainwater can vary quite significantly. Okay, thank you for your attention.
Thank you, Barb. Our next presenter is Professor Mason. So Professor Mason is an assistant professor at UNC Charlotte. She was the lead author on the publication that showed that Gen X was in the Cape Fear Rivershed. And with that, I'll let her talk about the Team 3's project. Thank you.
Our team will focus on treatment technologies, what we can do to remove those chemicals out of our drinking water, and how do we make choices when we have multiple options open there. Our team, include myself, Orlando from UNC Chapel Hill, Frank from UNC Chapel Hill, Detlef from NC State, and Heather from Duke University. We will be looking at a few options that is already commercially available, and also some novel technologies. If you are here in the earlier talks, you know that we have talked, other speakers have mentioned that active carbon, ion exchange resin, and high pressure membranes are the major available technologies that can remove PFAS from water from different extent of effectiveness. So we will look at them and see what would be the best option between those commercially available technologies. And also, as I will mention in the next few slides, those 3 technologies are all separation technologies. They don't destruct PFAS. They only concentrate them from drinking water in large volume into a smaller stream, and the concentrated PFAS in the waste stream has to be handled properly so that they don't contaminate our environment for a second time. So we will also look at what is the possible option for handling the waste generated from resin regeneration and membrane treatment. We will not be able to do things to look at exhausted active carbon, though, at this project. And then we will move on to other novel technologies that has not been widely used in the water treatment facilities, but we will look at the performance of those novel technologies and compare them with existing technologies. And finally, we will look at, instead of the treatment plant scale, at household scale, what kind of water filters would perform best for our residents to remove PFAS from their tap water. Research needs is obvious. We need this research because we need to find out ways to get PFAS out of drinking water to make sure that people drinking the water is safe. This is to respond to the bill which asks us specifically to test the performance of relevant technologies in removing such compounds. We want to conduct the research on the existing technologies because they can be quickly adapted to the treatment plants, and the plant owners, operators need the information within these 3 technologies, which one should we choose, and within each treatment options, there are different types of carbon resin membrane out there, which one would suit the need for individual plant best. And also, how to handle the waste for the treatment plants, as I just mentioned, and what are the ways that we should look further beyond what's already available on the market. And finally, people in the affected area, the residents, they anxious of how to solve their problem, either before their treatment plants can install and operate a treatment process that we pick, or for residents who are not living with drinking water from a facility but rely on their backyard groundwater wells, what they could do to provide themselves and their families safe drinking water. We will start this research through both commercially, through the testing of both commercially available technologies and novel technologies. For the available technologies, we will evaluate the effectiveness of 10 types of carbon, 10 types of resin, and 10 types of membranes to see their treatment performance in groundwater, which is a relatively simple matrix. And the top 3 candidates from each type of technology will be screened out and will be challenged with surface water that has been contaminated with PFAS, which has more competitors, coexisting components that might better, to a greater extent, impact the effectiveness of each technology. And also, we will try to adjust the matrix a little bit for different pH, for example, to see how the performance of the top 3 candidates for each technology is about. This is about for the existing technology, and for a novel technology, we will majorly look at 2 options. One is take the existing commercially available membrane and do chemical modification to it to see which modification can, to the best, enhance the performance and lower the cost. And the second novel technology we are going to look at is to synthesize novel types of ion exchange resins that has fluorine in its backbone, so that it will have high selectivity and high affinity to PFAS to achieve better removal. And those novel technologies will be compared for the performance with existing technologies using the same groundwater, surface water, and pH-adjusted water. For the rest part, the waste handling, we will test the treatment using electrochemical oxidation to see if they can mineralize PFAS so that we have a safe handling procedure for the waste stream. We will survey about 100 households in North Carolina to take samples from their tap before and after their filter to see which kind of filter perform best, what would be the seasonal variability, what would be the impact of customer on the performance. We will use the same technologies that Team 1 just mentioned, both targeted and non-targeted analysis to look at the removal of individual compound, and also use absorbable organic fluorine analysis to look at the removal overall. And finally, we will evaluate the treatment effectiveness of every single option by both looking at the performance in terms of percentage removal and also cost and other associated factors. Thank you.
All right. So our next presenter is Professor Jackie McDonald Gibson from UNC Chapel Hill. She's an associate professor in the Department of Environmental Science and Engineering, and her research focuses on predicting population health impacts of alternative environmental policy decisions. If I can be better with finding the PowerPoints, let's see. All right, Jackie, thank you.
Well, thanks for hanging out for the afternoon, everyone. And Jason, thanks for the introduction. So this is a project that's going to be looking at trying to figure out why some private wells around the Chemours facility seem to have high levels of PFAS compounds, while others right next door don't have any problems at all, and trying to provide scientific information to figure out how to target wells at risk and what to do to prevent these kinds of risks. So the team includes me, Dr. David Genero, who is a professor of marine earth and atmospheric sciences at NC State and a hydrogeologist, and also Dr. Detlef Knappe. And I got involved in this in part because about 6 years ago, I was asked by the state health director at the time, Dr. Jeff Engel, to start looking at water quality in private wells in peri-urban areas of North Carolina that are within a stone's throw of infrastructure but don't have connections to that infrastructure. So I've been going around the state with my students for quite a while now doing some private well sampling. And there's me and one of my students looking at a well owned by this lady in the picture, and she's in a community where there's a water utility line that runs right next to her backyard, but she's still got a private well. We found a lot of water quality problems, so I got involved for that reason. And so I'll just tell you a little bit about what we're going to do. So Dr. Genero is really an international expert on looking at the transit time of groundwater through aquifer systems. Transit times can be very slow, and so there's the possibility that PFAS compounds that are in groundwater right now are going to be there for a very long time, but nobody really knows how long. So his work is going to look at how long it will take these compounds, once they're in the water, to be flushed out via natural groundwater flow. And then my part is to try to figure out, along with Dr. Genero, using data that DEQ has already provided to us, again, why some wells are contaminated and others are not, what features of the wells, the landscape, the geology, the weather, geographic location influence risks to those wells. And then, because there is so much concern in communities around the Chemours facility and potentially in the future other similar sites, develop some tools that households and also state agencies can use to identify which wells might be most at risk. So just as background on this, again, Dr. Knappe showed this map before, but this is a map that the state has prepared based on their analysis of private wells within about a 5-mile radius of the Chemours facility, and it looks like a patchwork quilt. So what you'll notice is that you'll have areas that are red, meaning in those wells, Gen X was detected above the state health-based target. Oops, sorry. See, right there, and then there'll be one right next door where it's a non-detect. So why do we see that patchwork pattern? Nobody really knows. So let's see, move on with that. And then again, a key question is, all right, so once we know that some wells are at more risk than others, how long is it going to take this stuff to flush out? So there have been controls. There's a hypothesis that a lot of the PFAS that are being found in these private wells might be a result of atmospheric deposition. So the stacks at the Chemours facility are discharging these compounds into the air, and they're later settling onto the ground, percolating into the groundwater. There's controls now to limit the air emissions, but the question is, even with those controls, are PFAS still coming into the groundwater faster than they're being flushed out by natural processes? So Dr. Genero is going to install a series of what are called wellness, which are like monitoring wells, to try to, again, quantify how quickly is this stuff still getting into the water? How quickly is it being flushed out? And then one thing that I bring to the table is I've been working on machine learning methods over the last several years that look for patterns in very complicated environmental and public health data. And I like to say that we're still using in the environmental field a lot of 20th century statistical approaches to look for patterns in data, but we need to bring 21st century approaches to solve these problems. And so the particular kind of approach I've been using is a machine learning approach called Bayesian networks that's able to uncover patterns. And this is just a picture from some of my other research that's looking at, can we understand the patterns of why some people who drink water with arsenic are at higher risk of diabetes than are others. And this is a little picture of kind of the variables that my machine learning uncovered from a sample of about 1,000 people in Mexico who live in an area with a lot of arsenic in the groundwater. And again, some get diabetes and some don't, and it turns out there's kind of complicated interactions between people's metabolism, which is represented here, their body mass index, and their exposure to arsenic, such that all these things together kind of influence the diabetes risk. So we might have a similar thing going on here with the private wells, where there's a lot of variables that might be interacting, having to do with the wells themselves, the weather patterns, the hydrogeology, and so on. And so we're going to be using that same approach. And this is just the center of this little machine learned model here is this little variable that's what's the probability that somebody's going to have diabetes. And the background in this particular population was 16%. But what you can do with this is then specify, what if I set arsenic so that arsenic here, this is the amount of arsenic in the water, is really high. Well, that influences diabetes risk by a little bit. It went up from about 16% to almost 18%. But then there's some other variables that also might have an influence. And what you can do with these also is design like a user interface. So this is a user interface for this particular one that I did for diabetes in private wells. And you can go in and enter evidence. And this one, I would say, okay, I'm a user. I enter that there's a lot of arsenic in this water. The person metabolizes arsenic very efficiently, which actually turns out that it's a higher risk factor for diabetes, and they have a high body mass index. And if you sort of change all these variables, all these things interact such that the risk of diabetes has now gone up to 41%. But anyway, the basic idea is with kind of the traditional computational methods that we've used, they're really not good at uncovering a lot of interactions. And this problem of PFAS compounds in private wells is complicated, and I'm hoping that this same kind of machine learning approach might reveal some useful insights. And that's all I have to say about that. So thank you again for staying, and thanks to my team.
I hope everyone's hanging in okay. I know it's kind of getting to be a long afternoon. So our final speaker is Dr. Jamie DeWitt from East Carolina University. Make sure I've got the right slide here. Get it, yeah. You can tell I'm a Mac user. So just quickly, I just wanted to say that Professor DeWitt's research explores relationships between biological organisms and their responses after exposure to environmental contaminants.
Thank you, Jason. Dr. Fry apologizes for not being here today. She had another obligation and was unable to attend. But I do have some additional team members who are going to join me so that they can tell you a little bit about their specific contributions to this project. I'd like to point out that our team clearly wins the award for the most innovative title. Other research approaches, other applied R&D. I guess that means we can do pretty much whatever we want. What I'd like to also point out is that our team doesn't have a specific legislative mandate. So in the wording of the bill, other applied R&D is pretty open and pretty loose. But as we tried to put together ideas for the team, we wanted to make sure to include experimental approaches that would meet some of the concerns of community members who are being exposed to PFASs. And so our team is hugely diverse as a result, but it addresses some of the issues related to context. So we're going to be getting lots and lots of information on what types of PFASs are in the environment and where they are in terms of the surface and groundwater. But what people also want to know is, what does this mean for me? What does it mean for the food that I'm eating? What does it mean for animals that live in the environment? Where else do they come from? So our team will be providing some of the context to support the findings of the other teams. And as we've heard numerous times today from all of our other speakers, PFASs are hugely complex, And to address this complex problem, we need integrated and unique approaches to address this problem. So that's what we're hoping to do with our team approach here. And what I want you to see in this particular figure is that our approaches are going to focus on sources, exposures, and effects. And so as we go, I tried to come up with a clever acronym. See what I did there? I'll laugh now. So our different approaches are going to address some alternative sources into the environment, some effects on biological organisms, including humans, and then uptake processes that might impact dietary crops that could be additional sources of exposure. So not all of our team members could be here, so I'll be trying to muddle through some of the approaches of the team members who aren't here today. And one of our first sub-projects will address this source issue. So what additional sources contribute to PFASs in the environment? And Dr. Mort Barlatz from NC State, I think he's the chair of Detlef's department, is going to be asking questions about contributions of PFASs to water from landfills. He's going to be looking at municipal solid waste landfills and leachate that comes off of those landfills, as well as contributions from construction and demolition landfills, which are not lined. And so those may be additional sources of PFASs from all of the carpets and other agents that end up into those landfills. And so his approach will allow us to understand what other sources contribute to PFASs in water apart from maybe biosolid runoff and industrial inputs and wastewater inputs. Our next approach is going to be explained by the person who designed the project, Dr. Scott Belcher from NC State.
Yeah, I'm Scott Belcher. I'm an endocrine toxicologist from NC State, and our project is really a community-based approach. Actually, we really begun with input from the community, and we're partnering with Maddie Pollard, who's back there from Cape Fear River Watch, and we were really by the community asked, you know, what's going on in my pet? What's going on in my dog, my cat? What about the fish that we're eating in this? And we had the opportunity to look at American alligators and actually fish that are in there. And you ask why American alligators? They're a lot like us. They're kind of like they're eating and drinking in the water. They're the top predators, and they don't like to leave. They like to stay in their area there, and we'll be able to look at animals that may have been there 50 years for the entire duration of the Gen X exposures, and that's kind of our goal. So we're adding on to the study that we've had to add more animals, more alligators. We're going to be sampling from striped bass in the Cape Fear River, which actually we have some benefits there. We know the genetic background of all of their fish because the striped bass do not reproduce in that river for some reason that's unknown. And we'll be able to have a reference site from the Pimlico River where they do actually reproduce, as well as the fish facility there that's coming from groundwater that should hopefully serve as a reference that is not contaminated. And we're also going to be looking at fish that are frequently consumed, probably by some of the more vulnerable communities in there. We'll be looking at largemouth bass and some of the panfish, including the sunfish. And that's kind of it in a nutshell.
Oh, who's that? This next project will focus on some of the health effects, and I'm going to be looking, and people from my lab are going to be looking at some of the immunotoxicities. In 2016, the National Toxicology Program published a systematic review of the immune effects of PFOA and PFOS. And from their review of the literature, they determined that vaccine responses were impacted by exposure in humans to PFOA and PFOS. These data were supported by findings in animal studies. They also found a certain level of evidence that natural killer cell activity was suppressed. So adaptive immune system is impacted by exposure to PFOA and PFOS, and the innate immune system is impacted by exposure to PFOA and PFOS. So we're going to ask the question, do other compounds also impact the immune system in the same way as the legacy compounds, or do they not impact the immune system in the same way, or does it differ in some way? So we'll be addressing these immune-related compounds with experimental studies so that we have some data that will help perhaps DHHS generate some reference doses for some of the additional compounds that have been discovered in the Cape Fear River and other areas of North Carolina. Dr. Owen Duckworth from NC State is not going to be able to be here, is not here today, so I'll again try to muddle through his contribution. He's going to be focusing on some of the important food crops, and as Dr. Kanape mentioned earlier, some individuals are concerned about levels of PFAS in the soil and in the water and air that might get deposited in the soil and be taken up by important dietary crops. So Dr. Duckworth is going to be looking at uptake of PFAS into these crops, as well as how soil characteristics may influence the uptake of PFASs into these crops. His proposal is pretty amazing, and there's a lot of detail to it. I am definitely underselling it, but this is going to be extremely important in helping us to understand if PFASs can move from the soil into crops that then we may consume. Our next sub-team proposal is going to be explained to us by Dr. Jackie Bangma, who is a postdoctoral research associate in Dr. Rebecca Fry's lab at UNC Chapel Hill.
Hello. So for Team 5E under Dr. Rebecca Fry, Dr. Fry is a director of the Institute for Environmental Health Solutions at UNC. So her expertise is in the field of environmental exposures, specifically in humans. She has done a lot of work on placental biomarkers and looking at placental health. And so for her specific objective, she is interested in looking at a number of matrices in North Carolina women, pregnant women specifically, what they're exposed to, whether through drinking water, what we can see in their serum, which is a very standard measurement, but also other matrices such as the placenta and cord blood. Another aim that's very important to her particular part of the study is to focus on placental cells, and that would be human placental cells in a 3D culture model that will be more environmentally relevant than hopefully 2D models are. And that is the focus for Team 5E.
So finally, our sixth team member is Dr. Nicholas Luke from North Carolina A&T. He also could not be here today, but he's going to take some of the information from studies performed in my lab and in Dr. Fry's lab and start to build some pharmacokinetic models so that we can better understand how some of these emerging PFASs move around the body. So he'll be able to build models that tell us where these compounds go in the body, perhaps what their half-lives are, so that we can make predictions about where these compounds go in the human body and what the half-life in humans would be. He also will be able to use some of the data generated from the other projects to big, larger models to help us understand a little bit of the mass balance of PFASs in the environment and understand some of the fate and transport. And we're also going to be getting some information from some of the other teams to help to build these bigger, larger scale models to understand better what's going on in the environment in terms of transfer and movement of these compounds throughout the environment. And that is the end of Team 5.
So we wanted to leave plenty of time for questions. I'm sure many of you have questions for some of the project PIs. I'm wondering if it would be easiest if the project PIs could come to the front, maybe sit at the table here, and we can add a chair. I know there's more than 4. And I would like to thank again the PIs for presenting their talks or presenting their research work that they're planning to do for the network. We have plenty of time for questions. We want this to be an open session where people can ask any questions they would like. We've tried to leave as much time as possible for that, so I think we are happy to go as long as people have questions. Oh, thanks.
I just wanted to check, are all of your methodologies state SOP certified so that the data that you do collect could be used in regulatory action, if necessary?
No. At least not for us. Others might come. That's, I mean, I'm not trying to be glib, but it's actually definitely not the intent for us to take the place of the DEQ. So, I mean, we will be collecting data, especially in the monitoring program. We'll be collecting data that will be obviously made available to DEQ. And so my personal hope is that they would use that data to develop their own methods or adapt methods that will comply with the QA, QC, and GLP requirements that they have to use in order to make regulatory measurements. That's my hope.
The immunotoxicology data will be generated following harmonized test guidelines established by the EPA and the World Health Organization for immunotoxicity testing under FIFRA and TSCA.
The absorbable organic fluorine method is not following any standards because there's no standards on that yet.
I was going to say for the private well data, we actually, DEQ has already provided us with PFAS monitoring data that they've collected for all the private wells, and we'll be expanding that data set with other information about well characteristics and proximity to the facility and hydrogeologic characteristics. So we're not actually collecting any new well water quality data for this project.
For air sampling, we'll use best practices, of course, for quality assurance, but we're developing methods so that we can measure more compounds. So some of those will be new methods.
Yes.
Thank you. Well, while we're talking about methods, as a chemistry geek, I had a question about, it came up when, Barbara, when you were talking about the atmospheric compounds, and I think, we don't know a lot about the volatile fluorinated compounds, and so, but it looked like some of the methods that you were employing were going to be still water-soluble molecules. So I was thinking, what can be done to look at things that are the more hydrophobic or maybe soil-bound or bound to dry deposition, for example?
Jason just picked up the mic, and I thought for a moment he was going to answer that question.
Oh. Well, go ahead, Barb.
I'm happy to have you.
So we have sampling methods that are established in their community that we plan to use. We can use puff sampling if we needed to, or other methods, but we have online chemical mass spectrometers that we can use to actually sample the air directly. But in terms of these more hydrophobic compounds, I'm not quite sure we can actually measure those species well, but certainly the small water-soluble compounds, we can measure those very well with the types of mass spectrometers that we have in our lab and in Barb's lab as well. Barb, do you want to add anything to that?
No, I guess, well, I will anyway. When you're talking about the sort of the semi-volatile, little bit larger compounds, we do have some nice methods for fine particle analysis, and but some of those involve derivatization, GCMS, and others, LCMS. So we'll do our best to measure as many things as we can, but I think we're going to find that there are hundreds or thousands of compounds which are really interesting and exciting. So we won't measure everything.
Yeah, I'm going to preface my question by saying I'm not trying to be critical of the collaboratory, but I have a question relating to what I view as kind of a gap in how the collaboratory is built. Recognizing that I know I am part of the collaboratory on the peripheral, and I appreciate being part of that, but all these talks were raised earlier, particularly by the legislatures, about the human health connection. And I don't see a strong focus within this to look at a lot of epi studies for human health. And I'm wondering, with all the resources there are with the North Carolina Cancer Registry and the Vital Statistics Office, why there's no research being focused on health outcomes based on regional differences in exposure.
Jackie can answer that question because Dr. Fry's project will include some evaluation of human data.
So Dr. Fry's project will include looking at cell culture, but looking at the exposure data across North Carolina, we'll be able to know what women are exposed to. But I think part of the reason that we're not able to do a full
encompassing of it, because we don't really know what everyone is exposed to, especially with all these new chemicals that just haven't been measured in human populations previously. It is a big source of exposure, but it isn't the only source of exposure. It is a good start. This is true.
Heather, let me just jump in with one point. I think it's a fair point, but I think we also have to have the data, the exposure data first. And so I think part of what we're focusing on here is actually doing the analysis to actually give the data, right? So we need that data first.
I would disagree.
Okay.
I would actually say we know enough that there are geographical differences in exposure based on the data we have already, that you could at least add to the literature, the research you're developing to say, well, we know that there is a higher risk for X cancer in this area. We do know that the levels are higher in this drinking water. Maybe this deserves more attention and follow-up studies. Those can be done now. I mean, we have capability. I'm just wondering why they're not included in this, because that seems like that's a question that gets asked a lot.
It is a question that gets asked a lot, but I think the wording of the Senate bill was explicit about what needed to be tested in terms of the water. And Dr. Belcher's project also will include some sampling of biological serum and tissues. So he will be looking at sentinel
There's no health
species.
outcome, is there?
There is the potential for some health outcomes in terms of, there's some potential to do some immunotoxicological work with some of the blood that he'll be collecting from alligators. So we will have some health outcomes associated with serum concentrations, as well as serum concentrations in our experimental models.
I would just like to encourage the collaboratory to think more about that, because I think it's a big gap in this, and I think it could also be very informative to how we move forward in that area.
Thank you. All right, just more. Yeah, Jeff, do you want to?
Heather, thank you for that comment. And I just kind of want to make a comment to everyone in here. This is going to be an evolving project. We certainly have the cornerstones of what is required. And by the time you fund those cornerstones, then you get down to what I call the kitchen sink team to do the applied and other R&D. And there's not much left monetarily. However, we are still bringing in matching grant money, and we still know we're going to supplement this project. So I think you bring up a very good point that we need to discuss further, and we may be able to tack on an additional project that runs parallel with the PFAS network project. So thank you. And for anybody in the room, let's keep having these conversations because we consider all these scopes of work evolving, and we're hoping this is not just an 18-month one-time project, that this is actually the start of an ongoing network. So.
Yeah, for the study on pregnant women, how are you determining the exposure via drinking water versus other exposures?
So since we haven't narrowed down the specific performance we're interested in at the moment, we haven't picked a specific method. But for drinking water, we have a cohort of women who have sent in their household water, and we have that frozen in storage. We also have collected samples of placenta and cord blood and their serum in order to be able to do those measurements. And that's in the process of being collected at the moment, but since we haven't narrowed down the specific perfluorinated that we're going to focus on for this particular study, we don't have all of the information parsed out just yet.
Looking at if you're finding some perfluorinateds in the placenta or the urine, how are you going to be determining that it's coming from the drinking water and not from household dust or product exposure or other sources?
We won't have household dust. We will just have drinking water, and we're not sure if drinking water will be a major source, and this will help tell us since we'll have paired drinking water with the blood. But if there's more in the blood that's not in the drinking water, we couldn't say the exact source of where that will be coming from.
Hi. I also had a similar question in regard to potential treatment technologies.
I'm really happy to see that there's water treatment technology options that are being considered and evaluated, and wanted to see whether anything was being done on the consumer side, and then also for municipal biosolids application on lands.
For the consumer side, could you please specify what exactly you mean?
Sure. So, I mean, I guess twofold. Number one, companies that produce materials that may have PFAS substances on them. And then number two, consumers, their ability to know or understand what their purchases are and how that may contribute to what may be going into their washing machines and then out to wastewater treatment plants, and their contribution to this.
For the consumer product side, we don't have that planned in our scope of work because currently we only focus on treatment of drinking water. I think consumer products are really important sources. We just don't have the capacity to do that right now. And the second one is about biosolids. Biosolids will impact surface water, groundwater, and eventually impact drinking water. So we don't have a project that is directly looking at biosolids, but indirectly just by treating drinking water. It's again limited by the scope of work that we have now.
I'll just mention on the biosolid side, so my hope is that as we start looking at the signatures of PFAS in water samples around the state, we may be able to pick out specific scenarios and areas where it looks like the major source is biosolids. You saw the slides that Detlef showed actually from Andy's work. So hopefully we can use the fingerprints of some of the PFASs to tell us something about sources, biosolids, that sort of thing.
Thanks. This one's for Jamie, I think maybe for others. So there's been a lot of mention of immunotoxicological effects and potential cancer concerns. If we think about the matrix of all the chemicals that we're considering or concerned about and the matrix of all the potential health effects or toxicological effects, how well is that matrix covered? So we're prioritizing these two, as I understand it, based on a set of studies, previous studies on a subset of those chemicals. Are we reasonably confident that focus on those endpoints covers the breadth of them, or are there areas of uncertainty there?
Oh, there are huge areas of uncertainty. If you look at the most recent public draft of the Agency for Toxic Substances and Disease Registry report, which highlighted, I believe, 14 PFASs, they emphasized some of the health points for PFOA and PFOS, and there's a variety of health endpoints ranging from liver toxicity to changes in serum cholesterol to immunotoxicity to developmental effects to effects on reproduction as well as cancer. Those are largely associated with PFOA and PFOS. There are a few associations with PFH excess, but for some of the other compounds, the health information that we have is still very limited. But from what I've been seeing in the literature and what maybe others have been seeing in the literature is that when we're starting to evaluate the alternatives or the replacements or whatever we want to call them, the emergings, some of the health data, at least for the health endpoints that we've identified for PFOA and PFOS, are producing similar outcomes. So it appears to be there's a similar suite of effects, at least on the functional phenotypic level. Whether or not they operate in the same way mechanistically is probably going to take decades to figure out. So the matrix is incomplete, but it appears to be associated with a set of effects.
Mark has a question.
So it's maybe a generic question. I've seen what each of the members of the group are doing and the teams are doing, and I'm wondering if you could, or if you have already articulated, this is my main point I'm asking. These are the data gaps we have. These are the things that we require we don't have enough information on to maybe be sent out to the greater perfluorinated compound community that could maybe respond and say, okay, we have some of that data you need, or we know where to find it. I don't know where y'all are at in the process. Are you doing that?
Who wants to start that one?
I think I'm the dumb one. I'm not sure if I really understand your question. It was too high level.
So The main point is, so you have a major question you're trying to ask, and where do you need help? Where don't you have enough information? And what information that if you got would help you do or answer the question you have, and put that out to the broader PFAS community that may have some information that helps contribute and answer that.
Well, I can answer that from the immunotox side. Doses. What concentrations should I administer to test organisms? And do I use just what's been measured in the water, or do I titrate those in a different way to reflect what we've already seen in other test organisms? Because I think you know as well as I do that when you're working with emerging contaminants, there's very little data. So what concentration do we administer to test organisms?
I'll just mention, I think that it's a great question, Mark, and one that I think we all are sort of utilizing our own networks, right, to get that information, but I think that's a very informal way to do it. I mean, far be it for me to suggest more oversight, but I actually think that an external advisory board for this project would be a good resource. That would include people that are not necessarily sitting here at the table, but perhaps are leaders across the world in PFAS. And so having that sort of oversight and advisement actually would be really useful. The problem is that the time frame that this project is operating under is so fast. We're going to have to use at least our own networks, but also hopefully some kind of hybrid EAB type of approach. So that's the only thing I have to say about it.
Any of the other leads want to add anything?
So to answer the question about the major data gap for the treatment team, our work is pretty application oriented. We just want to answer the questions, what do we do about PFAS in our water? And that's the key driving force. That's what the major conclusion we want to make, and that's the key information we want to spread out if we successfully achieve all the goals of our research.
So I would say we're working now to optimize our sampling strategy and our analysis protocols. And so, looking at breakthrough, looking at compound separation. And so what we need to do now is pick a suite of compounds for which we can get standards, and sort of an optimized suite of things that will be, that we expect to find in the air to help us to do that. And so people like yourself would be very helpful in doing that. And we're drawing on the literature, especially from Europe. And then I keep reaching out to my colleagues on other teams as well who have more experience with PFAS work.
Detlef, if you had a question.
It's not a question, but maybe also in response to what Mark was asking. We have a parallel project that's about to begin that's funded by ESTCP. And so for the treatment side of things, this project will focus on a life cycle costing assessment of treatment technologies, but it's focused more on the remediation side of things. So as part of this project, we have actually meetings scheduled, sort of an expert panel to help us populate the parameters we need for the life cycle costing and analysis model. So one possibility could be that for Team 3, we participate or include the PFAS team, so that what we do in the surface water treatment context, and maybe to some extent for the private well community context, that we generate the right kind of data that would then also help inform that life cycle exercise.
Sorry, I see him.
So I have a question about the water sampling. I'm really thankful for Dr. Ferguson and Dr. Knappy's work in the HAW, and some of the results that we've seen have changed with times of high flow or low flow or just random spikes. So do you think that sampling 1 to 2 times a year is enough to confidently capture those issues?
This is great. I can answer all my questions with no. So no, it's not. It's definitely not. I mean, in all seriousness, the ideal scenario would be basically a reimagination of Matthias Ruff's presentation for every sampling site that we are mandated to sample in North Carolina. But the cost and effort for that would be incredible. Because, so the challenge, or the balance we have to strike is if we take grab samples, then of course we're only getting a snapshot of that moment, and that's a big concern where we have flowing rivers, where the surface water, drinking water source is flowing. If it's a lake or maybe it doesn't change quite as quickly, but still there would be seasonality. So just as Jeff was saying earlier, we hope that this is the beginning of a process that will continue past the 18 months. Ideally, what we'd find is the ability to prioritize sites that might be specifically sensitive to PFAS in this case, that we could then target to go back and do periodic sampling so we can understand something about the periodicity, the changes in concentration with wet versus dry conditions, changes in seasonality because of temperature, or so for example in beach communities where the population changes in the summer versus the winter. All of these things are going to affect. And so yeah, I think that it's not ideal for us to only sample 2 or 3 times during this period, but it's a start that should let us at least help to prioritize. So.
And then my one quick follow-up question to that is, will you be able to collect all of those samples within one watershed within the same time period, so you can at least target spikes from one site to the next?
Well, that's a good question.
Sources?
Yeah, it's a good. What I can say about that, and I mean, Detlef, if you want to jump in on this, we're going to. We're still kind of in the process of trying to strategize how best to time the sampling. So, for example, it'd be difficult, I think, for us to do the entire Cape Fear watershed, for example, within, say, a week, because that it's going to be a lot of samples. So, we would like to try to focus sort of geographically and sort of rotate through geographic regions when we take the samples, both so that it's feasible as well as so that the data is meaningful. Detlef, do you have anything else to say about that?
Yeah, I think it's going to be hard to capture spikes that way. There's actually, in my view, almost a better chance to randomly sample, and then you have a better chance of seeing the watershed a few times instead of just one time. So within the limits of what we can do, I think that's, yeah, it is a limitation, but I probably would not recommend trying to do the watershed just in a single day.
So in the spirit of external advice, I will say there has been some good work on the development of active uptake, not active uptake, but passive samplers. And I think your statewide effort would be a great opportunity to try and see to what extent that applies, in particularly given the potential to pair with a lot of grab samples. So happy to talk later about that, but there's been some really good work on those.
That's actually something we've discussed at length, and actually so we've got experience using passive samplers in combination with grab samplers, not within North Carolina, but in San Francisco Bay and some other areas. And yeah, it's great to get a overview of what's there. The problem is making it quantitative in any way, and also I'm not sure. I certainly don't have any experience with knowing how well the sort of suite of PFAS is selected by things like Hostess samplers or silicone and that kind of thing. But I would love to pick your brain on that. We should do that.
So I'm excited about passive samplers. I'm quite confident that we can use passive samplers quantitatively for organic gases, perfluorinated organic gases. And that would be great because we can measure in a lot of people's homes, outside their homes, you know, and with distance from sources. We could learn a lot from that. I just wasn't confident that we could do that with this short turnaround with the kinds of quality assurance we needed. We just need a little more time to get to do the prep work.
Yes, I had actually two questions. The first one, I realize research takes a long time and it's a hard process, but I'm wondering in the interim, is there any thought to doing some research to try and protect some of the receptors that are being impacted right now? As an example, so we have situations where we have concentrations in the soil that are eventually getting to the private wells. We have things that are in the air that is getting, to the soil, et cetera. We have things in the groundwater that are going to get to the rivers. Is there any thought to some research that can be developed to protect these receptors before we get these impacts? Because as we all know, it's harder to then treat these receptors once we have the impacts. And then the second question I had was with the situation with Florence, some of the data that's out there, particularly some of the data that DEQ gave on the private wells, has that data now been tainted a bit because of the impact of Florence and what that has done?
I don't know who wants to take that question first. Detlef.
And I think those are really good questions. In terms of protecting receptors, and the first line of defense really is to stop the emissions from the Chemours facility, for example, and that's already being done, right? So, and they're filtering the air now through activated carbon, and the rainwater sampling event that just immediately after the GAC installation actually showed non-detects in the rainwater. Now we'll have to see how long and this will last, right? And the wastewater is being captured. So I think there are a lot of efforts, at least at that facility, to prevent the stuff from getting into the environment already. Now there are many other locations, like I showed in my talk, where PFAS are originating, and so that remains to be seen. But I think so the treatment team, the information that will be gathered is one way, to protect, for example, PFAS from entering, let's say, Lake Brent in Greensboro. Right? You can develop remediation technologies at the source where the PFAS are originating. So I think the treatment team will inform some of the needs associated with protecting receptors. Now the Florence question, we did collect some private well water samples post-Florence several days in a row to see what's happening as a result of that input, whether there is a fairly immediate change or not. They're high porosity soils, so it's possible that you see a quick change, but I would imagine it won't last too long.
Anybody want to add anything else up there?
Oh, the air was quite clean for a couple of days there.
In the back of the room, Jason.
Oh, where? Yes.
So it sounds like there's a lot of new data that's going to be collected, and it's a great first step, but there's a lot of uncertainty, and it's not going to be comprehensive, right? And there's been some discussion of prioritizing and the risks, and I'm wondering whether there's going to be any formal risk ranking or risk prioritization recommendations moving forward out of this, or whether at this point it's going to be kind of more informal based on these individual studies, and that would be something to be done at a later date.
Well, we do have this executive advisory committee, and that's a great suggestion for us to consider. I think the advisory committee at the end needs to look at the results across all the projects and figure out, where are the most important areas for future focus and which contaminants. So I think that's a really good idea. Yes, right.
Yeah, and also we have our risk communication team. So our communications team in this case is not just a sort of website development team. This is a team that is also involved in risk communication. So Jane Hoppin's a member of that team, and I know that's going to be a critical part of the synthesis of this work. So what we wanted to avoid is just going out and making measurements for measurement's sake. So taking advantage of the expertise we have to try to get a handle on risk as much as we can, certainly be part of it.
Yeah, I was wondering if you could tell me, as part of the communication plan for the collaboratory, does it involve how to share knowledge with the state agencies and regulatory community?
So I see Kathleen. Do you want to put you on the spot, and do you want to answer that question? Oh.
I was just wondering, I know that there's some effort to work on the communication of what's been gained, and I was wondering if that included knowledge sharing with state agencies and regulatory communities.
Thank you. Hi, I'm Kathleen Gray with UNC Chapel Hill Center for Environmental Health and Susceptibility. So yes, part of the goals of the communication team are to share results from the project to audiences that want them and can benefit from them. So that hasn't been fully scoped out because, as you heard from Jason, all of us are waiting for final approval on ideas that we've suggested. But for us, some of the communications activity is focused on briefings with specific stakeholder audiences. And I would encourage anyone who's in the room who is interested in such a briefing to come talk to me, or Jory Weintraub is here too. Jane had to leave early today, but come talk to us before you leave, because we're looking forward for the next year to figure out who those briefings will be set up with and which projects of all of these they will focus on. And if it is more of an overview of the entire project, well, that is definitely going to be towards the far end and will be an active dialogue with all our PIs. But yes, I know that Lee and Detlef and Jason and others have already met with DEQ, and there have been ongoing conversations about their interest in this study and their concerns about the study. So there is active conversation and dialogue, and please speak to us if you want to talk further about specific briefings.
Is there a hand I missed over here? I thought I saw one. Any other questions? Are people tired? Probably. Yeah, I see a couple people staring at me. All right. Well, if there are no other questions, I'd like to thank the speakers again who are at the panel there. Thank you.
Clap for ourselves.
And I just want to say from the PFAS network, thank you to Lee Ferguson and his team for hosting us this afternoon, and again the sponsors for funding the events, and all of the external experts as well, some of whom we've sought out advice as we've been building our network, and many of them are in the room here. So thank you guys for your input as well, and we certainly will take the input that's been given from this session into consideration as we move forward. So thank you very much. We appreciate it. And I think Lee might want to add a few closing comments.
Yeah, so not much. I don't want to keep you guys long, but one thing I do want to make sure I do is acknowledge so Sarah Phillips, who is sitting in the back there. She was the one who made this really happen, so I want to thank her for the hard work helping to organize this, as well as the rest of the EAC, and also in particular I want to call out Jeff Warren for his leadership up till now on getting the policy, the NC Policy Collaboratory engaged with all of us as academic researchers in making this this happen quickly so that we can really get the work done. So thank you, Jeff. So. And finally, to Jason, my co-chair, for the leadership also. So thank you, Jason. Okay. Thanks, everyone.